Hello everyone. Welcome to ICRA and welcome to this workshop at the very beginning of the first day. So I'm very excited and very pleasure to welcome you to this workshop on Dexterity with Multifingered hand, covering hand hardware, sensing, and skills. My name is Zhi, and I'm currently a researcher at Amazon and also incoming faculty at University of Chicago. So in the first slides, there will be a website link, so you can see all the information by scanning the QR code. This QR code will also be appearing in the next slides. So to start, I want to set the context that robotics is a very fast-growing field. I think everyone will have this impression that knows the fact that there are huge investments from industries or venture capitals to invest in this field, especially in more general purpose and AI-driven robots. And as I show here, so there are many humanoid robots, and one of the most challenging and exciting area of humanoid robots is arguably the dexterous hand. And nowadays, in the past several years, we have seen a huge amount of companies not only doing robotics, but they are specifically doing dexterous hand. And only in this ICRA conference, we can see like more than 10, almost 20 different hardware companies showing off their demos and hardwares. And in addition to the huge investment from industry, we also have a very growing interest in academia, like the government investing in academia research. For example, in the US, we have the NSF and ERC centers, and then we have huge amounts of partners and research leads from different academic institutions to contribute to this effort. And in the UK, we also have the area program focuses on robot dexterity. And I also have some very interesting quantitative numbers. So in archive, that I think every people know. So if you can search by a specific time frame by specific keywords. So if you search dexterous in archive and then get some statistics over the few years, what is the number of papers containing the dexterous in their titles, you will see an interesting trend. So this is a figure I showed in last year's RSS. It's a similar workshop, dexterous manipulation workshop. We have seen at that time, so there is almost exponential growing, even in the middle of 2025. And this trend keeps continuing, and in the whole year of 2025, you can see there are maybe more than 5 times more papers in 2025 compared to 2024. And the same trend also happens this year. So this year, we have past 5 months, not even half of the year. We have seen like the similar, very fast-growing trend in dexterous manipulation. So I think this really indicates it's the right time to invest more of your research into this field. And it's also the right time to bring people together to discuss what is the most exciting topics and take inspirations and motivations from each other. And that's our major motivation of organizing this workshop. So in this workshop, our schedule will look at the following. So if you also scan the QR code, you can get the full program. So we were going to split the whole day to be morning and afternoon sessions. And each session will contain several invited talks, also contributing spotlight talks, as well as panel discussions. And of course, poster sessions right after the spotlight talk. And in the afternoon, we also have a similar organized schedule. And today, we also very excited to have 9 invited speakers, which covers different research topics spanning from hardware, learnings, as well as the algorithmal systems. And we are also very gratitude that we got sponsored from Rika Robots and Agile Robots that sponsored the Best Paper Awards for our workshop. And there are, of course, huge amount of work of organizing this workshop. I also want to say thank you for my co-organizers, Kenny and Shuang and Cheng, and also Lei, Sanjay, and Kevin. So with that, without further ado, I will going to invite the first speakers, Pulkit Agrawal. Pulkit is an associate professor in the UX department at MIT. So his research has been broadly spanning AI and robotics. And in Dexterous manipulation, he has done a full stack of research, including from hardware design, data collection device, or learning systems, which inspired a lot of people's research, including myself. Okay.
Thank you for having me, and thank you for organizing this very timely workshop. So today I'll share my thoughts on Dexterous manipulation, but in context of multi-finger manipulation. So if we if we look at what's happening in a lot of robot learning today, is that there are these large-scale efforts to collect data to train VLA models. But these VLA models have come a long way, and they can do things which are very impressive. And we couldn't have imagined a few years ago that we'll be able to do these things. But it's also good to contextualize them in context of what humans are able to do. Okay, so, for example, here is the state-of-the-art VLA, which is packing these phones. It's impressive in what it can do. But let's compare this to what humans are doing on factory lines. And so here's a video of humans packing phones. So if you look at these videos side by side, the one thing that you will notice is how fast humans are at performing the task. And that is what is known as throughput, which is how many tasks can you perform in a particular unit of time. And this is what people care about when they want to deploy robotic systems. So I like to think about these robots along these two axes. Axis number one is the speed and reliability, which is a measure of throughput. The axis number two is how general these robotic systems are. So historically, we had industrial robots which were very specific in doing a few things, but they had high throughputs. Right? Now we have a lot of machine learning robots which are more general, but they lack the speed and reliability which is required to make them useful. So the question that I've been asking is, how do we go to these robotic systems which are both general but also have this high throughput? And some people would contend that this is about collecting more data, but this is what I disagree with. And I'm going to present my views on how do we get there. So the one thing which comes along a lot when talking about dexterity is the role of tactile sensors. And I think the community is very divided, where some people say, hey, we don't need tactile, versus some people saying tactile is very important. Now, of course, if something is not visible, we do need tactile sensing to feel things. But that's not the scenario we're talking about. Right? Let's talk about scenarios where things are visible. Then what is the role of tactile sensing? So to investigate this, we conducted a sequence of experiments. So what we did is we had humans who are wearing these pods. And these pods you can think are kind of silicone gloves that you can wear. And what we did was after people wore these gloves, we made many different gloves so we can vary how much force a human can feel, and also what is the spatial resolution of sensing the human can feel. And this gave us this 2D plot where on the x-axis is spatial resolution On the y-axis is how much force you feel. So top left is where you feel more, and bottom right is where you feel less. Then each black dot is a different glove that we made for the human to wear. Then this is work done by Lawrence, who is a postdoc, and we analyze this on 2 tasks, which come as part of a manufacturing challenge where you have to pick up these small items, like M2 screws and nuts, and insert them in the slots in both of these tasks. And what we did was we computed throughput. Now, what does throughput mean? If I give you, say, 2 minutes of time or 3 minutes of time, how many times are you able to perform the task? And the results are the following. So what we found is that the more high resolution tactile sensing you have, the higher is the throughput that humans are able to achieve. Right? So red means the throughput is high, and the blue means the throughput is low. Right? So what you see is on the top left, the dots are colored in red. On the bottom right, the dots are colored more in blue. And so what this is indicating is the role of tactile sensing is not magical, that you can do some tasks, that you couldn't do some tasks before and now you're able to do some tasks. The role of tactile sensing is to increase the throughput. But today, when we evaluate a lot of our robotic systems, what we are measuring is accuracy, which says what is my success rate. But success rate is not the same as throughput, because that doesn't include how fast you are able to perform the task. So I think once we move towards measuring throughput in our robotic systems, I think this question will no longer be asked, do we need tactile or not, but the role of tactile would be quite obvious. So that's the first takeaway, which is, hey, if you want to have these robotic hands optimized for throughput, which in our opinion is the right metric to be optimizing for, we do need higher resolution tactile. The second question, which people are often divided about, is do we need 2-finger grippers or do we need 5-finger hands? Like, how many of you are for 2-finger grippers? No? How many of you are for 5-finger hands? Okay. We do need one.
In between.
3. How many for 3? Great. So again, thinking about this throughput, helps us, figure out how many degrees of freedom are required. Right? So if you have a 2-finger hand, right, or a 3-finger hand, now suppose if I could take out my wallet and open it, I can do it, with just 2 fingers, but then I'll have to move it into a different arm, again re-grasp it, and again perform manipulations. So the point is, the lesser number of degrees of freedom you have, the more time it takes you to perform the task. The larger number of degrees of freedom one has, especially closer to the object, you can go faster. Right? Then another thing which happens is, the more degrees of freedom you have, the less precise each finger motion needs to be. And if you're building a machine learning system, you want to deal with less precise predictions. So in some ways, having more fingers helps you both go faster and also be more reliable, which is the same as throughput. So again, if you're optimizing for throughput, there is no debate whether it's 2, 3, or 5. It's just a matter of how high you want your throughput to be. The higher you want, the more degrees you should add. Of course, it comes at a mechanical cost, so we should be aware of it. But the principle being more dots closer to object increases throughput. And I'll show you, some examples of this. Even in the context of not just the hand, I think we get fascinated with dexterity and hand. I would like you to start thinking about dexterity as throughput. And if there are 2 robotic systems which have to perform, which come in, you want to evaluate them, then the way you can evaluate which one is more dexterous is to compare the 2. Right? And then when we think about manipulation, it's easy to get focus on the hands, but the arms also become equally important. Right? So this is a typical design of the arms that you might buy off the shelf. This is a UR arm. Now what you see is this arm has wrists which are serial. They're not collocated. So even if you have to move by a small amount, you have to move your arm by a big amount. What this means is, going into constrained spaces becomes challenging. And this is possibly a reason why we are seeing a lot of manipulation happening on tabletop. Right? So what we wanted to do was to change this. So we came up with a wrist design in which joints are co-located. Now again, co-located joints is not a new idea in wrist design. I think what we did was we made this wrist with quasi-direct-drive actuators, which also makes the wrist be good for forceful interaction. And this is something I'll show you shortly. But once you start having co-located joints, what this enables is, as compared to a wrist which doesn't have co-located joints, we can go into more cluttered spaces and still take out objects, as you're seeing on the right. So you can go into more cluttered spaces. And if you look at a lot of the hardware that we have today, this is a human moving one of the Z1 arm. You see the arm is really, really stiff. These arms have been designed to move precisely to a position, but they're not really designed to interact with the physical world, which is different from what's happening in locomotion, where a lot of these actuators and legs are very force transfer. So it's very easy to ascribe all the advances which have happened in locomotion to software, but could only happen if we had the right hardware. So it's a combination of hardware and software which led to these advances. So in the same spirit, we took this, the kinematics that I was showing you, but augmented this kinematics in a way that these hands are also good for forceful interaction. For the wrist, as you can see, can move quite fast. It can take up to 5 kilograms of payload and has a small gear ratio, which means the movement of the wrist also tells you how much force the wrist is applying. And just to illustrate the kind of dynamic things we can do with the wrist, this is a pre-programmed behavior, this is not learned. And here is where we actually go and learn policies, and we are learning policies on the task of wiping something on the blackboard. Now this is something it is well studied under impedance control that we can do. But the question becomes, how easy or hard is it to implement an impedance control? So if you have an arm or a wrist which is making contact, and then the wrist is moving fast, then if you have small errors in your location of the blackboard, right, then this can generate a large force which can trigger your safety settings. Right? And this can happen even before the impedance control becomes active. So this is why typically, even if you are wiping, you'll have to wipe slowly, if your wrists have not been designed with the perspective of being compliant. Versus if a wrist is compliant, it can absorb these errors in the mechanical hardware, making the job of machine learning become much easier. So, in summary, what we found is, Dexterous does two things. One, because of the kinematic structure, if you're collecting data with it, the trajectory length is smaller, because you can move much more naturally. And this results into, higher performance. Now, why is that? Because in machine learning, if you're doing reinforcement learning or imitation learning, your episode length determines how efficient your machine learning algorithm is. In RL, that becomes a great assignment problem. In imitation learning, we all know the performance scales worse with the length of the episode. So because we have these smaller episodes, our performance also improves, and the system can also go fast. So the same ideas, we have also been transporting to, our designs of our hands. So this is an eyesight hand, which is covered, fully in tactile sensing, based on the insights that I showed you before. That high resolution tactile sensing can help one go faster. These are just side sensors which have been put on this hand. Again, this hand can move fast. This hand is super compliant. So it's really being made for forceful interaction. And this is an example, showing this hand, while grabbing an object, it is not afraid of making contacts. Which does two things. One, this allows the hands to go fast. Second, if you have any error in your perception or in your vision system, the hand can compensate for it, because the moment it touches the table, it knows it has touched the table and can close the grip. At the same time, the hand can manipulate, objects which are heavy, or at least 2 to 3 kilograms, which is a lot of everyday objects around us. So as we were developing these hands, we were also thinking about, hey, what can we start doing with multi-fingered hands? And to investigate that, we put mechanical linkages to connect the robotic hand with the human hand. Now, as compared to teleoperation, where you're only visually looking at what the human is doing, with teleoperation, you have these mechanical linkages between your robotic finger and the human finger. And because of this mechanical linkage, you get joint level feedback. And because we're getting this joint level force feedback, it enables the human to go faster on a range of dexterous tasks. So again, these policies are not automated, but are showing the value of having force feedback, in collecting both faster data and also higher quality of data being collected. And this is something that we, quantified. And what we found is, teleoperation, which involves this force feedback, helps you achieve higher throughput than just doing teleoperation. So, to summarize what we have seen until now is the role of tactile sensing in producing higher throughput, thinking about, kinematics and the dynamics of the hand in context of throughput, which helps us resolve some of these debates of whether we should have 2-fingered, 5-fingered hands, what should the kinematic structure look like. Then the other thing that we always like to do is to say, hey, can we co-design our hands along with my controller? And this is something has been an active area of research in the community for a long time. We were also attempting this a few years ago to co-optimize the hand for the particular task that we are doing. But the challenge in co-optimization always becomes is that your metric of performance, if it is success rate, you have to train the whole policy to get to that success rate. So you aren't able to do that co-optimization that easily. And so people have come up with many different metrics to overcome this problem. So the question being, can we somehow not have to train the entire policy either through behavioral cloning or in simulation? Because even in simulation, to train policies requires a lot of reward design. Can we somehow not do it and still optimize my hand design? So, in the literature, if you go deep at it, there are many metrics which have been proposed, which measure how much is the reachability of the fingers, what is the reachability of the palm, so on and so forth. And even talking about how each finger and how much force it can apply. But a lot of these proxies are not telling me what are the kind of tasks my robotic hand can do. They're telling me what is the range of motion and what is the range of forces my hands can apply, which is not the same thing. So we wanted to take a step towards this direction to not just measure the hand and fingertip motion, but also how much can the hand move objects. And we stuck with a particular definition, which is to say, if I hold an object in my hand, how much can I translate it and how much can I rotate it? And that is a good proxy for saying how dexterous my robotic hand would be. So we proposed this metric called karma. And there are 3 variants of karma. They're measuring translation, rotation, and how sensitive the hand is in where it has grasped the object and being able to manipulate the object. So what the karma metric takes as input is a kinematic model of the hand and tells you how much the hand can translate or rotate the object and how robust it is to where it has grasped this particular object. The algorithm is pretty straightforward. You take, for example, a spare that you hold in your hands, and then we generate many different schemes of many different grasps, or many different initial grasps. Then we translate. We figure out how much we can translate the spare. We can figure out how much we can rotate the spare, and that gives us a metric of what is the volume of translation, what is the volume of rotation, and how sensitive it is to the initial position in which the spare has been done. So as an example of doing it on a couple of different hands, where the hand is moving the sphere, and we are calculating the translation and rotation ranges. And what we have found until now, and this is still work that is in progress, is we can decouple the rotation and the translation ability of hands. For example, the lead hand has 2x the karma score of the allegro hand. We are able to, the other thing we are able to find is that if you have more degrees of freedom, then your hand is more robust to the initial grasp location, because you can always reorient the object with more degrees of freedom. So the initial grasp matters less. It also provides an explanation for why we need thumb opposition when we are designing robotic hands. So, going back to the picture that we started off with, right? We said, hey, we want to optimize for two things, throughput and gentality. And what I have discussed until now are these hardware design principles which help us optimize for throughput. Now, of course, the next question becomes is, what about control? And I also know I'm probably, getting close to my time. So I'll maybe take a few more minutes to discuss about things on the control side. So on the control side, I think the technology that has worked well in machine learning is learning from passive data, which a lot of large language models have been working on. The question is this the right technology for doing physical interactions? To make the point, let's look at the map. So whenever we are training any system, we are optimizing a cost function or a reward function, say J. The policy is pi of theta. Now the same is happening for LLMs and same is happening for robotic policies. Now in both cases, we are learning a stochastic policy. The difference though is that in LLMs, there is no noise in sensing, there is no noise in execution, and even the dynamic model is deterministic. Versus in the physical world, all of these things are super noisy. So if you want our systems to be reliable, what we should be optimizing for is the performance under the data distribution denoising. Because if we can't be reliable under that data distribution, we are not going to perform the task. And this is where I think if we only go and learn from human collected data, which I call passive data, we are crossing our fingers and hoping that humans are going to induce the right noisy data distribution that the robot is going to encounter. Versus the other way of trying to get the data distribution naturally is for the robot to roll out its actions on its own. So the robot is acting and collecting its own data, then you will naturally induce the right data distribution. And one way of doing this is through reinforcement learning. And that's why we have been, in my lab, a big fan of pursuing reinforcement learning as a way of building reliable systems. So, going back to some of the older work, right, we were training these RL policies in simulation to perform object reorientation, which we showed in the past, could be transferred, into the real world. Right? So there's an example of the hand reorienting the object to the orientation shown in the top right. And here's an example of the hand rotating a squash, so a second arm can come and pivot. Now, when you're training things in simulation and attempting sim to real, there are many challenges which have got to do with reward design, environment design, so on and so forth. So those are some things that we have been tackling. But there's one particular thing I would want to point your attention to is the fact that details matter a lot when we are doing sim to real, or even doing any kind of manipulation. So to give an idea of that, so let me show you these two rollouts coming from two policies which are trained. They have been trained with the same amount of data. But once we roll them out, the performance is very different. Okay, so the architecture is the same, the amount of data is the same. Anyone would like to guess, what might be the difference between the two policies? Yes?
Maybe data augmentation different?
No, what difference?
Different data augmentation?
Same data augmentations, which have been used. Yeah.
One of them seems to think of the problem as purely planar, and the other one seems to think of it as 3D.
Okay, so one is planar versus 3D. Yes, in the back.
I think KP and KE are different.
The KP and KD are different.
Yeah.
Yeah, so in the interest of time, let me not take more responses. But the only difference between these two policies really is, which achieves drastically different success rates, is what the controller gains were. Everything else in the policy remains the same. And I think what we have done today in machine learning is, once you think about a task, we put this neural network model which outputs joint handles. Right, this is where we say the intelligence lives. All the dynamics is something that we treat as a black box. This is where the actual physical interactions are happening. But small changes in the physical interaction can lead to big changes in your task performance. Right? This is just trying to illustrate this with the example of this Rube Goldberg, right, where a small change can trigger a big downstream reaction. So I think we have to pay attention to this physical interaction part. If we don't do it, then we are going to have suboptimal policies. So once you start looking at this problem, right, I'm sure that a lot of you are optimizing for controller gains. And there is this classic notion in control theory that if you choose high KP, your controller becomes stiff. If you choose KD, you can change the damping of the controller. But when you're doing machine learning, these intuitions are different. Like, actually, the controller gains are not changing how compliant your robot is. You can achieve compliant behavior with very stiff gains. You can achieve stiff behavior with very compliant gains. What the controller gains are actually doing is they're affecting your policy learning. So, in interest of time, I will summarize and say that how you should choose your controller gains depends on what machine learning method you're using. If you're using behavior cloning, you should use compliant plus overdamped gains, because if you have any errors in your execution, the compliance will solve it, and your performance will still be more robust. If you're doing reinforcement learning, pretty much any gain regime is fine. It's just a matter of tuning hyperparameters. If you're doing sim to real, stiff and overdamped regime is not good. So in summary, I showed you some thoughts about how we can go from where we are in machine learning today to start building more generally useful robotics. And we discussed both in context of hardware and control. Now, before I end, I'll just do a small advertisement for our company ETA. If you're interested, you can learn more about it. But we have been taking this idea of optimizing for throughput at the core. And here's an example of us maybe trying to pick up a light bulb. And this robot is moving at 1x speeds, as you can see in this video, where it goes, picks up the light bulb, puts it on, or over here, trying to grasp a raspberry, and everything working at 1x speed. And this is it grasping the raspberry at 1/25th the speed. So again, if you are interested, we are hiring. So feel free to reach out. And with that, thank you, and happy to take any questions.
For the interest of time, maybe we just take one question. Yeah, over there. Yeah.
So, really amazing talk. But I was wondering, while we are taking force data, do we take the image data because we get the image from the gel side, or do you take the force data? I mean, what's more reliable, and how does it affect generalization across different objects or different tasks?
Yeah, so I think images and forces play a different role. I think images is good for doing planning, and even, for example, knowing what should be my initial graph force, for example. But in the control, to me, is how do you interact with the physical world? Like, how much force you have to apply, how do you react, if something unexpected happens. This is where a lot of force data is useful.
Okay, sorry, for the interest of time, we can Professor Rika Antonova. Rika is an associate professor at the University of Cambridge. Her research interests including data efficient reinforcement learning algorithms, active learning and explorations, and robotics. So Rika did her postdoc in Stanford, and before that she received her PhD at KTH. And without further ado, I'll give the stage to you, Rika.
On the topic of co-design, which is great because that sets up the stage for what I am about to talk right now. The whole talk today is going to be specifically focusing on co-design. So we'll take a look at what are the consequential things when we're considering dexterous manipulation, but I will just also be considering general question of co-design for robotics. So there are some fascinating examples of what I would call a manual co-design. We just hosted a speaker from the ICRA project at the Robotics and AI Institute, and he shared some of the things about how this robot was constructed and what considerations went into really pushing the limits of hardware design for really dynamic manipulation. This was manual design, but it was still called a co-design because they considered certain tasks, like for example, throwing a ball, like in a baseball game, and batting it back to a human. So the open question is how we can co-design this automatically. Another example of manual co-design that I would like to highlight is under robotics. With some of the graduates from Stanford started this company for general manipulation of everyday objects in everyday environments. And you can see here what is being showcased is a fairly non-trivial for a robot kind of manipulation maneuver. But the interesting part is that one of the strengths, as I can see, of this kind of setup is that they've made the hand kind of close the sympterial gap on itself in a sense. So the hardware has been simplified enough so that it is easy for human to collect data so that you can transfer it. So these are examples of what I would call manual co-design, even though these companies or research labs haven't specifically focused on co-design as a goal. Why is co-design not ubiquitous yet? Why are we still talking about manual co-design? So one of the reasons is that co-design had a few waves. So in the 90s and maybe even a bit before, in 2000s and 2010s, and most of the time it has been confined to simulation. So it has been fairly expensive to transfer it has been fairly expensive to even train complex policies back then in simulation, but then to transfer this to hardware was even more challenging, and kind of the manufacturing technique for mobile hardware have been, pretty expensive back then. So what has changed? We now have ubiquitous low-cost hardware. So you will probably see a number of talks here presenting kind of work that utilizes low-cost hands even, right? So it's not even just low-cost, very simple robot morphology, but even something like a dexterous hand, maybe even an anthropomorphic hand. So, for example, we work with CMU read hand, but there are a number of other hands that are out there that one can pick and choose. There are some are fully actuated, some are tendon-driven, and they have different pros and cons when you consider how well they would work for co-design. The second aspect that has changed is we now have scalable policy learning. So that in part came from the innovation from the learning community, not necessarily just robotics community pushing forward, and we're benefiting from a lot of basically off-the-shelf components that were designed in machine learning in general. But now we also have scalable simulators that are specifically simulating robotics, let's say parallel robotics environments that are conducive to training with, let's say, reinforcement learning or some other methods that really need scale. So this combined together is missing one other component that I will talk about, but already has the ingredients that people in the 90s, 2000s, and even 2010s did not have for co-design. And so there is a possibility here to transition this to actual reality. And here by co-design, I mean automatic co-design. So something that can utilize an algorithm in order to find the new shape of the robot, to find the updated properties of the materials that are used in the robot actuation, and also the policy. So what is still needed? I think one of the things that would really be helpful is an end-to-end scalable framework or a number of such frameworks with hardware validation. So something that people can get started with and work on, let's say, a particular, improving a particular component, but really have access to the whole co-design loop, potentially later on with hardware and optimization. So one of the things that are coming out of the UK right now is that there's a new funding agency called ARIA, who is actually a real believer in automatic co-design. So they have started a program that part of which specifically focuses on making smarter robot bodies, and in particular incorporating automated co-design into the design and developing of the novel hardware. So Cambridge has a few projects, some of them are on more low-level and hardware development, like incorporating novel sensing, either particular novel sensing technologies or full body sensing, so like high coverage sensing. And I and my group have a project specifically on co-design, and so with that we're hoping, with also a number of other UK, US, and Swiss collaborators to be able to address this problem. So it's not just an effort of one team, but a number of other teams are brought in together under this umbrella with an eye for smarter robot bodies for Dexterity. All right, so here I'll talk a little bit about what our team has done so far for creating this initial kind of end-to-end framework. And we first looked at very low cost and just very basic setup for the hardware aspect of it, and specifically targeting very, very fast iteration. So something where we could redesign, let's say, fingertips within, let's say, an hour or 2 hours, all the way from the finish of the optimization, or even kind of the run of optimization, to the fingertips being ready and manufactured. So overall, what would I say I envision as the end-to-end framework? So one of the things that I will highlight here is that kind of the part that our team plays in this project is really bringing in the global optimization into the picture. So as you've heard before, there are some other groups and at different universities that say consider automated co-design and let's say apply modern RL to incorporate the RL into co-design. But one of the things that we know about reinforcement learning is that it is particularly prone to getting stuck in local optima. So you have to be really skillful with how to make RL learn in such a way that it is making progress. And putting that together in the loop with global optimization in principle, and we'll show some success in practice, would allow to try different parts of the search space and not be basically held back by the fact that reinforcement learning can frequently get stuck in local optima. So what are the components that are needed for this global optimization framework? So one of them, as I mentioned before, is modular hardware. So we're developing some aspects of it, but we're taking, let's say, some of the off-the-shelf already developed hands, such as the CMU leap hand, and modularizing some of these components, like for example, switching fingertips. The other part that is really needed here is automatic real-to-sim alignment. So this is something that will also come in, and we are working on right now quite actively, but I won't have time to go into that today, but just to mention that this is a very important component. And the global optimization. So global optimization has been applied to a number of problems before, let's say in dexterity, like patient optimization, for example. But there is a need to really have a much tighter, much more interesting integration with reinforcement learning, because it really is more than just something and a next starting state for the RL method. And so that's basically what this aspect of the project is about, that global optimization and reinforcement learning should talk to each other in more advanced ways than what has been done before. Okay, and one of the other things here is the figuring out what would be a good task reward, because with novel designs, maybe it's somewhat non-trivial to come up with rewards for reinforcement learning. Our team specifically is not working on that, but there are a number of collaborators within this ARIA co-design umbrella that are considering that as well. All right, and so today I'll talk about just this first kind of proof of concept of this end-to-end pipeline or framework that considers morphology changes, so changing the shape and material properties, so changing the kind of material that the fingertips of the dexterous hand are built from. All right, so global optimization and reinforcement learning can get us something that trains in simulation. So what we have here as a backbone is we have for now existing scalable global optimization methods, but we're developing kind of some variants of them in order to explore how they can inform RL a little bit better. And we have a scalable off-policy reinforcement learning. Now, off-policy doesn't mean offline, so off-policy still means that you have to actively interact exactly with the task on which you're training. Off-policy just means that you're not necessarily only learning from, let's say, the immediate policy that you're deploying, but you might be considering other kind of policies that you've tried before. All right, and we're conditioning this reinforcement learning policy on the finger tip shapes and the object shapes. So the interesting new aspect here is kind of that this is conditional RL, but normally we just, let's say, condition RL on the goal, or maybe on the, a part of the observation state is the pose of the object. But here we now also have conditioning on the shape. And so what we're hoping here to see is that our reinforcement learning policy would understand, okay, when the shape is changing, what is actually happening to the optimization landscape. All right. And I will talk right now about a little bit of our forays into updating, let's say, and generalizing things such as cage-based deformation, which have been used in computer graphics for morphing the shapes. So standard cage-based deformation considers a cage of a sparser kind of cage around, let's say, a densely meshed object. It is fairly simple, fast, and intuitive to control with this. Initially, it was also favored in computer graphics because it is quite, let's say, easy to interpret. So, you pull on a certain cage vertex, which here is denoted by white nodes, and then the shape deforms. And you can have various influence or weighting methods, such as mean value, greens, or biharmonic methods of computing the weights. And depending on how you compute these weights, you can have different properties of how the shape is actually stretching. And so in computer graphics, this has been used for a number of different applications. But why would this be a good fit for robotics? So we've considered a few other options, like for example, isometric models, and there are some pros and some cons for constructing them. So the biggest con is that it's mostly for non-volumetric surfaces. For non-volumetric applications and kind of described surfaces, but we're also interested in something that has volume and mass. There's some implicit surface representations like GPIS, Gaussian process implicit surfaces, and I've worked with this before, and they can be pretty nice for smooth shapes. But with precise manipulation, let's say, of small objects, we don't necessarily only want the smooth shapes, and instead over-smoothing can actually be problematic for the tasks. So another problem is that GP-based methods are quite computationally heavy and memory intensive, and they're somewhat sensitive to the choice of the kernel. So cage-based information, by comparison, as I said, is fairly fast. It has reliable open source libraries already from computer graphics, and the potential shortcomings that it does have, they're not really so consequential for robotics. So we've selected that. Now, here I've just listed a few of the libraries that we've gone over, and basically what needed to be done is this needed to be brought into the overall framework that is actually doing scalable GPU-based computation. So if you just take a vanilla CBD library, that probably will not have the interfaces that people are usually used to. So we've provided such interfaces and some of the visualization tools and ported them basically to PyTorch-based GPU accelerated optimization with scalable simulators. So one of the things though that we did have to change on the algorithmic side or kind of contribute on the algorithmic side is that for many of the weight computation techniques in cage-based deformation, if you pull on the vertices, what you usually have is kind of really sharp and, let's say, sharp pieces of the shape that are not really nice to manufacture. So something that would get smoothed out during 3D printing or casting, and something that would not transfer between simulation and reality as easily. So we have developed this method that quantifies how much the neighboring cage handles should actually move to avoid these kinds of spikes. And also we've created a way to distribute the cage deformations across the neighboring handles to prevent bad things happening to the shape, like collapsing of the certain parts of the shape. And so we have much smoother results then, while still maintaining the sharp pieces that are consequential for the task. So now just to illustrate how this generally works, we have a few stages here. So one is this structural affinity approach that I've just described that builds on the cage-based deformation that makes it a bit more suitable to the kinds of shapes that we want to see that are sharp for the task but don't have kind of irrelevant sharp features and are still manufacturable. Here, to speed up some of the convex compositions that are needed for some simulators like Jogo, for example, we've introduced some, let's say, simplifications such as wanting to, for some parts, design the shapes that are symmetric, but this doesn't have to be done. We also have examples without the symmetry. If we're running this with Mujoko, so specifically Mujoko Warp, which is a scalable GPU-based version of Mujoko, one needs to do the convex decomposition, so we do that, and there are some basically advanced caching and speed up techniques in order to make this scalable, and then we train. So then global optimization, GO, and is integrated with RL in order to train this kind of policy. And in this particular case, what we're showcasing is that we can find some fingertips that work for a particular class of objects, and then another, let's say, pair of fingertips that are well suited for another class of objects, and we want to see, okay, how do the shapes actually differ? Okay, so this is an example of picking up kind of long, thin objects, and this is an example of picking up very, very small objects, like, for example, tiny screws, small nuts and bolts. Okay, so after the policy is trained, results look like this. We showed it to our Harvard engineer. He said, "Oh, what am I looking at? This looks like a piece of modern art." I think the convex decomposition and makes it look a little bit like that. Anyways, what comes out of it is actually the shape of the fingertip, and then what we do is we actually cast it in silicon with a 3D printed backing for the silicon. And I'll talk a little bit about the casting process, but the reason why we've done that is because we also wanted to experiment with how much deformation actually helps with grasping. We've experimented with a wide range of different, or we've considered a wide range of different silicon materials with different properties. And that was also a part of exploration of trying to understand what sort of materials are beneficial for fingertips. Now here we have a particularly shaky policy, which is actually good because we wanted to see that the object is actually grasped securely, and even with the shaking of the robot you have grasp that even for thin objects like a scalpel, for example, does not make the object fall out. So in this particular case, the fact that we had the very low cost robot was not a problem from our perspective because we actually wanted to test the robustness for that. And this is just to show how a few of examples of this work. This is fairly repeatable. Once the policy succeeds, and if it is well aligned with reality, then it succeeds fairly reliably, which is nice. The alignment itself is non-trivial, but as I said, I'll leave that for a future talk because that in itself is a fascinating kind of problem, especially if you have the ambition to do it fully automatically, which we're starting to look into now. All right. So in particular, you see here some of the things that are spread out. These are not regular scissors. Many of these are medical scissors. So we actually had a real-world kind of inspiration in mind for this, which is to pick up the objects that that occur in the medical domain, because you would want to automate that part of the task. For example, picking up and disinfecting objects that have been used during surgery is something that you would want to for the robots to do instead of the personnel kind of potentially risking contamination. All right, and this is an example of picking up flat round objects, like for example the cell battery. You can also pick up washers, basically small round objects. And here the shape came out to be different because the object kind of need to be held securely, but also because we've noticed that the policy also tries to do this additional kind of scooping and pushing up part, which did not appear in the case where we were picking up scissors and small, like very flat, long objects like scalpels. Right, and some of the objects that are very, very small, we were very happy to see that, and by small I also mean shallow, which is quite difficult. We were happy to see that it was possible to pick them up with this very low-cost fingertips. Now, of course, there are also failures. I wouldn't just say that this is all wonderful and perfect. For example, here the washer gets pushed under the fingers, and that's because the deformation of the kind of this cardboard on which we're operating is not modeled in simulation. So in reality, the finger presses more and the washer kind of gets underneath the finger. So that's one of the challenges of like how to really align some material. We've not considered this at the start and then noticed that that deformation of the cardboard also mattered. And this is an example of growing the shape of the fingertips for small, very, very small objects. So picking up small screws and picking up various other small parts, like there's some, I think, LEDs here and small nuts and bolts and various resistors, things like that. Okay, so the idea here was that we don't necessarily need very high quality, like in the sense of expensive fingertips, but it really helps to have the right shape for them. And just to check this point that it's not just all about having a little bit of silicone on the end of the fingertips, we've tested picking up, let's say, small objects with a different shape that was generated for picking up flat round objects like the cell battery, and we can see that the policy and the shape for that are suboptimal, which in this case is not a failure from our perspective. We actually are happy to see that the shape does matter. Okay, so where to go from here? One of the things that you might ask is, okay, well, you've optimized and created these pairs of fingertips for different classes of objects. Well, now you need a human in order to swap the fingertips if the robot needs to pick up a different class of objects. And so we decided, okay, great, let's go sort of end to end and have a robot swap its own fingertips. So this is built on some of the prior work where there was an exploration of magnetic swapping for a single fingertip, and we've kind of taken it further to say, okay, now let's build this whole kind of system with the Dexterous hand and a mobile platform so that in principle this robot can kind of come up to the table, swap its own fingertips and start working. Now we're currently experimenting with the real sim adaptation that includes some things like compliance, for example, where if we have compliant manipulation, we can actually fine-tune things in reality and not only rely on, very difficult real sim alignment without any real iterations in the loop. The other thing that I've not really talked about here is vision. So for now, we've been thinking about relying on something like flotation pose to track the objects, and on, in the future, work incorporating tactile sensing. So this is something that we will be presenting with my Stanford colleagues about having a differentiable simulator that models a DanceTech Mini sensor and actually kind of can generate a synthesized image, and we've validated that it does some sensible things in terms of incorporating reinforcement learning into that as well. So now we want to incorporate that into the overall pipeline that we have, and that's going to be presented on Thursday at ICRA. Okay, so lastly, our final ambition for this part of the project is to automate this process. This has a nice kind of sample of interesting tasks like pouring, pick and place and read off of the, the weight of the, so what he's doing right now is actually measuring the weight of the cup that is going to contain the silicon, and then a few other steps that are necessary in order to make the silicon production. Of course, if you just had fingertips that are 3D printed, a robot could come up to the printer and pick up these fingertips and kind of figure out how to attach them. But if you have other materials, then there are some other parts of the process that you would need to do. And so we're wondering, some of these steps are basically like similar to lab automation tasks, so researching that would be useful as well. And then here the ambition there is to see, okay, can the robot also design and also produce its own fingertips, and how can we simplify the process so that current low-cost robots can actually do that. Okay, I think with that I'm done, and I hope that you will kind of get inspired by the co-design aspect of it, and I would love to chat with anybody who has interest in co-design. Thank you.
We do have time for one question. Okay. Also feel free to go to the mic.
I'll just speak loudly. Rather than bespoke design for each individual objects, have you done any mapping of the designs to the objects to try to find something that's a little more versatile for multiple objects or classes of objects?
We can chat, yes. Work in progress. Yeah, it's very interesting. Like once you understand how to work with one category, maybe you have learned something interesting about that design, but the optimization you have done already came up with the final shape, right? So what can you do in order to utilize that knowledge? Yes, and that's exactly what we're working on.
Okay, great. Let's send the speaker here. Our next speaker would be Professor Jie Song. Jie is an assistant professor in HKUST Guangzhou. He previously did his postdoc at ETH, and his interests are human-centered computer vision and understanding how humans interact with the environments. So his research has great applications in robotics, especially currently the popular paradigm of learning from human-object interactions.
Yeah, okay. Yes, thanks for us invitation. I'm happy to come to ICRA to share our research. And so today my talk is about how RL can help advance dexterous manipulation from simulation to the real world. So last few years, with like rapid progress on large language models like LM or LM, we already see very fascinating progress on, for example, scene understanding from the computer main side. And we can understand the scene, detect the objects, and segment them. And also from the task interpretation side, we can also use language to decompose for example, very long horizontal tasks into sub-tasks. And also this kind of language capability can also help us to define and to design high-level planning. This is like progressing very fast. But on the other hand, for manipulation, especially for multi-finger manipulation, reasoning intelligence of course is important, but more importantly, it's about the physical intelligence or the physical creation. For example, look at this video, like our hand. The reactive robotic control is very crucial for us to quickly respond to the contact with dynamic interactions, even just with our proprioceptive information. We can accomplish this very, very fine-grained task and also to keep the stability very high. This is one very, very big challenge. On the other hand, such closed loop interaction data is very expensive to obtain. Nowadays, for example, people are trying to use teleoperate, to collect some real world, for example, robotic data. But this process is still very tedious, especially to connect this interaction data. It's very, very expensive. So to quickly summarize here, like the reasoning intelligence is, decide what to do, and we already see a clear clue how can we deal with it. But for the physical intelligence part, which can ensure the task can be actually done, in my opinion, is still not that clear. So from, I think, 2018 to, starting from 2018, we're to say that the choreography robot has demonstrated that it can require very high level of physical intelligence, especially for the locomotion, with real-time feedback control. So as we can see in this video, they can deal with very complex contexts and also very strong dynamics, even in the wild environment. So how this kind of capability, for example, for locomotion, capability is achieved? It's in simulation. We can model, the key insight there is like, we can model locomotion as our problem, and the simulation can effectively provide this kind of contact-aware dynamic interaction data and learn the robot's reactive control. So motivated by how people deal with locomotion, we can also try to formulate the manipulation task as a reinforcement learning. First of all, in simulation. In simulation, we can obtain the privileged observations to train a teacher, so-called teacher policy. And the privileged information includes, for example, the proprioceptive information about robot hand, and also, for example, the full object state, plus something like the contact force and other relevant observation. For example, for the task of grasping, once we look for grasping, the reward is also relatively easy. It's to encourage the policy to hold the object and also to keep it stable. In this video, we can see that in simulation, we can train such policy among 500K diverse objects in simulation to stably grasp objects. Okay, the next step is, okay, from simulation, going from simulation to the reality. And then we can follow the typical teacher-student framework. The key thing here is like, okay, for reality, when we deploy the policy in reality, our observation won't be perfect. Yeah, for example, the content information will be noisy, and also the state of the object also can be noisy. For example, object pose, something like this. And also our own information about the rubber hand can also be noisy. Yeah, but with the teacher-student framework, we can somehow transfer the teacher policy into the student policy. And here we can say, sorry. Then we can directly deploy the trained policy in simulation to the real robot hand. Here is for grasping. On the top is a real-time simulation. On the bottom is real robotic manipulation. So we did some quantitative evaluation for example, for 500 real diverse objects, we can achieve 95% success rate for this grasping task in the setting similar like the video shown on the right. The grasping is somehow a relatively simple task. Yeah. So it's just to hold the object and to hold it stably and then place it somewhere. So the success rate is not that surprising. And interesting to point out is we can also show some resistances to the external disturbance. For example, here we can use our hand or our tools to try to influence the robot hand during the grasping process. And why it can somehow show the resistance to disturbance to some extent is because during our training simulation, we can also simulate this unforeseen counter-dynamic interactions in simulation. We can apply some external forces to try to disturb the learning. And for some simple complex tasks, for example, just pick and place, our framework can directly provide robots, this kind of robots, low-level grasping policy, and we put skills, and then this kind of skills can be directly called by some high-level planners, for example, obtained from LM or VLM, and to complete some, complete tasks. And several tasks require not only grasp stability. Yeah, for example, the picture shown on the left, to use a scissor. Sometimes we want to use a scissor rather than just grasping it. We want to grasp it with a specific functional poses. Yeah. And also on the right hand side, sometimes we want to grasp the glass with some preferred affordance regions. And with our framework, we can enable this kind of task area execution conditioned on this kind of kinematic or semantic requires. For example, the video shown on the left is like we just provide some reference hand pose demonstrations. Then we can follow this kind of hand pose demonstrations to fulfill this kind of task. So besides grasping, so other manipulation tasks with clear objectives, for example, in-hand rotation, can also be formulated in a similar way. So here the objective, compared to the grasping for in-hand rotation, is to keep the relevant hand and object rotation relationship. Yeah. And for grasping, it's okay, we hold it, keep them stable, but for in-hand rotation, it's okay, we hold it at the same time, the hand and object state should follow some motion pattern. Actually, House did a lot of research in this direction. Besides rotation, we can also do some assembly. For example, as the video show here, in hand, we can also try to assemble two isolated components into one component. But the framework is very similar. So to have a quick summary, so motivated by locomotion, then we try to formulate manipulation in a similar IO pattern, but they're still quite different. There's several aspects. First of all, for dexterous hand manipulation, in general they have higher degree of freedom. And then for IO, this means it's more challenging to explore. And in terms of the reward, locomotion reward is relatively clear. It's still okay. Don't fall down. Especially for quadruped. Of course, for humanoid, we also want them to move like human. But for quadruped, it's very simple. Just don't fall down. And also, so far we have studied the tasks of manipulation like grasping, in-hand notation, or in-hand assembling. Those rewards can somehow be formulated explicitly, as I already mentioned, as a hand-object relevant state changes. We can still formulate them. And it's a relationship between the hand and object position or rotation relationship. But as the video show here, for realistic tasks, in real life, manipulation usually has very long horizontal tasks. And it's not that easy for us to design the reward. And also, manipulation has much more refined contact compared to locomotion. We have more degree of freedom, and also our contact is more vibrant. This means we will have larger symmetrical gap compared to locomotion. One straightforward way is to, let's try to connect some real robotic data, for example, use telework. Try to reduce, to connect this kind of sensor motor data to reduce the symmetrical gap, because we can directly access the real contact dynamics. And also with this kind of real demonstration, it can also guide the learning task without defining a very specific reward. This is a straightforward way. But there's still several changes. Real-world demonstrations, especially in full arm hand control space, are very costly. And if you try it, for example, teleoperate some fine-grained manipulation task, you'll fail. It's still very difficult. And also, this kind of data can only provide limited evidence for recovery after failures. There is no interactive feedback data, especially for recovery. And then one promising direction is to leverage real-world area, leverage real-world reinforcement learning to more efficiently use the costly real-world demonstrations. And also the real-world area can learn from real-world interactions for precise contact and reactive recovery. This is one promising direction. But real-world ROS has also several challenges, especially the main challenge is called sample efficiency. How can we somehow elevate this kind of problem? Let's go back a little bit. Now, before, we already formulate some basic skills, for example, grasping, in-hand rotation, or in-hand assembling. We already formulate this kind of basic skills in simulation. We can somehow already obtain these kind of skills in simulation. Then how can we leverage these basic skills learned from simulation to boost the training efficiency of real-world RL. This is one, I think, very promising direction. For example, we can use, as I said, the simulation trained hand process as an action primitives to ensure that the exploration is focused near the feasible solution and to avoid unnecessary exploration. Yeah, because when you do the real RL, you'll see that the convergence is a big problem, especially for very high degree freedom manipulation tasks. And similarly, we can also use simulation trained head process as a real-time intervention interface to reduce the need for carefully engineered density work in order to prioritize useful corrections to concentrate imitation on the field state. What does this mean? Basically, when we collect the real world data, with, for example, with telework, one key fact is, okay, what data we should look at more? Yeah, this is a key factor for efficient real-world error. Yeah. So overall, structuring Dexterous learning around the functional hand skills is a practical path towards efficient and reliable real-world manipulation with multifingered hands. Here are some examples. For example, we did not, as I already mentioned, we did learn the grasp or rotation skills in simulation. Yeah, we already trained them in simulation and build some real-world reinforcement learning, fine-tuning. We can more efficiently complete with content-rich and higher tasks with higher precision. Because we didn't learn those basic skills, the efficiency of the real RL is higher. Similar here is a combination of in-hand rotation, grasping, and placing, which I already trained in simulation and then just try to do in the real world. Here is like grasping and flex. This is already learned in simulation. So to summarize, here is like for real world RL, the initialization is very important. If we can use the policy we can train in simulation, it will elevate the sample efficiency problem in real world RL. Yeah. And of course, we already proved that the real data can deal with the gap between the simulation and the real robotic hand. And also the real demonstration can help us to design, to help us to address the difficulty of design report, especially for non-horizontal tasks. So for future directions, especially for my lab, we will focus on those three aspects. One is about the low-level control. We can see like nowadays the reflex like low-level complex control is still missing in the semi-trivial pipeline region. Yeah. This is super important to ensure the efficient and safe execution of content-rich tasks. And secondly, is still the sample efficiency. No matter in simulation or in the real world RL, sample efficiency is still the key challenge in my opinion. Maybe the most important aspect in my opinion. And what we can do is to also leverage human data. This is also a very popular direction nowadays in the community. How can we learn from human also to help us to make the learning more efficient? And lastly, it's about deeper integration of the physical intelligence and rhythm intelligence. Nowadays, in my opinion, they are still quite isolated. I think this is also a promising direction. Okay, I think that's for my talk and all the work, collaborated with my colleagues, people from ETH and also some colleagues from CAS. Yes, thanks, and if you have any question, I'm happy to answer.
Thank you. Maybe we have if not, I have a question. So you talk about RL in Steam, and the problem of RL in Steam and the problem of RL in Real. You know, there are so many problems. Well, other alternatives, have you considered other alternatives, such as we can just collect some data in the real world and only use that data to train your model?
You mean you mean just robotic data or human data? Or?
Like using human data to train your model.
Yeah, as I mentioned, I think it's definitely a very promising direction. Yeah, and but especially for today's talk, I'm more focused on the the fine-grained control part. So I think this is still an open question. If we can, for example, we can also collect a lot of human data, but how this kind of data can help us to finish the last mile, in my opinion, is still very challenging. Because human data can, in my opinion, is something between the the big brain and the small brain. Yeah, they can give us some nice trajectories, but they are still the human hand are still very different from the robotic hand. Yeah, to ensure the final last mile of control stability, I think still missing. I think also, in my opinion, I think the community should pay more attention on this. Yeah. Of course, once we have, as I mentioned here, more human data can help us to boost the training efficiency. Definitely. Yeah.
Okay, nice. Let's thank the speaker. Okay, next we are going to have our spotlight session. So for the spotlight presenters, could you please either sit in the front row or line up on the right-hand side of the hall. And you will be present from Matei.
Hello, my name is Remark, and today I'd like to present to you Rika V2. This is a follow-up work from a past RSS submission Rika, which sort of introduced a tendon-driven hand with a novel controller mechanism. And in this work, we added a decoupled parallel wrist on that hand. And as you can see, well, as we all know, a wrist motion is heavily involved in any human data. So whenever we want to train any model using human data, we heavily need a wrist. So in this work, we present a tendon-driven humanoid hand with a wrist involved in it. So we have a 35 to 45, 35 and 35 degree ulnar and radial motion. And this amount of extension and flexion flexibilities. This is a fully tendon-driven hand, and the tendons are routed through the middle of the wrist. Then we added abduction and adduction mechanism, which I will talk a little bit more about how the system is. Then we have flexible soft tips, which can be converted to tactile sensors, but we have not in the paper iterated on how the inference works. Then we also added, to properly identify the joint angle errors on the control mechanism, we added attachable magnetic encoders. The major reason why we added these is because in Rika paper we used monogloves, but monogloves comes with limitations of the joint angles and fingertips are dependent on the skeleton model of the monogloves. So instead we wanted to remove that dependence and added attachable magnetic encoders. So these encoders can be attached basically in 2 minutes. Our speech is for 3 minutes, so I'm not gonna let you watch all of it. But they're pretty simple to attach and then can be used for further training or just like for seeing the errors. To give more detail of the wrist design, we have a hand connector that the hand gets connected to. We have driven linkages like for a proper decoupled parallel wrist design. And then we have a ball joint in the middle. So all the tendons go through this ball joint, and then driven linkages are attached on the side. So this enables that the tendon joint angle is in the middle. And this is the extension motion, this is the radial, and this is the general wrist. And these are the knuckle design. As you can see, we have 3 fingers. We added abduction to 3 fingers. The extension is done by a spring. It pulls the fingers back, and then the abduction is done by a tendon. There are other designs, but we chose to go with this one for simplicity. And for the control, we are given a human motion. We retarget that to the URDF, like a kinematic chain of the hand, and then we directly deploy this on the robot. This provides us with an average error controller of 8 degrees. Okay, sorry. And this is like a little bit more information on the attachable sensors. We have an average control error of 8 degrees, and here how all the attachable encoders look like. It can be attached to all of the fingers. And these are some of the teleoperated tasks. This is calligraphy. This means dexterity in Chinese. This is another bi-manual teleoperated task that we did. Obviously, this is all of it is open source and can be built under $1,500. And this is a policy task that we have. So we tested the endurance of the hand for 3-4 policy tasks, and then like around 12 teleoperation tasks. So you can see more on our website, more on the details. Yeah, and you can use the QR code to start building today. Just before ending, this work was led by Lucas and Cici with the help of Alejandro, and I would like to thank to them. And also I'd like to thank the open source community. Our work, or any of our work, would not be possible with any of this work. So I'd like to motivate the community to open source our work as well. Thank you so much.
Hello everyone. We're proud to present our work, Handful, Sequential Grasp Condition Dexterous Manipulation with Resource Awareness, where we do these kind of simultaneous multi-skill tasks. So the core question of our work here is like, how do we train a dexterous robot hand to make full use of hand dexterity? That might include multi-object grasping, picking up one object and pushing another, or pinching an object and then stabilizing the beam. And more specifically in this work, we focus on performing tasks with a grasp plus some other skill. So a grasp plus a push, a grasp plus pressing a button, twisting a knob, pulling a drawer, or picking up the second block. Our core insight here is about skill, diversity, and resource awareness. So we think that to accomplish skills simultaneously, first, it is helpful to learn diverse ways to execute the skills. And then second, as a result, you may, for example, grasp an object with your index and middle fingers, and then you leave other fingers free for other tasks. So you can later do skill composition. As a result, in Handful, we first trained 9 diverse resource-aware grasps that leave fingers and in-hand space free for downstream tasks. Next, a natural question is, how do we actually decide which grasp is best for which downstream task? For this, we use a curriculum learning strategy to weed out unsuitable grasps and then progressively train the best grasping policy for the downstream tasks. So the way that we do this is we start our curriculum in the lowest randomization level, C0, And then as training progresses through different stages, we eliminate candidate policies until only the best second subtask policy is left. And it's only trained from one grasp type. So at the end, we end up with one grasp type and one second subtask policy trained from that grasp type. And then after this, we use a pretty simple trajectory retrieval strategy to demonstrate effective sim-to-real transfer. In general, we find that resource-aware grasps that limit finger use, those are in the green here, enable successful downstream policies much better than those that use all fingers in the initial grasp, so whole hand grasping. But we do find that one of the failure modes of the work, or failure modes of the grasps themselves, is that these diverse resource-aware grasps are a bit harder to maintain in the second tasks. As for future work, we'd like to propose two major questions. One is, how can we more generalizedly promote diversity of skill execution for skills other than grasps? So how can you execute skills with different finger combinations, for example? And then second is, once you have diverse versions of each skill, how do you actually decide what skills can and should be composed for simultaneous execution? And so our work, more details at our poster or on our project website. And of course, I'd like to thank all of my collaborators and all of the wonderful graduate students who gave feedback on the paper.
Hello everyone, I'm Ray and I present our work called Grasp. So recently we have seen many works on dexterous grasping, especially on graph synthesis and graph generation, and all these graph posts were good. However, from many demos we can still see that real-world grasping will clumsy, and we often observe undesired object movements during grasping. So why does execution lag behind planning? Our answer is that multi-finger coordination under uncertainty has been overlooked. So real-world observation is partial and contains both shape uncertainty and position uncertainty. Even if the observation is accurate, the grasps generated by the network can be imperfect. In particular, fingers may contact, during approaching, fingers may contact object at different times. And during grasping, fingers may apply unbalanced force to the object, leading to the example shown in the last video. However, what we actually prefer is a right video. The robotic hand can gently grasp object without altering its original pose. The current best practice is a three-pose open strategy. During the approaching phase, the hand moves from a non-contact pre-grasp pose to the just-in-contact grasp pose. Then, during the grasping phase, the hand moves to the squeeze pose to apply sufficient force to the object. This strategy implies kinematic coordination, but since there is no feedback during execution, it cannot adapt to actual object position and shape under uncertainty. So our core insight is that if we can control the contact based on real-time tactile feedback and ensure multi-contact coordination, we can achieve much gentler grasping. So to this end, we propose a tactile driving model-operated controller, which contains three key novelties. It employs coordination over separation of the approaching phase and grasping phase. It involves arm-hand coordination to compensate for object position errors. And it increases contact forces in a balanced manner through adaptive force coordination. For evaluation, we perform a large-scale simulation study involving 15,000 graphs across 400 objects using 3 robotic hands. The results consistently show that our method achieves higher grasping success rate and less undesired object movements. The real-world results are also consistent. Our method adapts to the actual object positions and reduces the undesired object movements. In other words, our takeaway is that picking up an object is only the beginning. How the object is grasped deserves as much attention as whether it is grasped. This work will also be present tomorrow afternoon in the motivation and promotion oral session. Thank you for listening.
Hello, my name is Lepora. I'm one of the organizers, and I'm about to present our work Dexterity, task-agnostic point track policy for centurial dexterous manipulation. Unfortunately, the first author couldn't make it, so I'm presenting on behalf of Jeannette. Yeah, so as we all know, collecting real-world data via teleoperation is pretty hard, expensive, and also unscalable. So it makes it very susceptible to overfitting. In the meanwhile, learning and simulation, in theory, you can collect a bunch of data sets, but you also suffer from a bunch of your engineering and task specification. So in this work, what we tried to do instead is we wanted to disentangle the high-level, disentangle the generalist policy into two components. A, task-agnostic low-level fundamental control policy, and B, combined with the generalized level planner. In our case, that comes from video models and point tracker. So how do we do this? For the first component, what we do is we learn something called any pose to any pose. So in simulation, via reinforcement learning, given any object, given any pose, our goal is to just reach the goal pose. And this is just a single weird specification, and you can train with a bunch of different simulation assets so that you can achieve generalizability in the real world. And specifically, we found that using poses directly as a policy input is not very nice because you can't extract them robustly in the real world. So instead, we use something called point tracks. And how we encode it is a little bit different. We wanted to maintain correspondence, so we just concatenate the current 3D point track and the goal point track, and we put it into a format so that we call that paired point encoding. And we then combine that with the high-level planner you mentioned, which is a combination of video generation followed by depth estimation and point tracking. So if you combine all these components, what you get is, given any text description of the target task you want to solve, you can do something like this. So you get the temporal sequence of 3D point tracks of the object you want to move in time. And of course, for the current point track, you can also do this in real time, like that. So combining all these components, what you can do is kind of generalist policy. This is all single policy combined with video gem model and point tracker, and you can, as you can see, it's pretty robust to background or different camera location. And it can be also robust to distractors. And it can also show some interesting motion. Interesting motion, such as just unplugging the charger basically. And yeah, and it's also very reactive because we have the level controller trained from simulation. So it's very robust to perturbation, or yeah, whatever you do, you try to be robust to it. Yeah, thank you very much.
Hi, I'm Amber, and I'm here to present our project on robotic dexterous drumming. As we've seen in a lot of progress today, having truly human-like dexterous hands has the potential to achieve a wide array of dexterous tasks. However, in research, a lot of problems focus on isolated challenges. For one, a lot of papers focus on in-hand manipulation with a fixed wrist, or for example, simple grasping, or shorter horizon tasks like pouring water into a bowl. While I think progress along each of these axes is important, I also think it's important to consider multiple challenges for a single task. For instance, as you see in this video, drumming is a very challenging task that requires very fine-grained finger and wrist motion. In this project, we note that drumming has three main challenges. First, in-hand contact, which involves manipulating the drumstick. Second, external contact, including initiating contact with the drum head and also responding to the forces. And third, long horizon song playing. To focus on each of these challenges for in-hand and external contact, we use reinforcement learning and simulation with reward design. And for long horizon behaviors, we decompose our policy into a high level and a low level policy. Specifically, our method works like this. First, our high level policy takes in the song we would like to play and produces a trajectory of where we would like the drumstick to go. Our low level policy takes in this plan as well as proprioceptive state in the song and performs residual RL over the arm and also RL over the fingers. We train this in simulation, and here are some of the rewards we include, which include how to hold the drumstick, and then also trajectory tracking and contact curriculum, which is learning how to manipulate the drumstick before then enabling contact. We deploy this in the real world with zero shots into real. Our experimental setup includes bimanual arms. We have 2 simulation environments, and we also play real world songs. For our simulated songs, we play across 6 genres, and we show performance across 2 real world songs and exercises. Our first question is dexterity necessary for bimanual drumming. Here we compare against a fixed grasp versus a reactive grasp where our fingers are moving and adjusting to the drumstick. Higher is better, and here we see that a learned reactive grasp outperforms a hard-coded grasp. Second, how can we enable high-speed drumming where we're playing very quickly? Here, lower is better in terms of trajectory error and energy consumption. And we see that finger-driven motions, where most of the motions driven from finger moving, as opposed to the larger arm motions, performs much better. And lastly, here is a video of a real-world performance. We play in a bimanual setup, and here we find that closed loop performance outperforms open loop policy. In conclusion, our main takeaways is that careful reward design can produce policies capable of in-hand and external contact. The second, that decomposing the policy into high-level, low-level policy allows for long horizon performance. Thank you.
Okay, great. Hello, everyone. Please go back to your seat. Our next speaker is Professor Georgia. Georgia is a full professor for interactive robot perception and learning at TU Darmstadt and Hessing AI. Her research focuses on embodied AI, structured robot learning, mobile manipulations, and safe human-in-the-loop learning. She has received several Best Paper awards and also delivered early career keynotes at Coral 2024. Without further ado, stage is yours, Georgia.
Thank you so much. Thank you for the invitation. And also thank you for accommodating the schedule. I had cancellation of flight, and you can imagine what happened afterwards. But I'm very, very happy to be here and discuss with you my view on the problem of dexterity. I'm going to talk about the structure of contact. I will talk about how we should be reasoning about feeling and scaling dexterous manipulation based on work that we do in my lab, Pearl, together with collaborators. Let me see, this is not working. Right. Okay, so before we start looking into some research work, let's focus on this experiment. On the left side is an experiment on lighting up a match with your normal hand, while on the other side, as you see on the right, they have anesthetized the fingers, so there was anesthesia on the fingertips, and then they asked the people to light up the match. And as you can see, even if when you have like pre-anesthesia, you can light up the match right away, while after the anesthesia, well, even if you have a model of the world, you are not even able to grasp the match, let alone do the whole motion. Of course, it takes a few trials, for sure, partly having a model of the task helps quite a lot. But this actually is here to show you that dexterity alone doesn't depend on the fingers. It's touch that it is missing that is making the human fail to do a task that was very, very efficient in doing while having the touch feeling. So yeah, I think that we need to not only focus on the design of the hand, of whether it's going to be a multi-fingered hand or it's going to be a two-fingered gripper, but we need to understand where dexterity stems from. And dexterity stems from contacts, from understanding, reasoning about contact, making and breaking contact, feeling the difference of grasping different objects, and also everything that is built around this in terms of what we can now do in terms of skills once we have established, contact understanding and feeling. And we have seen that if we take away contact, we are not able to use anymore the fingers. And therefore, in my opinion, dexterity lies in the structure of contact and not in the number of fingers that we have. So why do multi-fingered hands still lose to grippers? Because don't get me wrong, I still think that for many tasks, having more than two grippers is very, very, more than two fingers is very important. But I think the core problem is that most of the times we care about making the hand the best, replica of the human hand, so making it look as anthropomorphic as it gets. But we do not do anything about the rest. So we can say that today's Dexterous hands are contact naive and contact blind. We have solvers, for example, for optimizing multi-contact planning, multi-contact optimization that cannot reason about when contact is being made or broken. Our policies are usually just vision-based, and they never feel, for example, the forces at the point of interaction of the fingertip with the objects. We cannot react to instantaneous slips on the instant of the contact itself. And learning from all these does not really scale on high-dimensional bimanual hands for solving more complicated tasks, where, for example, having even more fingers really matters. Because, it's very data inefficient due to the lack of all the inductive bias that having a sense of touch brings. So, as I said, my thesis is that dexterity is a structure of contact problem. And we will see now in the talk that we can see structure emerging at three levels. On the optimization solver that can reason about when to make and break contact, the sensors that we use, and also the policy that we use to learn some complex dual arm manipulation tasks. So yeah, I would follow this line and try to discuss some works, some recent results from my lab and collaborators, where we are trying to reason about contacts, feel the contacts with multi-resolution sensors, and also scale to ambidextrous manipulation tasks. So one important thing to understand why solving contact-rich manipulation is so difficult is that if you saw at the landscape of this optimization problem is highly combinatoric because you make and break contact. It is very dynamic because there are forces and wrenches in general involved, and it is very non-smooth. It's a very non-convex optimization problem. And therefore, we have noticed that usually if you try to use off-the-shelf solvers for solving this very complex optimization problem of multi-contact optimization, they usually get stuck, and this is because of the nature of the constraints that there are in these problems that are called complementarity constraints, constraints that try to reason on where there is zero force, on when there is no force, on whether basically there is a gap between making and breaking contact, which makes the optimization landscape very, very difficult. And we have proposed a new implicit active set trajectory optimization algorithm called IMPACT that uses slack variables and then a bi-level optimization approach that actually is able to reason about these multi-contact sequences in a trajectory. So I'm not going to go into too many details and tire you with the math of it, but I strongly encourage you, if you are interested, to look into the paper and also talk to my student Jeannette, who is at ICRA. As I said, the problem that makes this optimization very, very hard is the on and off nature of the constraints. This is called a mathematical program with complementarity constraints, and they are called complementarity because you either have force applied or no, or there is a gap, and basically either there is contact or not contact. So you have these complementary constraints that may or may not be justified, and at least one of these two complementarity constraints is equal to zero because basically the constraint is applied. And it is very, very difficult to actually find when there is also the transition between these constraints. Multipliers blow up usually, KKT is not valid anymore, and they are very, very, usually NLP solvers that are used are very initialization sensitive and very brittle. So I'm not going to go into much detail. What we proposed is a safeguarding of the augmented Lagrangian approach that is commonly used for solving such problems. And then we basically try to track which is the mode that it is currently applied. So whether, for example, there is a contact being done in the environment. And then we use block coordinate descent to do a very fast inner loop of optimization in order to find the trajectory within the mode. So it's like a two-layer optimization problem where, for example, we select the mode and then we implicitly ensure that the inner solution respects this mode. And we have also several guarantees derived by this method. But for me, what is very, very important here is that this algorithm is in essence able to figure out the switches between contacts and not contacts. It doesn't have a prescribed schedule even in the initialization. And you can see, for example, in the push T task in the planar case or on pushing this rectangle here, you can see how we can discover how the forces change when the robot pushes the T in order to arrive to a location, a desired location, desired pose, following the trajectory here in blue. And you can see how our algorithm is able to determine where and with how much force you have to apply in order to ensure that you can bring the T in the desired pose. So what we can do with that? So there was a benchmark introduced about the problem of contact implicit trajectory optimization based on the Allegro hunt in Mujoko, where you have to do in-hand reorientation. And with our approach, because we are decoupling the problem in this two-layer bi-level optimization, we are able to apply, to do trajectory optimization at 10 Hertz and basically reason very fast, almost real time for solving this problem. And we can also do the push T task in the real world with a 10 out of 10 success rate. So we were able to push smoothly the T to arrive to its goal location, starting from different initializations, as you see, successfully all the times that we applied our solver. And we are very excited about this solver because now what it actually allows us to do is to create trajectories for a problem that it is very, very difficult to teleoperate. So if you want to learn for dexterous manipulation, for example, for the in-hand reorientation that we saw with the Allegro hand, it is very, very difficult to teleoperate or to provide data as a reinforcement learning problem. It's also a very exploration-heavy problem. So having a way to control how you can extract this trajectory that you could learn from is very, very interesting for us. And this is a future direction that we want to, and we are actually currently exploring. Now, as I said, the first part is about reasoning, about making and breaking contacts in complex dexterous tasks. But then one important aspect is that the vision alone is not enough. In many cases, if you scale up, of course, the data, as we see with the now massive teleoperation-based data collections, yes, maybe you can, find a side way for the problem of not having a sense of touch on the fingertips. However, remember the problem of the numb fingers. Why shouldn't we try to make the most out of our touch sensors in order to accelerate learning? So a couple of years ago, Niklas Funk has created a version of a vision-based sensor that is called the EVTAC. So it has an event-based camera instead of a standard RGB camera, that it can capture events at 1 kilohertz, and it can sense vibration at around 500 hertz. And what we did there is to, in the same way as with gel side that you can see here on the right, we created also some dots, and we do a dot tracking and learning process for example, detecting sleep. And I want you to notice something here. There is a nice complementarity between these two sensors. Here we are studying, obviously, on the one hand, we have the EVTAC on the left side, and on the right side, we have the gel side. And what we can see is that when the sleep happens, and you see the vibrations here with blue, the events are only detected at a very high temporal resolution with the EVTAC, while the landscape of the dots of the RGB sensor remained intact. Obviously, the RGB sensor can give us other benefits in terms of spatial resolution, but I think that this is a very important, considering also how high frequency our sensing ability is. So as I said, we also etched dots on the gel of the EVTAC. We did dot tracking. We are able to detect shear forces with a small network that is very, very efficient and can give us outputs at 10 milliseconds. And here you can see the architecture. It's very, very simple. It uses a fast and slow history of interactions. And it is very, very effective in being able to detect sleep and trigger a regrasp action whenever sleep is detected. And we also found very interesting, because usually with these tactile sensors that the gel wears off, it is very difficult to transfer from one gel, from one sensor to another. Usually you have to maybe collect a few more data with a fresh new sensor. We found 95% transfer. So the structure is actually there underlying in the events of the sensor. And here you can see how during the sleeping action, so we opened slightly the gripper, and then the objects start to sleep. They are having different surfaces, or different types of frictions are appearing. And you can see that in all the cases, the sleep detection and regrasping strategy manages to regrasp the object in time before it actually drops. What else can this allow us? It allows us to do tasks that go beyond quasi-static manipulation because of its very high frequency. So we wanted to study exactly the same problem that we saw sorry, I didn't automatize this. Exactly the same problem that we saw in the beginning of the talk with the lighting, with a match lighting with a robot. Here is some data collection instances. And we wanted to see whether really vision is needed or not. Or is our IFTAC sensor quite strong to actually help us do this very dynamic contact-rich task? For doing the inferences very, very fast, we have used flow matching as our policy parameterization. We found that this really has higher benefits than using diffusion policy because it's much, much slower. And what we do here is that we fuse the information from the vision that it is on the hand. And the tactile sensor, they have some dedicated stems, then they get all fused into an observation signal that goes inside a flow matching transformer that outputs AC3 trajectories at a quite high frequency. And one other thing that we tried is actually to mask out the sensor modality. So, for example, to 50% of the time, we drop the tactile input, which increased by far the robustness of the policy that we achieved. And we found out that in this work and also in the follow-up work that I will show you, that actually doing this masking makes your final policy very robust, even if you don't have the actual tactile sensor in place. Some very, very interesting results that I think are very important in the context of this workshop is that our results show that deploying vision and touch gave us 80% success rate in doing the match lighting versus 20% of training a policy with vision only. And it was very interesting to see how the attention in the network shifts from vision to touch-based features whenever the contact is actually instantiated. So it really shifts, and I think that this is also the gap that you see in the performance there. Let's see here a slowed down instances of deploying on the top vision and touch versus doing vision only. And you can see here in these six instances, only once it was able, let me replay it for you. So the robot has to go towards the point of contact. It has to detect it. So it's also this part of the problem to actually detect the area that, I don't remember now, how is it called, this strip that you do the lighting of the match. And then once you are there, you have to do a very fast striking motion to light up the match. So yeah, vision only fails, especially when it comes to making the contact. Touch only fails alone, so because it lacks the special context. So the complementarity of vision and touch is the best. And we have also, as I said, seen improvements in training the vision policy with the IFTAC sensor, but without deploying it later on. But even with this type of training, you get a way more robust policy for the vision and touch also. And this led us to think of what happens if we combine the high temporal resolution of the IFTAC with the high spatial resolution of gel site. What can we achieve with this heterogeneous tactile sensing? So in a similar fashion to the architecture that we had before, now we have specific convolutional stems that output tokens per sensor. So we have the RGB history, we have the history of the gel site, and also of the IFTAC. Also notice that the IFTAC frames are way more than the other ones because the RGB-based sensors, whether the camera that sees the scene or the one of the gel site, they have lower frequencies, right? So we need different histories here. And these get pulled into the same flow matching policy that we had before. And what we found out is that actually it really, really helps. So here you see some insertion tasks of putting a bulb into the connector and then switching it all the way that it actually clicks and you turn on the light bulb. And you see here from the attention maps that while reaching for the tiger, as it makes sense, the vision-based sensor matters. At the point of contact, well, the very small disturbances happen because you slightly made contact there with the hole. You see that the Eve tag starts having like a higher, let's say, attention. And then while screwing, because this is more a special task of like, okay, now I am already in contact and I just have to rotate, gel side helps the most. Also here we tried co-training. So basically we trained with the multi-tactile data, and then we dropped the IFTAC sensor at test time, and we saw a 10% boost in the performance. Rikmar is standing there, and he could give you more insights about the results. If I'm not wrong, the multi-resolution system gained 80% across tasks. Gel side and vision only was around 460. Okay, and vision only? Vision only is really bad. Okay, so okay, you got this. And like, just to be a bit now fast, let's talk now also a bit about more coordinated skill learning, that we have to coordinate high degrees of freedom arms. So we have the 7 degrees of freedom, and then we have also the Allegro hands that we need to learn to control all of them for doing various bimanual symmetric or asymmetric tasks, meaning they are in the asymmetric cases, the roles of the hands are completely different, so they have to really coordinate. And we have exploited symmetry here as an inductive bias for accelerating the learning and also generalizing over different configuration of the arms and the environment. So let's see a bit what we did. So first, as I said, we use morphological symmetry as our inductive bias, basically the mirroring of the two arms and hands. Now, there is actually a small asymmetry there, but it doesn't matter in the learning process because already deploying this inductive bias has accelerated by a lot the learning, and we do reinforcement learning here, so it really helped with the exploration problem. The policies are equivariant networks, so the left hand experience is also automatically translating as experience for the other hand. We decompose the problem, the task that the arms have to solve, into per hand subtasks, and we train dedicated equivariant networks for each part of the task. And then we distill and we combine these subtask policies into a single hand agnostic policy, which is also equivariant, and it is independent of the hand and task assignment. So this actually allows us to now have one orchestrate or equivariant policy that, by seeing the scene, understand which hand has to interact with each object without needing any input from us, in terms of like what task are we currently solving and so on. And we can also scale this up and use the same kind of inductive bias to go from 2 arms to 4 arms. Here are a sample of the tasks. It is very important that we found that actually the acceleration, the gains that you get by introducing this inductive bias are huge. The experience sharing is making the learning very fast and robust. And we found that it really wins the most when the task is asymmetric, when basically you have this imbalance on actually the horizon and the complexity of the task that each hand has to do. For example, for taking the whisk and doing the cyclic motion versus just taking the ball and bringing it close and holding it. You can understand already that the one task is more difficult than the other. And we were able to actually do a zero-shot sim to real transfer, but these policies require the state estimation, where we use foundation pose for extracting the poses of the objects. And as I promised, you can also scale this up to teams of robots. Here you can see 4 arms where they have to hold up the how are they called? The things of the box. put the objects, put the objects inside and then close them. And in different configurations and in different also assignments of roles, it works very, very nicely. I hope I gave you a new perspective of considering dexterity as a structure of contact problem and not just a design of the best anthropomorphic hand problem. We need to care about structure on the solver level, on multi-contact reasoning, on the sensor level, on which features we want to extract from our touch sensors, and the type of policies that we are using in order to scale this up into complex ambidextrous manipulation policies. I think that this beats to just scale up and use more data, because with more data anyways, this will emerge. Because first of all, it's very expensive to do this, as we already know, and very, it's tedious. The gap, in my opinion, the gap to grippers is not just, the volume of data, is just the contact blindness. And I hope I gave maybe something more to discuss later in the panel. And thank you very much to my students and collaborators for this work. I'm happy to take questions.
I have to take one question from audience.
Yes. Yeah. I think this is not only for the tactile. For sure, this is one issue. I think I don't know how much we are going to progress into making the simulation of tactile sensor work better. If this will progress, for sure, there are quite some people that are looking into that. So definitely this was going to help. But I believe in informed domain randomization. Domain randomization that is not happening basically crudely on just randomly doing noise injection, but doing information theoretic injection such that you ensure that you maintain the performance gains that you have in simulation and you are able to transfer to some extent in the real world. The other gap that we find is also the dynamics in essence. What you see here with the Allegro hand doing the reorientation doesn't transfer in the real world just like that, the trajectories, because there is a gap in the dynamics. And this is also something that we are currently trying to address from the point of view of neural dynamics learning. So we want to bypass actually the Mujoko simulator if possible. Yeah.
All of the professors who share the latest progress about the reinforcement learning and the hardware co-design and the evaluation framework, as well as the tactile-based manipulation. So I want to raise several big picture problem questions for all of the panelists. So what's the biggest barrier to deploying the general proposed dexterous manipulation in the real world scenario instead of the laboratory settings? So firstly, maybe Pulkit, can you share about your idea regarding this point?
Thank you for the panel. I'll reiterate what I said in the talk. I think reliability and speed are two very important things. That we can have demos, but getting people to pay for robots is a different question. And no one is going to pay for causality if the robot doesn't do the thing that you want it to do. Sometimes people would argue that, hey, in a home, maybe reliability is less important, or speed is less important. But if the robot is dropping one utensil every day, which should be 99%, you will get irritated at that robot very quickly. So I think thinking about throughput, which combines reliability and speed as a metric for dexterity and for manipulation, optimizing for that, will be great to transition robots from being demos to robots which will actually be useful in the real world.
Okay. So, Professor Rika, you also work on lots of work related to the hardware co-design. What's your points regarding that?
Right, so I think I totally agree with the reliability and speed. Definitely the case both for urban environments and for industrial environments. One other aspect is that the hardware hasn't converged to a point where there is volume manufacturing for some of the required features. And sometimes we're even still experimenting, like what Georgia mentioned, for example, with tactile vision, how to combine them, things like that. So I think that's one of the problems, that there might already exist technology for some higher reliability, higher repeatability, higher sensitivity versions of something that can be made into Dexterous hand, but the industry hasn't scaled up yet and hasn't yet reduced the cost. So it will take some time to do that, and then maybe we can start thinking about how we can.
Hi, Professor Georgia. What was your points regarding this question?
So yeah, I will maybe continue on the point that Rika said, that I think that the repeatability of the tactile sensors that can give you the frequency, the resolution, for example, being able to detect to like shear forces with very good precision, and then how they can. This is like one part that it is not there compared, for example, to RGB cameras, and I think that this is why many also industry startups, etc., are very reluctant to actually deploying this kind of sensors compared to a well-documented RGB camera that exists out there. This is like one important fact. And then the other fact is like robustness and resilience. And this is currently not showcased neither in any of these demos that we see, but either we've not seen any deployment. This is very, very important in several fields that this robot is going to be applied. I would say that the home robot should be the moonshot for the community. I don't buy the low liability thing, because if it is going to be next to my kid or next to my grandma and drops something on the kid while walking, for example, this might not be a low liability. I mean, who gets the liability is a question, but then the final outcome, what is? So I think more work needs to be done into the direction of on designing better tactile sensors.
I think the stability is super important. As well, the Dexterous manipulation will give the multimodal problems. So I think Professor Jie was working a lot regarding the data side. So what's your point regarding this?
Yes, actually. So your question is like general purpose.
The best area.
I think other professors have already mentioned several aspects. So like towards the general purpose robotic hand manipulation, I think I have a lot of problems. Like hardware already talked about, and reliability of countries, like the load control. I think if the keyword is general purpose, then if we still believe it's a somehow AI problem, then I think the data is still one of the biggest problem. And where the data comes from, because as I mentioned in my talk, it's manipulation is a reactive interaction process. And how to get like diverse data is still a problem. No matter it's human data, real robot data, or simulation data, no matter it's imitation learning, reinforcement learning, no matter what kind of training, learning mechanism, I think in the end, if we believe it's an AI somehow still a lot of AI problem, I think data is still one of the key problem. So we still don't have the clue.
I see. So for the next part, I want to start with the hand-object interaction data problem. Because I think today you already shared lots of results using the reinforcement learning from the real world to increase the common case data to train the imitation learning or the VLA model. However, for the current popular egocentric data, do you think we can use the large-scale egocentric data set then improve the generalization ability of the policy and just reduce the efforts to collect the data from the real world?
So you mean still the data problem, yeah?
Yeah, right.
I believe so. For example, let's first talk about the robot hand. Let's just think about the human hand. Yeah?
Yes.
If we can have a way to collect enough, diverse human hand with interaction data, maybe we can first try to build this kind of foundation model to see if it works. If this works, then I think the community definitely will jump into close the gap between human hand and the robotic hand. This is my opinion.
I think the data can be generalizable before the hand or the anti-vector have the contact with the object. Can you imagine a limitation of the current pipeline for the egocentric data?
You mean the collection pipeline?
Yes, yes.
Yeah, I think the data problem, in general, data problem have two aspects. It's a distribution, and how good is the distribution, how realistic it is. And another aspect, in my opinion, is labeling. How fine-grained we can label it. For example, can we have very fine-grained tactile labeling, this kind of thing, for like hand object poses labeling when we have a lot of population. So if we can solve those two aspects, then I can say it's possible. To get the very good distribution, we need a very natural collection pattern. Okay, for example, nowadays I saw a lot of hardware-oriented collection pipelines, and they're too heavy. It will influence our daily life. So I don't think if the hardware is too heavy, the data distribution will be a big problem.
I see. So Professor Pulkit, I think you was working on the Dexterous data collection on devices to collect manipulation data. And what was your point regarding the egocentric data for the large model training or the imitation learning?
So I think egocentric data is good for planning, perhaps, where you know what objects you want to interact with. But I think planning and control are two separate problems. Control is the problem, as Georgia was also mentioning about contacts and how do you manipulate contacts. I think that data is simply hard to collect by humans. One, because we don't have the right interfaces. Second, a lot of that data is very high frequency. And for humans to be in loop at that high frequency is next to impossible. So my vote is that the control should be learned through reinforcement learning. And my bet is on simulation as a way to learn control. And I think egocentric data is useful for doing planning in the same way that VLMs are useful for doing planning.
Yes.
So I think for us, DexOp was really a way for us to understand how good are our hands that we are building, but definitely not as a mechanism for doing control, mostly for doing planning.
But may I ask, what do you think is the differences between the simulation data and the egocentric data for the retraining of the VLA?
Yeah, so I think there are a couple of differences. One, egocentric data is no force information. A lot of the data from simulation has the force information in it. Now you could say, hey, I'm going to wear gloves and then I'm going to collect egocentric data with it. So now I'm going to get force data also. But then even in that scenario, we're collecting all successful examples. We're not collecting data in the distribution that the robot is going to encounter. When you have noise in your sensing, when you're going to have noise in your control. So I think the goal is not to get to 90% performance. Your first question was, how do we make robots be useful?
Yes.
And for that, the performance has to be in the high 99s.
Yeah.
And that requires us to collect data on policy. and not off policy. So I have two issues with it. Right? One is the data is off policy, and therefore it's not the right data distribution. And second, the data doesn't have force information and reactions to forces, which are important.
So I think there are also different modalities, including the force or tactile sensor data from simulation. So do you think the current simulation environment is already enough for capture the force data and the tactile sensor data? Because from my perspective, there's still a large gap for the force torque sensor data in the simulation environment. Right?
Yeah, I think if you look at locomotion, a lot of the locomotion sim to real has happened mostly through proprioception. I think manipulation problem is harder, definitely. But there is no fundamental reason why that cannot be done. I think it's just that a lot of the community is focused more on doing teleop data collection, because if I want to get 80% performance in a new task, that's simply much easier to do it. I think sim to real does require more time, more investigation. The tools perhaps are not as mature in the open source, but with the right engineering effort, I definitely think it can be done.
Yeah, I see. And I think for the tactile sensor data it is similar to the vision data, because we can capture the vision imager and use it as the tactile feedback. And do you think the tactile sensor data will help us to increase the feedback loop compared with the force?
So I would not compare vision and tactile in the same way. Yes, we can use vision as a modality to capture deformations in a gel, but the information is flowing at very different rates. Like if you were to make a contact with a rigid body, with the camera, you would not be able to detect how much force the contact is happening with. So I would say if you just had wrist cameras, that is not going to compensate for what a tactile sensor is going to give you. That is point number one. I forget what was the other part that you were asking.
I mean whether the tactile sensor will be better. We include feedback data to have the more dynamic manipulation ability.
Yeah, I definitely think it depends on what your metric is. So if your metric is just accuracy and you can take a lot of time to complete the task, in that context, I think the role of skin-like tactile sensors is less. I think if you want to perform the task faster, then the role of skin-like tactile sensor is higher.
And Professor Georgia, what was your point? Because I think you was working on both these topics as well.
Can you reground again the question?
So because you just mentioned that the dynamic gap for the tactile sensor is manipulation. So I think we can also use the force sensor data and the tactile sensor data. And what do you think is the best way to use all of these modalities and how to represent these modalities?
In simulation, you mean, or in general?
In general, between these two modalities.
So I think that they capture different layers or like different levels of the contact problem. So the force torque sensor is also very important. It might be even accelerating, for example, learning in some sense on when you are making contact with the environment, when you could, for example, even help you adjust the impedances of the robot. So for example, change the stiffness depending on the task. So it might, the phase of the task. So I think at this level, they might be quite helpful to be included in the pipeline. But then when it comes to going to contact and interacting with an object, yes, still you can get some information about the change of the wrenches, but then what happens in hand, which is very, very crucial. For example, when there are slips happening, or for example, if you need to apply inside your finger, like control the forces of the fingers on the object, because maybe you're manipulating a potato or an egg,
this has to come from tactile sensing. It will not come from the crosstalk sensor that you have mounted on your end effector. So I think that they capture different granularity of the contact interaction that are important at different levels of decision making in the pipeline, and they might be fused all together depending on what you are doing, but they might also interfere. We have not investigated yet the integration of crosstalk together with the tactile, so it is something that because we have like two lines of work. One is like vision force proprioception, the other one is vision tactile proprioception, and now it's time to see whether these can come together. But I still feel that while force talks are quite high frequency, they give some information that might not be, as like Pulkit was saying, important at for example, at one very dynamic part of the task, like regrasping, like closing a bit harder, or releasing a bit my fingers, or doing a small manipulation to the orient. Might not be beneficial so much, might be noise even.
I think this topic will be super difficult. I'm looking forward to the general representation between the different both sensor, talk sensor, as well as the Asian tactile sensor data problem. As well, you also mentioned that they can use the domain randomization in their simulation environment to capture the diverse distribution for the Asian tactile sensor data. And recently, there are also some based representation method to improve the vision generalization ability. Do you think the domain randomization will be the final solution, or the representation will be the future direction?
Yeah, this is a very good question, because actually while the previous speakers were talking, I was actually thinking about that we have not worked so much on the representation level for these sensors. For example, we take these dots, we take the features, and we take the raw RGB, we throw it inside a CNN, we take the tokens, and then that's it. But not much has been done on like maybe understanding what is the proper like representation for these kind of sensors, or whether, for example, they could be sort of supervised in a different way. For example, even with a force torque sensor or whatever, to give us richer features than just adding a CNN stem and extracting the features in an end-to-end fashion. That said, along the representation, I don't think it's going to solve the sim-to-real gap. So either we have to work on more differentiable simulators that can basically improve and in some sense do the system identification that we're missing, or we have to do much better work in the direction of the sim-to-real pipelines, and also Pulkit hinted to that. I'm also a believer of reinforcement learning for these high-frequency control tasks, and I think that the community should look a bit more into these problems for improving this pipeline. So I think that these are complementary. You would need still to study better representations and still to study better sim-to-real or differentiable simulators for solving these tasks.
And Professor Rika, I think you also use the realistic simulation environment to improve the hardware code design. What's your point regarding this problem? Maybe when we want to solve this problem, which task we need to solve first, and maybe what's the next?
Yeah, that's a good question. So I started using and then working on domain organization quite some time ago, and it seems like the community kind of ramped up quickly. So a lot of things have been achieved, let's say like 2016, 2017. And then there was a little bit of a stagnation, because like what Giorgio was saying, kind of uninformed domain randomization with reinforcement learning frequently just ends up getting stuck with a policy that is very, very suboptimal. So it might even solve some simpler tasks, but it fails to either get reliability or solve more complicated tasks. So that's certainly one of the things, like one of our bigger projects that we're planning for next year is looking much deeper into real to sim. So including, differentiable simulation, of course, but also various much more advanced techniques combined together, and with a lot of different kinds of real data. But I don't think that it's a sort of a 1 month, one project kind of problem. I think that would require a contribution from a number of different parts of the community. One of the things that would be very interesting, and I think that also links up to the previous point about how do we know what kind of sensor data is helpful. I think right now what tends to happen is a group would have a project, they would run, they would consider certain tasks, and on those tasks, the sensor, the tactile sensor or the force torque sensor or the vision would help or not help depending on the task. And so there is not a lot of kind of systematic analysis of, okay, perhaps we already know that in these kinds of tasks, it's really the fast, force torque sensing feedback that is crucial. But if we take away some sort of a dynamic part of the task, then it's not crucial anymore. So there's no reason to search for whether this modality really helps. So one of the things that could be really cool is if as a community we get together and we figure out, is there a certain, almost like benchmark or a set of tasks that we know are supposed to have some gain from a particular modality. And then perhaps release some data, for example, somebody could look into using perhaps very expensive and high quality sensors, but really showing that, okay, with this high quality sensor, you are able to gain good results from this modality, and then maybe others can take a look at, okay, what are the lower cost versions of this, noisier versions of this that are still useful. And so that would help, I think, both this understanding of which modalities are useful where, because you can do much more systematic analysis, and at the same time, this could also help the real to sim. Because, for example, if we have this kind of data, we can see, okay, maybe our algorithms can handle sort of level 0 of like very high fidelity, very clean data from an expensive tactile sensor or force torque sensor. But they're still struggling on the very noisy ones, so what can be done? Instead of throwing them at right away the very noisy ones and then just saying, oh, this is hard, and falling back on a kind of uninformed, simpler generalization topics. So that's one of the things that I think would be very useful. This is much more in the academic realm, not yet something that would be directly usable by industry, but the industry can contribute to that by basically saying, oh, we know these and these kinds of sensors are very good so far, or have the reliability that we would like, but they're too expensive for us, let's say, to deploy right now. So we really need to make, to help academia make progress to lower the costs, but maybe via this sort of creating the benchmark first that can inform.
I see. So exact the modality alignment problem. So do you think the representation learning can maybe avoid the embodiment alignment? Because if we train one policy, use the first hardware, then we transfer into another hardware, there will be the embodiment gap. So however, I think the representation learning can somehow learn partial for this problem. Do you think in future we can have the one super powerful policy, and then we can just ignore the embodiment gap? And how do you think the future direction for this?
Yeah, that's cool. So that's like one of the North Star that we're shooting for, because we're working on co-design, right? And we would like to consider all the different kinds of difference, right? And as ultimately sort of getting a policy that can deal with many of them, hoping that, okay, in the process, maybe it will discover some of the representation that is useful. Nonetheless, there could be directed efforts for actually analyzing much more as to what kind of representations are useful, and so it can also happen the other way around, that somebody else in the community would discover them and we would say, oh, that's great, this representation could really actually help co-design. So I think in this way, like both model, if I may say model-based or model-free, or more like analysis-based versus just end-to-end learning-based, they can be complementary.
Yeah, I see. So Professor Pulkit, what do you think about this embodiment gap? So I think your Dexterous calibration devices will be one super great method for the collect data from the real world. Do do you can you imagine whether we can use this data, maybe train the policy can work with another robot or the game hands, and what will be the difficulty if we want to solve this problem?
I think we can think about the problem at different levels. Like,
Yes.
so first is how significant of a problem embodiment gap is. I think a lot of it depends on the choice of the learning algorithm. For example, if we're doing sim to real, in simulation we can have a lot of different hands with a lot of different embodiments.
Yes.
And collect data for a lot of embodiments. And then, as happens in machine learning, when you go to a new embodiment, transfer should happen. So if you believe in sim to real, the embodiment gap is not a problem. Okay?
Yeah.
Then if you, but for some reason, if you still want to do real world data collection, then the embodiment gap is a problem. And the problem comes, I think we do a lot of transfer based on kinematics of the hand, but not the dynamics. That's how all the retargeting is happening. So again, if you're going slow, I think the problems are different. If you want to go fast, the kind of things that Georgia was also mentioning, like when you slip and you want to recover, you know, those kind of dynamic things, I think that is where the real embodiment gap problem is, in my opinion. And we even haven't scratched the surface, you know, for that. I think we are stuck in the kinematic territory. So yeah, I mean, my bet is simulation. Therefore, I think embodiment gap is not a problem. I think Dexop is going to run into a similar issue because it is built for real world data collection.
Yes.
But again, I think at least my personal intention was not necessarily to use it for data collection, but to really study, you know, what the hands can do and what are the limits of the hardware, more than using it for large scale data collection.
Yeah, that's why you developed the general benchmark for the evaluation, right? Yeah, I see. So, but how can we reduce the effort for the final fine-tuning after we have the pre-trained policy using maybe the Centurion or the simulation-based reinforcement learning treatment? How can we reduce this effort to collect more tactile sensor data and fine-tune this policy?
Yeah, so I think a lot of these questions come if we start with the VLA perspective. But we should rethink if VLA is the right solution to the problem.
Yes.
So I think if we start with the perspective that I am collecting, you know, data in simulation, then we have all the force and tactile data in simulation. We can collect large amounts of data. So the amount of data that we may need to collect in the real world is ready to close any sim to real gap which remains. Right. Now, when you're training in simulation, you can also meta-learn things. You can meta-learn things like how to explode, which can make real-world data collection become much more efficient. Right now, what happens is if you take a VLA model and you try to do RL on top of it, the problem is VLA has been trained with behavior cloning, so it only knows how to explore very narrowly. If the explosion is very narrow, then it becomes a problem. So what you want is for it to explore very broadly. But there is no mechanism to explore very broadly. But if you could train in simulation how to explore, then that problem becomes much easier. So I think we should think of simulation not just as a tool for learning control in the very narrow way, but also think of it as a way to meta-learn these strategies of how to explore in the real world, how to explore safely in the real world, so that we can benefit from real world interaction data. So maybe my suggestion is we should not start thinking by saying VLA is the solution. Let me figure out how to make VLA work. I think we should question if VLA is even the right solution. Think from the first principles, and then build our learning stack on top of it.
Hi, Professor Jie. Do you have different insights regarding this problem, regarding whether
so I think actually similar. Like I think I started to work on simulation for my application. It was around 2021, something like this, because I was and then I was in ETH, and then I saw a lot of colleagues working on the docs, and the locomotion started to work, and then I really believe simulation is the solution. But after several years, working on this and talking this morning, I still think locomotion is quite different from manipulation. So like locomotion, we interact with the ground. Maybe it can be soft, it can be grass, can be sand, but in general, our tolerance is higher. So like even for dogs, our goal is just to keep balance, but we don't care about them much about our gait. For manipulation, the control is really fine-grained. And a little bit mistake, a little bit error, it's disaster. And this is one thing. So the symmetrical gap, I think, is much larger than locomotion. Secondly, like simulator has been developed for many years from graphics community to today, and like NVIDIA, they jump in, they try their best. So the physical part, I didn't see much improvement, to be honest, for the last decade. And plus, a lot of things, it's also difficult to simulate, like soft body, those kind of things. Right now, we can interact well with rigid body, but that is only a very small part of our daily manipulation work. So I think, of course, every part have changes, but in the end, I believe if it's an AI problem, then it's a data problem. No matter simulation, or telework, real data, or human data, they just data. How can we collect those data and those data distribution match the real world distribution is very important. Secondly, it's about the reactive interaction. This is also, as other professor mentioned, like for robots, we feel and then we recover. It's like we have this interaction process, how to get to such distribution. No matter no matter we get this kind of ability from simulation, as what you said, maybe it's like a meta learning manner. So, okay, we work on rigid body interaction, but during this process, we somehow learn, the interaction recovery, something like this, even this kind of thing can be transferable, non-rigid body. Maybe it's true. But still very challenging. I think purely based on simulation.
I think I have same idea. So I think we still need to solve for lots of problems, including the symmetrical gap, modality alignment, and the in-body alignment, as well as the hardware co-design. So because of the time schedule, maybe we can raise a few questions from the audience.
Thank you for your talk. I have two questions. My name is Kim. I'm from Remark. It's an industrial robot manufacturing company. I have two questions, one for Pulkit and one for Professor Jeannette. So for the questions to Pulkit is, I know you've been showcasing a lot of good demonstrations in Dexterity with multi-fingers. I've been following up. Then I just wonder, so a month ago, you uploaded a video on LinkedIn of each robotic with 2 fingers, and just want to ask the reason behind still stuck to the 2-finger solutions for your startup. Is it because it's more useful? Is it more optimized towards picking up some delicate objects? That's one question. And to Professor Jeannette, I know you've been in the previous interview. You've been talking about some egocentric data, and I want to ask you some how much you believe in blind grasping. So when it comes to that, I know human beings, even if their eyes are closed, they can still do assembly. Up to what extent can Dexterous hand and the system can do at the moment? And are you actually, how much interest are you into it? Thank you.
I can go first. So I think the videos that we uploaded, the point was to show the interior gap can be closed. And we showed things which are deformable, things which are not rigid, do it at human speeds and faster. And also do it in a way that can be deployed at scale, which means the hardware is simple, deployment is easier. I think doing things with multi-fingered hands is definitely of interest, but that's a more open research question as of now. So that's the simple answer to that question.
Yeah, I think you have two questions. One is about user-centric data, another one about black control. Actually, I still believe black control is why I started with simulation. So at the time I believe with simulation, then the data is cheap and we can learn the black control. And you say for us, if you know, for example, the Bauza is here, then once we approach the Bauza, we can graph it blindly. I still believe it. But still, it turns out the final question, we still have a lot of things we couldn't simulate in simulation. How can we solve this? As I mentioned also in the talk, for some more complex tasks, even the reward, we couldn't really write down the reward. This is why, I think still user-centric data, no matter it can, we use it as a planner, general planner, or even future, we can even use it as somehow data for controller. I still believe they can help because we couldn't simulate everything in simulator.
So we're going to have last question. So Lucas.
My question is to Pulkit. So, in the landscape of full scale general purpose Texas manipulation, so what you see as the path to shared autonomy versus monolithic model, and how to combine this primitives, because most of the RL, if you train them, it's hard to compose them, chaining them for a long horizon task. So what will that change?
Is this for me? Okay. Yeah, so I think one goal of learning is so that agents can learn new things and pick up new things quickly. And I think that should be the goal also in context of dexterous manipulation. And in that worldview, co-learning where a human is involved in teaching the robot naturally makes sense. I think it is definitely the case that today's RL policies are very specific. And a big reason is that we are training from scratch individual models. And we don't really have a foundation model trained with RL. So I would say once we start getting to that level, then you would see generalization happen to different tasks. You would have the same kind of task level generalization that VLAs are doing today, but potentially with higher speeds and higher robustness. And the same way we are studying human-robot interaction in VLAs, we could study it in the context of RL. The other way to think about this is that VLMs are a good planner. As my colleague was saying, that we can use egocentric data also to have plans. So you could think about plans coming from these models, and then RL being the control layer, which is able to execute on those plans. So I'm optimistic about both of those futures. And as far as human in the loop is concerned, it can also happen at different levels, like whether it is to provide hints to a robot of what to do. The other big question is, reward design. At some point, reward design would become easy because if you have a small foundation model, it starts generalizing, it has a base policy. So for newer tasks, maybe reward design is not as critical. And I think we have seen this happen with RLHF, right, where you can give sparse rewards, the humans can come in and provide rewards. So how do you learn from different kinds of signals? Like sometimes it's a video, sometimes it's a human feedback saying good or bad. There are different kinds of feedback, but if your controller itself is good, which is what we as humans have, you can take this feedback very naturally and improve with it. I think to me the core problem is how good is the controller? If the controller becomes really good, then a lot of these questions become much easier to study. But we are not at the stage where the controller is really good.
I mean, could you more expand on like, even though the controller is good, we have different layers and they're working like atomically very good. What will be the mechanism, what do you say is the mechanism to combine them, like when to figure out chaining them in like a long horizon task?
So at least one, there can be many answers to this question. Like at least one architecture is to have goal conditioned, RL policies, where the goal can be expressed in different forms. It could be latent representation, it could be language, it could be an image, it could take any of those forms. And that could be the bridge, which bridges more high-level planning with low-level execution.
Okay, thanks a lot for all of professors who shared the latest insights regarding the Dexterous manipulation. And because of the time schedule, we will close the panel discussion. Thanks a lot.
The screen. All right, let's see if this works. Perfect. So a couple of months ago, I was in China, or last year during IROS, and I took this video. And one thing that really kind of like struck me was the fact that these systems are all like extremely like moving, dancing, jumping around. But the one thing they were not doing is making a lot of contact. And that lack of contact was really what kind of inspires us a lot in our manipulation work, is to build these systems that actually can go into contact. And if you look into nature or look into us, we can actually do contact very well, and we can plan extremely well under contact. And why is this? Because we have the systems evolved over like billions of years of like actually being able to do all of this planning while being adaptive. And today I will touch on a few points that how I see it of like what we need to do to actually push this forward and actually make a difference to how we build hands, how we build systems that manipulate while being safe and making contact. So I brought you the motor homunculus, which is a concept you might be familiar with. You might have seen it before. Raise your hand if you have seen the motor homunculus before. Okay. So you're all familiar with whatever is enlarged in there means that part of the body, in this case, has much more motor actuation, or is much denser in that sense. And I will get later to its sibling as well. What I want to touch on is 4 points. I want to try to touch on the question of how can we improve learning for manipulation, and I will present you a method on that. How can you think about muscles instead of motors for manipulation? I want to talk about benchmarks. How can we bring in benchmarks for dexterous manipulation, specifically for that topic? And I will want to touch on the question of what can we do in terms of building soft simulators for richer contact. And so to get started, I want to talk about ligaments, bones, and joints, everything that we know in nature our hands are made of, and how would we produce this. And in conjunction with this, I will keep switching between both the ligaments, bones, joints question, as well as the controls of these systems. So I put this slide together last week where I thought to myself, how can I best sort of bring the last 5 to 6 years of development together? And so let me try it with this slide. So we started in 2020 roughly, trying to print hands from scratch. This was the vision controlled shedding project. And in this project, we were trying to figure out a way of building hands that are fully printed. End to end, we want to have the whole hand, including its ligaments and everything printed. So like here you see Thomas's hand scanned as the student working on this, and we kind of derived from the scan of the hand of the underlying bone structure. We added some capsules to it, and we added some ligaments to it, and we tried to print this. So what we came up with was our vision controlled shedding system approach, where we're using an inkjet shedding principle to sort of deposit soft, rigid and other materials to basically create a hand that has all of these features in there. You could print other things. You see here on the print bed, there's not just a hand, there's other robots as well on there. And we wanted to try to understand how to build synovial joints, how to put capsules around this and build the structure end to end, and have in the end a structure that can be actuated where the whole thing is actually printed. And it took us a long time to come up with this and to get it actually to work. And it was extremely hard to actually have tendons that are printed and don't rip. And it made us a strong learning that, like, even though the idea is kind of maybe interesting to be able to print it all at once, it doesn't lead to the most optimal sort of parameters that you might want to have and properties in terms of durability. So that's why we started working on the robotic hands that are being assembled. And this project then eventually became Mimic as a spin-off from our lab, where we looked into how can we make hands purely driven by the mission of what we already know, what is robust about it. And these hands are fully assembled. Individual parts are either printed or machined, but still using a tendon-driven architecture. And so at Mimic is basically being challenged by industry customers to solve those parts in the chain where the human worker currently has to still do them. So here's an example where Audi has asked us to make a robotic system that can, or take our robotic system, that's our hammer, and actually automate the insertion of these rubber gaskets into door frames. And so Mimic has then basically gotten this mock setup where you see here's a door frame, where you see these rubber pieces, and what happens is, now she's going to be kind of mean, takes it out again, and the robot has to do it over and over again. And yeah, it's an interesting thing to do, like that you actually have a robot that can just sort of like go over and over and sort of like keep doing the same task over and over again. Unfortunately, it's not very intelligent because I couldn't be able to right now tell this robot to insert another rubber piece because it would be out of distribution. But for that, Mimic is trying to really tackle this from like 3 stages. The first stage is just to do human video pre-training on a large scale, so just taking egocentric inputs. That's off the lower part of the pyramid, and it's the biggest part in terms of data. Then the second part is just using teleop data using glove data where the human is themselves doing the task and you recording that task. And it gives us a speed up about 5 times, and it's much cheaper, obviously, than hiring teleoperation personnel. That's what you see here on the right side, where it's actually about now picking up the items. For example, here we are learning how to assemble a drivetrain unit, but this is teleoperated. So these are the 3 pillars that we use to then, for example, have emerging behaviors, such as here where you place a base fixture down and then you come get a couple of fans. The hand has now learned that this is a task to do. Assemble this, please. It goes in there, but then we kind of annoy it. We steal it from the hand. So for like, this is not a good one to use. You should take another one. And it's able to at least operate within this realm in somewhat adaptive fashion. And now the other one hand dropped it wrongly. The other one comes in and it adapts it and trying to place it in there. So we see already initial emerging behaviors by just scaling that data with these 3 parts of the pyramid. But it's still not intelligent, unfortunately. You agree, I guess. So going a step further is how do we make this proprietary solution somewhat accessible to also researchers, that we can actually work with this and that our lab can work on it. And that's where we thought about Orca as an initial start, to make just an open source hand that uses sort of a simple approach to building these 5-fingered hands, and use this hand as a starting point for other machine learning work and other endeavors that we want to go into. And so here in this step, we basically want to have an easy assembly guide that you can just click from our website, all the way from like printing the parts to making the rubber pieces from silicone to assembling the tendon. Everything is explained with small little videos. So if you want to build this hand, you just go on the website, you download the videos, and you can assemble it. It's fully open source. We have an auto-calibration procedure in there because in the initial version, we only used motor proprioception. And we showed also certain amounts of stress tests, and also that we can do 7-hour-long learning with this platform. So you can run an imitation learning approach on this hand, and it will last you sufficiently long. But as I mentioned already, teleop is very tedious. It really takes some time to get this to work. And it's very slow as well. Like here you see it, but it is in real time, but it's tedious. Like you just learn to stack cubes or learning how to pick up a cup of water and pouring it. It is not very much the way to scale. So my students looked into the current stack of how we do learning with these systems. And when you look at that, you see that currently diffusion and flow matching is kind of the way of many of the underlying architectures, what they're relying on. And they are good for going from some sort of a noisy image to actually generating an image. So in the 2D space, that seems to be working great. But now comes the point which I'm trying to make here, which I think this is a dead end in some sense using these methods. Why? Well, you start off with your data over there on the left. And this data goes through many steps of adding noise to it. And then in the end, you have to go back and reverse do this, denoise all of this in the case that you're doing training with this. And so if you do this for 1,000 steps of denoising, you get really much to run into this problem of having vanishing gradients and your memory can really easily blow up. So these models are not very scalable in our opinion. While if you look into normalizing flows, those actually give you a single step forward and backwards in terms of operating. So we start off with a base distribution, and with the operators that are invertible and differentiable in a normalizing flow architecture, we can actually go from that into any distribution. So it's a fairly rich way of describing these distributions. And since we do our research in Switzerland, we have many rivers. We were inspired by one of them called Sernf. That's actually the name of the river. It sounds kind of funky, but yeah, it means to flow, and that's the river. And that's also the acronym of our method called sample efficient RL with normalizing flows. So here we take in the data, the information from the system. So this could be RGB images, joint poses, artifact poses, tactile sensing eventually as well. Wasn't done for this work yet. Then we have our normalizing flow actor down at the bottom, which basically consists of K of these normalizing flow blocks that start from a normal distribution to whatever distribution you need. Then we have this intermediate output set of actions that we then place into our Q value creating action chunk critic up here. So you see this block goes into the action chunk, into this transformer, and then we can roll this out. So how do we do this? On the part initial policy, we start off with, on the one side, with some teleoperation data, very little amounts, to then do rollouts. In this case, we tried a task called scissor retrieval and cutting a tape, which we actually did not manage to do with teleoperation. So that's just sort of a quick sort of thing, like with just teleoperating this, it's really difficult to do it because you have to go in with the robot, pick up, you don't feel what the robot feels, pick up the scissors and cut the tape. And doing this over and over, we rarely get it to work, and we had a lot of failed demonstrations. Another task we took here is we also did just pure simulation on an upside down, palm down, rolling the cube task, and in the end, learning it on the real system. So let me show you how this works. We basically have on the one side the actor block that allows you to forward and reverse to come up with the actions. And on the right side, we have the critique block. We copy these actions over. Let's go to the results. So here we are picking up the scissor, and then the scissor, this is the final result after doing the full stack. And let me explain the stack. So if you look all the way on the left, we do imitation learning for about 70 imitation learning episodes. Then we run offline RL, and the performance goes up tremendously. So blue line is the final cutting step. Scissor retrieval is not so hard, but the cutting step is the hard part. And then afterwards, we're using the architecture I showed you, doing online RL on this, and we can actually get to a 90% success rate with the scissor tape cutting task. The same works with going straight from distillation, so no teleop, just simulation, to online RL on this setup. And we also have done this for pick and place tasks as another example. Okay, so now I spoke about the motor homunculus. Let me speak about the sensory homunculus as well. In the case of the sensory homunculus, that's actually what we need to make these hands more sensical, like because the human body has not just motor units or muscle units everywhere, it also has sensing units everywhere. So how do we do this? We took our Orca platform. Everyone was complaining about the fact that the Orca platform doesn't have good proprioception. So we added the proprioception to it. So, and I mean, it makes a big difference. If I add disturbance into it, I need to properly capture all of the joint disturbances in all of its states. So this is what Jehan has been working on. We just released this paper on arXiv last week, or I think, or 2 weeks ago. So please take a look. But now we can actually, with the Orca hand, capture the full deformation. You see on the left side, it actually properly captures now what it is feeling. It's not anymore motor induced, but properly. I mean, this is not news in that sense, but what was new about it is that we have now developed a stack that can give you a unified readout stack among a very efficient, fast readout for all kinds of analog sensors that you want to throw into your hands. So we start off with joint angle sensors and Hall effect sensors because they give us both proprioception and tactile feedback in a very easy way. We only need 3 signal lines, which makes it super easy to route this through hands. We don't have a lot of extra lines for every sensor you need to throw in. And it runs for 20 channels at 1 kilohertz, and we have shown it can go stable up to 1.5 kilohertz. So that's our starting point. We want to make these Orca hands in a way that can really fast sense because we want to have dynamic behaviors with these systems. And so like here's a characterization. So we do proprioception, it tracks it well. Once I hit the obstacle, you see it actually still tracks it properly, while motor kinesthetic sensing would have not gotten you an accurate reading. And we can also read out forces accurately. And we characterize this both with force sensors against our on-the-finger force sensing and also with mocap, or in this case, apotex. So this was Orca. Going a step further, we still continue our work on 5, which was sort of the first project that got Mimic started. But 5 is very much about the biomimetic design of the joints. So here it's the question of how can you make biomimetic hand designs that can be used for surgery support. That's one of the projects where we're collaborating with the hospital, and they're very interested in using our hands in their scenarios, what they have in an OR typically. So here we are not using ball bearings anymore. We're just using rolling contact joint designs. So you see each joint here, except for in this example that doesn't have it, but the current hands, I don't have a picture, has everything rolling contact joints. So you have abduction, adduction, MCP joint with the 2 degrees, and then also DIP and PIP joints, all rolling contact. What do we use them for? Is we use them, for example, for heart stabilization in a PICC heart surgery. So the hand can come in, stabilize the heart, and the surgeon can now disengage and let the hand do its thing of holding the heart in the stabilizing posture, and the surgeon then does like a valve repair, for example. Currently, this is done, just to give you an understanding, this is usually done with suction tools where you like a nurse has to stand there, wear a glove with a certain amount of suction and just holds it to the heart, and it destroys a lot of heart tissue during this open heart surgery. So we want to get away from this, that the robot hand can just support these operations. So why not only doing rolling contact joints? We can also go larger. Why not? Like this is 3 times the height. This is the mega hands. We thought we also could use hands in other scenarios. For example, here we're going into a disaster site where we basically have the hand go, this was in Japan, so Yasu and Ronan from the team, we built the hand, we flew to Japan and put it onto an excavator and show we can do these things. This is a robotized Menzimuk up in Zurich, where we're actually able to control the hands and do these maneuvers. And this is just using fairly low-tech, just VRs to sort of retarget. And lots of fun. Like this is fully sort of connected end-to-end to do stuff with this. Maybe not in your bedroom, but out there in the wild. Okay, so this is the mega hands. We can obviously also do other ways of, for example, doing manipulation. One of them is like, this is a project we did a few years ago where the team built Raptor, and there's other projects where they took Raptor out in the wild. So if you're ever curious to see these things, we also built other kind of grasping systems on drones, but we haven't put any hands onto drones yet. So one thing I want to drive home to today, as I mentioned, was also this question of muscles versus motors. Why should we care about muscles? Let me explain. So, well, bioinspiration is a bad argument. I won't use that. But let me use something else. If you have 2 muscles, you can have 2 mechanical effects. Right now, most of our learning operates on position-based control. We are not even thinking about force control for most of the learning manipulation. Unfortunately not. But we should be, because the control input could be both a bias and a co-contraction term. That means you're controlling both the torque that the robotic hand is performing independently of the stiffness that the robotic hand is performing. And really, these two things together is I strongly believe, and if we can build hands that can do both simultaneously, we get much better control performance and much better learning performance. As an example here, this is a 2-muscle unit that we built in a lab with using hazel muscles and clutches here. And this allows these fingers to move, this element to move back and forth and to control it. But really, if I want to go into interaction, we need basically antagonistic actuation. So 2 muscles that each can only pull. And this way, they can be stiff, like my hand can be stiff like this, or they can be soft like this. But it's the same hand that just changed my muscle tone and the way I pre-tension my muscle. So the way you can think about this is my AI picture in the slide deck. On the left side, you're running on a rigid ground. Your muscles, both the antagonistic muscles will go soft and stay soft. So you can do this rigid contact. So you kind of do an impedance matching. And if you run on a soft ground, like you step 1 foot off the asphalt and you go on the soft ground, you will go to high stiffness. And because you have this ability to co-contract in the human body, we can do this very fast and very dynamically. And we are not doing it in our robotic hands right now, and we should be starting to do it now. So that's why we're also interested in building robots made from muscles. So this is an example of a biohybrid muscle. Yes, granted, it's only 2 centimeters long, but it's a starting point where we can control muscles that are grown from tissue. We can already start making jumping robots. We can make walking robots with these. So we can start making something with that. We've also been using not just biological muscles, but also using hazel muscles to build, for example, here, a jumping leg that uses antagonistically contracting units that allow it to jump over this terrain. Just not using motors, just using muscles to achieve this. And the nice thing about this, it doesn't even require necessarily closed-loop control to achieve this behavior. It's just the 2 muscles pulling on each joint, one pack for an antagonist, another pack for the other agonist. We can also start making hands from this. So this is something that Misato worked on. She started building the very first one that we got to work in the lab, where we had multiple hazel muscles in one unit using one of the rolling contact joint hand designs. And now this gets us the question of how do you start evaluating hands? And this is what I want to now motivate with this slide. You can have many different hand morphologies, but you don't know really which one to go with or which one to use or which one to build. Because, yeah, this thing could just go on. It's obviously a very biased list of hands that we build in the lab, but we don't really have the right metrics for it. So if you look in the medical field, they use performance-based outcome measures. They look into this from a perspective of, we don't care about how many degrees of freedom you have. We don't care about how much motor torque you can produce. We only care about what performance you have. And for a patient, that's anyways anything you can measure. So what do? They do, for example, the box and block test. They ask a patient who has maybe had a stroke to see how well they have recovered from the stroke by taking blocks from one box and putting them in the other side. And so that's why we came up with Ponder, which is our framework that allows us to do this. It's a 3D printed framework that as of today, you should be able to download everything from our website, the full set as a 3D printed toolkit. And you can test vertical, you can test grasping, you can test scissors, all kinds of tasks. In the interest of time, I just want to bring across the points. We want to have something where you can get a score out of this, and so how well you did it and how fast you did it. And we want it to be easily 3D printed and also simulatable. So you have both a simulation and also the ability to test it. So this is a human doing the task, and we get a baseline score from the human performing the task of how fast and how well they do the task. So this shows you sort of a subset of those tasks. But we also have sort of defined them as a set of tasks that are actually derived from the CRASP taxonomies that you know. And we made sure that we covered all of the areas in the existing CRASP taxonomies in literature, so that you can not only run this in simulation, but you could also run this on the real hardware. So this is a speed up of Davide collecting all of the scores. And in the end, you end up being, for example, for manipulation tasks, we tested using different amount of fingers of the orca hand. And then we found different scores in this radar chart for the different type of tasks you could be doing. So, and what we also found in this context is we are nowhere near to being at human performance. So we still have lots of way to go. And here, this just shows you different amounts of artificially locking joints in our one-hand design. This is all teleoperated. and the human, that's obviously human doing it by themselves. So last thing I want to touch on before I close is, so what will it take to simulate now also the interactions? Not only the hands that I showed you, but also the interactions. And so here you see we've collected something called Pokeflex, where we just poke randomly at dozens of objects that are soft. And then we build a simulator for this. And for this, we already have understanding of the well-modeled physics, such as the ones I'm showing here. But we have a very poor understanding of the poorly understood physics that will in the future shape a lot how we're building these robots and building a simulator for this. So system hysteresis, the electrostatic actuators, how do you living actuators in these models? How do you have fabrication error characterized? And so for that reason, we developed a framework that's called SOURCE. And maybe to motivate this briefly, we looked into what is there. You can use Mojoko, ICRA, that's a rigid simulator. You could use a soft body simulator such as SOFA or Jane Queen, or you could use an FEM tool. But they all have their trade-offs. Either they don't do soft bodies, or they're too complex, or they have a limited accessibility in how you can interact with them. And with SOURCE, we basically have an energy minimization technique that allows you to define the simulator, put the energy in there, and sort of model the system. It's called soft over rigid simulator, because obviously soft is the thing we want to do. Or you could also call it source over rigid simulators if you're into recursive acronyms. What it allows you to do is you define your meshes, you define your lists of physics and your parameters, and then the simulator itself will assemble it for you and will solve it for you. So you can try out what you want to do with them. Okay, so maybe one example to show on this would be this example where we're poking at the object in our motion capture studio. Then we get all of these nice point clouds from these objects with RGB data. And then we can now do proper comparison of the data. Sorry, this kind of turned out dark, but we can do then meshing of the simulation against this data. And then we can get, so from the poking, we can build up simulations of these soft objects in the simulator. And we can also do this with other scenarios where we might want to do optimization. So to wrap it up, I'm all for the question of how to build up open source tools that allow us to basically develop systems that can be, somehow the slide always crashes on me when I click on it. Okay, that happened this morning as well. This is unfortunate. Let's try this. Okay. There's something about the slide that always crashes. I have tried everything, but let me summarize it now without taking too much time. So I've covered onto 4 topics. One, I want to bring across, and hopefully that came across, that in learning, we need to rethink the learning architectures that we currently do. So we need to think about, do we want to use diffusion models and flow models, or can we use normalizing flow models, or other ways of learning more sample efficiently? The second thing I've covered on was the question of, turn this off here, just quickly cancel this. The second thing I've covered on is, should you use muscles instead of modes? And I hope I could bring a point across that using muscles has the advantage that we can control both compliance and stiffness independently. The third thing I want to bring across was that benchmarks is really something we need to think more about, that we can compare robotic hands against each other. That's why I presented to you Ponder. And then finally, the last point I was trying to make is we need simulators that not only do Mojoko-style rigid simulation, but we need simulators that are capable of doing more than this. That simulators that are capable of doing soft interactions and also cover other types of physics that you might not otherwise be able to properly simulate. And with this, I'm open for any questions. Thank you very much.
This is the first presentation in software robotics. So now the topic is please.
So I'm intrigued by one of your slides, which had the, very cool talk. I was intrigued by one of your slides that had learning from illustration, I think, that offline RL and then online RL.
Yeah.
So online RL did a good job, but from that starting point.
Yeah.
Right from scratch, and what are the difficulties? RL from online.
So with online RL from scratch, I think we wouldn't have the ability to do this on a single station, right? The online IL from scratch. So that's why in the one scenario we used about 70-ish sort of demonstration, teleoperated demonstrations to sort of regularize where we get started. And the other thing I might have not brought across clearly is it was not only that we used imitation learning here, but we also leveraged a lot of offline RL on all of the crap data that we reported. So that actually the operator didn't feel so bad about themselves that they had recorded a lot of bad demonstrations too, because they were actually useful, and with the offline RL approach, we could actually bring them in with the proper sort of attributions to this. Yeah.
And the online RL was on real? In real?
Just in real. This was just in real. This was fully in real. Maybe I show you this on the slide. The online RL was just running on that single robot, single system, and learned that behavior. Actually, I won't go there right now. It will probably crash my computer again. So, but it was, yeah, over here. So think of it, for this task, initially when you started just after offline RL and we started the online RL, it would never get to the cutting point, barely. And so it took another maybe 100 or so demonstration and then was able to reliably do the cutting. And for the simulation one, we didn't use any teleoperation. So for the cube, we just did this purely in Joko.
Okay, then one last question.
Yeah. Thank you for your presentation. Very nice work. The question about the source.
Yeah.
Very cool simulation. I saw several weeks ago that you posted on LinkedIn. The question is, you model like only soft part. What if you have a rigid part inside of the soft parts?
Yeah.
Are your model capable to handle that?
Yeah, so we have currently a module, if you email me, where we put in also rigid extension to it if you want to just have an articulated body in the simulation. We have a module for it. It was not part of the first publication where you can define any stiffness if you like, but you obviously will run into problems if you have a huge mismatch in Young's modeling between different components in your simulation. Also, what I didn't touch on, but Henry is working with GPU acceleration. So we have already a GPU acceleration about to be released soon, where we show that we can actually run all of this on a GPU.
Thank you.
Thank you. Thanks for Professor Katzschmann. The next presenter speaker is Professor Jeannette Bohg. She is an assistant professor of computer science at Stanford University and the director of the Interactive Perception and the Robot Learning Lab. Her lab focuses particularly on robotic grasping and manipulation. She has received several awards, most notably like 2019 ICRA Best Paper Award and also 2019 the Early Career Award and also 2017 Best Paper Award in Law. So please, the stage is yours. Thank you.
Sorry, I'm trying to get this in full screen. Somehow doesn't quite work as I want. Okay, let me just leave it like this. I hope that's okay to get started. Okay, thank you very much for the kind introduction and for the invitation. So today I want to talk about learning dexterous manipulation via learning to play. And I sort of think I probably don't need to motivate this too much in this room, like why we care about dexterous hands as opposed to, for example, grippers, which I think is like a very dominant hardware platform right now. So here's an example that actually one of my students found on YouTube of a person basically using tools. And here it is a bit slowed down, the entire situation. So you see the pickup, you see the person actually doing in-hand manipulation of this tool, even twisting it when noticing that it's not quite in the right orientation. And so all of these things happen really quickly, right? Like without thinking for this person. And it would be impossible to do it in this way with a gripper,
right? Like with a gripper, you would need to have an entirely different strategy, of course. So that, for me, motivates studying dexterous hand or multi-degree of freedom hands. And yeah, so I hope that convinces you if you're not already convinced by being in this workshop. So today I want to talk about two works that we have done recently. One of them is Sim-to-Real, an object-centric policy for zero-shot dexterous tool manipulation, which will be presented at RSS. And Kushal should be here. Kushal, wave your hand. Oh, over there. So he's going to present a poster later and about this work, and you should ask him everything about it. And because he is one of the first authors, and also bug him about this new work that I'm going to talk about today, which is Play to Perfect. So basically, we start off with Sim-to-Real, which is more like you could look at it as a play policy that has like the basic skills already kind of learned, and then fine-tune it to do actually contact-rich dexterous assembly of different tasks, okay? So, okay, so I think, again, if you're in this workshop, you probably work with dexterous hands, so you probably are aware of how hard this actually is, right? So you're trying to control a high degree of freedom hand. So here it's a 22 degrees of freedom hand. It's actually the sharper hand, which was kindly lent to us by the company. And it's mounted on a 7 degree of freedom KUKA arm. So you have to control all of that. There are multiple contact switches. You have to grasp. You have to in-hand rotate. You have to use the tool. Finally, all of this has to happen at a very fast speed. So all these videos that you see here, just emphasizing this, is at 1x speed, okay? And we're doing a 60 hertz control as well. Okay, so how do we achieve all of these examples that you see here? How do we train such a system right now? So a lot of the related work actually, there's a whole category of related work that approaches this from the viewpoint of teleoperation. So here, I just picked one, I just picked one work here, and I just want to show that I don't know if you ever tried to teleoperate a dexterous hand. I did with a glove. Not even with just like a visual system like here, but it's extremely unintuitive. So I could not even do the simplest thing. I could basically at most do pick and place, right? And so because dexterous teleoperation is so hard, it kind of restricts what you can actually let the robot do when you teleoperate it, right? Like although in principle it's capable of doing much more with this dexterous hand. So I think teleoperation, at least with the systems we have right now, kind of limits the capability of a robot. And then there's, of course, this other category of work that learns these kind of dexterous manipulation strategies from simulation. And of course, what is nice is that experience in sim scales actively with more compute. But of course, because it's simulation, the data is of course mismatched, or there's a domain gap to real world data and from the real world. And we got one trick up our sleeves, which is basically domain randomization. That was, I think, at least popularized by this now classic OpenAI paper. And and that way you can bring these two distributions closer to each other, okay? But there are, of course, like lots of work that kind of do this. But one thing that we also see, although these capabilities that these systems show are like really impressive, they do require quite a bit of task-specific reward tuning environment design as well. And so if we have to close the sim-to-real gap, it kind of requires task-specific engineering so far. And we really wanted to have a policy that can actually do all of these manipulation skills with one policy only, instead of training all of these kind of atomic skills, let's say, separately as prior work has actually done, okay? So our key insight in this work, Sim-to-Real, is that we can unify manipulation as a goal-reaching task. And so what we basically do is we give at rollout, at inference, we give the policy basically goal positions for the policy to reach with this object. So this is object-centric again. We are giving it object goal poses, essentially. So then this policy is really a goal condition policy where the goal is the 6th of object position. Okay, so this is the title of this work, Sim2Real, with this amazing team. Kushal is here today, and he can answer all your detailed questions as well. So let me go into the details. So basically, we defined this unified objective at train time, which basically manipulates random objects to random goals. So we have a bunch of procedurally regenerated primitive objects like these ones. You see they have kind of a handle and kind of some kind of tool head. And then we sample random goal poses that start kind of on the table. And then we train our policy to reach these goal poses using SAPG, which is a variant of PPO, and we found that it works really well for us. And so this is kind of how this looks like at training. As you see, we use ICRA in this case, which can be massively parallelized. And here's just a little bit of detail on the reward. We basically, instead of like representing it somehow as a mesh or like as a pure 6th of pose, we actually have particular key points on the object, basically on the bounding box that we ask to bring as close as possible to the goal pose. So that's how we define this reward function. Okay, so this was training with this unified objective. And then at inference time, we basically collect a human video demonstration. So this here is basically this video demonstrations for picking up this brush and, like brushing this garbage into this, whatever it's called, this little shovel. And then here you see basically the sequence of goal poses that got extracted. We use foundation pose for this, by the way. And then at rollout, the robot basically tries to use this policy that it learned to basically get the object to follow these key points. Okay, so here's how this goal pose condition policy looks like. It takes in proprioception, the grasp bounding box, so there's kind of label for where the handle is in the current pose, and then a sequence of goal poses, and then it does this. So here's what we get from this, right? So this is one single policy that can do all of these tasks, and it has, during training, never seen any of these objects or any of these trajectories. And so by specifying a sequence of goal poses for these objects, it can basically do all these tasks, okay? And here's also comparison with baselines. So the Sim2Real policy is more reliable as, for example, basically just tool grasping and then keeping the grasp steady and trying to do this task, right? Like, because often when you pick up a tool, you actually do want to adjust its pose to actually use it. And then if we do kinematic retargeting from this demo, that also doesn't work really well, as you see like in the last part. We do have some failures. So for example, object drops after a grasp, or incomplete in-hand rotation here with the spatula as well, and then it cannot really reach the goal, or failed grasp as well. Which I like this video. It looks like The Thing, if you remember that. But so one thing that is really nice is that because it's close to policy, it actually does recover from failure because it has seen this during massive parallel training in the real world. So I think that is something that is really compelling about this. And if you're curious about this policy, you should totally play around with it yourself. So this is, with this QR code, you get to the webpage. If you scroll down, you find this cool in webpage kind of little app where you can actually manipulate the goal pose or basically teleport the object again on the table and stuff like this. And you can play around with it and actually also find out about in a way, all the boundaries of where this actually works. So pretty fun, actually play around with it, encourage you to do it. Okay, so so I think we wanted to get rid of this task-specific engineering. So and instead of training a policy for each of these tasks that you just seen, we find this unified manipulation objective that, arguably not all tasks can be described by a sequence of goal poses, but many can. And if you use that unified manipulation objective, you can do all of these tasks. Okay, now that's pretty cool. Basically, at least in Sim, you can now do more tasks, and that also, if you do domain randomization, we still need that. You can transfer this to the real world. Okay, let's talk about some remaining limitations of this work. So first of all, the policy only tracks the tool it's using. Okay, so that means there's really no environmental awareness. So it doesn't know, like you've seen it do things like brushing the trash into the little shovel. Forgetting the word in English for this. What is it called? Dustpan. Thank you. It does that not because it knows where the dustpan is or where the trash is. It does that because it follows this trajectory. But even if we somehow give it this trajectory, it can even do some contact-rich task, but it doesn't yet know how to even let go of the object because it hasn't learned that. So that was kind of like Kushal and Tyler's first attempt at solving the Fabrica benchmark. So we were really intrigued by this. So let's maybe move on to this new work that you won't even find on arXiv yet. Sorry for that. We're not ready yet, but I'm going to tell you about it anyway, and you can look out for it. So we call this work Play to Perfect because we thought, okay, this sim to real, it kind of learned, but with the simple unifying objective, it learned these kind of basic atomic skills, right? Like picking something up from the table, doing in-hand orientation, holding something to use it. So all of these kind of atomic tasks that are useful for a variety of assembly tasks as well. We were wondering, like, okay, like, can we take this play policy and fine tune it, and what actually matters for this? So this is this follow-up work that is not at RSS. Sorry, this is wrong. It's submitted. Forget about this. The sim to real is at RSS. But here's the basic idea, right? Like, so we use sim to real as the play policy, and then we fine tune it with RL, hopefully fast, compared to training from scratch on these different kinds of benchmark tasks that are actually in different benchmarks. And so how do we define the reward in this case? So again, we have these benchmarks that we use, Fabrica and also the furniture bench. And we take our CAD design from these benchmarks and basically define a reward function by disassembly, right? Like, so the original one is like a model is basically all assembled. And by disassembling it, we can define a bunch of goal poses as well to it. And so at inference time, so we train the whole thing, the fine tuning basically works with the same algorithm. And then at inference time, here's basically the input and output of what you see, right? Like, so we have, first of all, we do pose estimation using foundation pose again. We also find the goal pose once we have the fixture detected as well. There's also a grasp bounding box still defined, proprioception, and then it goes into this fine-tuned policy to output joint position targets. And so these play pre-training yields actually effective assembly policies. So here are kind of the tasks that we looked at. So this is peg and hole, where we actually also changed the tolerance. I will talk about this a bit later. This is just like picking up this pillar and putting it into this, or then grasping the beam as well and putting that on top of everything, or screwing in a table leg as well into this furniture bench table. Okay, so now let's talk about the questions that we were interested in. So we were wondering, like, can this, like, instead of doing this play pre-training, since we have all these CAD models, why don't we just define a dense reward? Right? Like, we can probably do that with our assembly by disassembly reward definition. We can just make the reward denser and then skip the whole pre-train. And so what I show you here on top, sorry, there's a lot of information like right away on the slide, but basically if you look at the top row for now, you see our approach of fine-tuning the play policy in blue. And then you have on the x-axis the training time, on the y-axis, the success rate. These are all things we've done, we tested in simulation, by the way. And so then as baseline, we have from scratch training of this policy per task on a dense reward, and then from scratch on a sparse reward, which basically means you get to the object pose goal. And so you can see there's a huge difference between using our play policy for pre-training and training from scratch, even with the dense reward. And so now if you look at the bottom, you see that eventually the dense reward is also better than the sparse reward, but it still takes significantly longer to do it than using the play policy for pre-training. And also this from scratch baseline, it actually is pretty brittle. It learns the weird kind of strategies that are not very robust in the real world to force perturbations. So here on the right side, you see that increasing basically force perturbation on the x-axis, and on the y-axis again success rate. And in blue, you see the fine-tuned policy from play. And in orange, you see the from scratch baseline with dense reward, and it actually fails really quickly when you introduce these force perturbations. Yeah, so this was our first question that we asked. And then we have, we also wondered how maybe we can use the play policy directly for insertion if we just kind of define, the goal pose in the end. And that actually works. So we can take sim to real if the assembly task has actually a very high tolerance or a very loose clearance if you want, right? So then you can even use the sim to real policy with a 60% success rate. But as soon as you go into more tight tolerance tasks, sim to real display policy actually is not very successful. So this fine tuning really helps. So and finally, we wanted to know, okay, what actually enables this fine tuning? What matters in the play pre-training that makes the fine tuning actually effective? And so we varied these three different kind of ingredients for the play pre-training. So if you remember, the sim to real was trained on a diverse set of procedurally generated objects. We also basically experimented with the training objective. Maybe it's just a translation, maybe it's just a rotation, right? What actually matters? We wanted to know whether the randomness in the goal poses matters and the threshold for actually giving the reward at the end as well. How much time do I have left? 0? 5 minutes? Okay. Okay, I'm just wondering how much in depth I should go into this. So first of all, if you look at the object diversity, you have basically in blue, our approach versus using 100 objects. So our approach, I forgot, is it 1,000 procedurally generated objects? Yeah, Kushal is nodding. And then, but it seems like 100 objects is actually fine, right? So you just need some diversity. You don't have to crank it up to 1,000. So that's interesting. And then we looked at, the training objective, meaning we looked at whether we can train maybe on only in-hand rotation versus only translation. So here on the bottom, let me actually go there now. So here at the bottom, right, you see an orange, if we only change the rotation of the goalpost instead of also translating it around. And you see that actually works quite well, because, but if you take away the rotation and you only do translation, that is not very helpful for the play policy, actually, to then fine-tune it for a particular task. Then finally, we also looked at trajectory diversity. So instead of randomly sampling goal poses, we actually had some predefined 10 or 100 trajectories that we would basically train with different objects. And you see that also has a detrimental effect on training speed. And finally, goal precision. If you basically train with a very loose tolerance in terms of reaching the goal, that also really doesn't help to the fine-tuning later on, essentially. So because the policy is pretty loosey-goosey, I guess you could say. Basically, when you fine tune for these high precision tasks, you basically have to learn a lot, like later on. Okay, so here are a few more examples of how this actually looks like with these tasks. So again, these are just a few examples of those. And what I like about this is this kind of retrial behavior, which is so hard to kind of hard code otherwise. And again, remember, the representation of the object is just like a bounding box of the object as well as input to the policy, so that it could, in principle, generalize to all sorts of different objects. But here, for each task, we actually have one fine-tuned policy per task. In Sim2Real, we had one policy doing all of this, but here we are fine-tuning it from display policy to these particular tasks at speed, right? So we don't need a lot of compute anymore. Okay, so I'm already at the end, so I just have a few discussions. So these were the two works I told you. So it's basically play on the left to perfecting on the right, if you want. And so here are a few takeaway lessons that I just wanted to share with you. So the hardware is really critical. So we started off this project with the Allegro hand, and not to bash the Allegro hand too much, but it's super large. You can make it compliant, I think, but it's not, in terms of the hand design and kinematics and everything, is really suboptimal. So there's also a large Sim2Real gap in modeling. And so as soon as we actually went to the sharper hand, which has like a more human-like kinematics, the learning and simulation actually became much easier just by exchanging the hand. That was interesting. So, we are not at the end of hardware advances. And probably better tactile and force sensing will also be critical. If you want to hear about that, I'm giving another talk later where I'm doing a deep dive into my thoughts on that as well. But here's some remaining limitations of both of these works. So right now we are having this goal condition policy, and it's basically the object pose represented as a bounding box. So that doesn't necessarily always work for every task, right? So we have to rethink that. The main source of failure in this entire thing is, of course, vision. Vision people, please work on better tracking. It's literally that. The problem is that things like foundation pose always ignore occlusions, which are, of course, constant in manipulation. And then we also, if you remember, we have to actually kind of manually specify the object graphs region, which helps exploration. And so in general, this whole object representation and using vision for tracking objects is kind of annoying and makes this whole thing still a bit brittle. And so there's also this other direction to come at this whole thing, which is learning from in the wild videos. So if you are interested in how we do that and maybe how these two things can meet, then please meet me and Jia Ying, who's going to present this on Wednesday at our poster. So thank you so much for the time. Happy to take questions if there's time.
Thanks a lot. It's really inspiring. So due to the time limit, we only have one question open to the audience. Please.
So my question is, what is biggest strategy when we conduct the Sim2Real task?
Yeah. You should definitely ask Kushal, who's sitting right there, what he found most challenging. I think there were a few step changes from what I recall, right? Like one was exchanging the hardware. That made a huge difference, even in simulation, right? Like the other is exchanging the RL algorithm, like from PPO to SAPG. That I remember was also a step change. The other thing that is most challenging is the vision part. So I didn't mention this because of time limits, but actually for all these benchmarks that we used, we scaled up the benchmarks so that vision actually works with them, right? Like, so the objects are bigger than actually defined in the benchmark so that there isn't a majority occlusion on the benchmark, makes it easier. So I would say this is what comes to mind right now. And I think, right, like we also can't do deformable objects, for example, right? Like because we are doing everything in simulation, which for deformable objects is rather suboptimal. And so all of these things point also at this direction of learning from human videos, but it's not super clear how to actually marry these two directions. Yeah. Thank you.
Is Dr. Villalonga. She is a research scientist at Google DeepMind working on robotics manipulation. She earned a PhD at MIT. Her research focuses on developing
Great, that's good. That's great.
Hi everyone, thanks for inviting me. I'm a bit sick, so sorry for my voice, but I think we're gonna manage. So I'm here, I'm working at DeepMind. I've been at DeepMind for 3 years and a half. And I wanted to talk about how do we think about multi-finger dexterity at the scale, right? When we think about the scale, we think about how we're building these robots somewhere else. How do we make them in a way that we really want to believe they can help us a lot? And I think it's no surprise to this room to say that robotics is a big challenge. I would like to say that I think probably there's lots of things that we need to think when we think about the scale, robots being precise, being general, have lots of type of robots, and I would say want to get better. But one robot does a lot of things. And the important part here is that we are Google DeepMind. You probably guys know that we like to have lots of robots. We like to collect lots of data. One thing that you can think about is, well, if you get these capabilities, can you think about one model? We are not saying this is the way to go, by no means, but we are making an exercise which is, what if we had one model that actually is capable to be precise, safe. Large language models. Well, at Google, we have what we call Gemini. Maybe some of you have interacted with it. It is a large language model trained on a lot of data, as you all know these days. And our question was, what if we take this model, we fine-tune it with lots of robot data, how much can we get out of it? And again, we're going to go into the context of one checkpoint. And as you can imagine, this is not just one person, it's lots of person, right? We're trying to do things at the scale, and Google is massive. Google Robotics in comparison is small, but it's still a lot of people. So with that said, of course, the big grand question that everyone else is trying to solve is AGI. We are trying to ground this on the physical world, robots. How do we get them to be very capable? And we like to make these nice plots and say, hey, when we started working on this, on Gemini robotics, we managed to get some dexterity and some generality. And I would say this first work had no hands. I think hands are the coolest. Don't get me wrong. We're all here because of that. But parallel grippers give you a lot, and we need to give some credit to that. We've all been using grippers for a long time. And if you think about dexterity, there is a lot of things that you can do with just these platforms. And it's just a reminder, because I think, yes, we want to do hands because they will be so cool. We will be able to do so many things with them. And yet again, grippers, I think, will always come back and be like, hey, but this is reliable. This works. These people want to have an industry, and they still can do a lot of dexterity. So just to say, yeah, grippers can do a lot. Well, in this case, maybe not so useful, but you're going to end up having the head of a fox. If you like origami, this seems to be pretty cool. Yet again, no tactile, no forces, just the motion itself. There you go. Now, this is something that I was more surprised about. This is assembling a belt. That this is some challenge that NIST proposed, saying, hey, this is pretty cool, but it's probably also very hard. And it's very hard. If you try yourself, you're going to fail the first time. It's going to take you some attempts because you really need to push and squeeze. And of course, because now there is a video here, you can imagine that the robot manages just with grippers. So again, just to say that even those very industrial tasks, if you have enough data, high quality data, even with teleoperation, no one loves teleoperation, but teleoperation can work up to some extent. We love hands. Grippers can also work to some extent. And here you can get rid of that the robot manages. Again, sad to me, because I love tactile and force, nothing comes out of that. So teleoperation overall can do a lot. And now we're going to go back into the idea of one checkpoint. We're going to claim that we can do even more things. And this is where we are right now, but actually not right now, 2025, where we were able to do lots of things, one checkpoint, many robots. One of them is a humanoid. Is it the most capable humanoid? Not yet. The hands are still something that we are working on, but you can do things with it. And the important part is that we can actually touch on many axes. When you think about this one checkpoint that needs to do lots of things, I'm only going to talk about the multi-embodiment, because I know it seems hard to believe. And when I first heard people in my team saying, yes, multi-embodiment transfer is happening, it was like, but actually there is some of that. There is value. And I think that's also true when you think about other models in AI. There is transfers that do actually happen. This is great. I don't know if it's every time all this great, but you can definitely see it. Another one that we focus on in this paper is, well, wouldn't it be great if you collect some data with some robot and some other robot is able to do it, right? And I think hands are the coolest, but I think hands can still maybe learn from some grippers, right? And with some naive examples, I think you can see both transfers. So in this case, very simple, picking up a cube, we only collect the data, sorry about the noise, with a humanoid, but surprise, surprise, the other grippers can do the task. This is very simple, pick and place, but it means that probably we can reduce a bit the complexity and the amount of data that we need to collect. This is on the other side. We're going to go from grippers into humanoids. And it's a bit of a more abstract task, because you're going to take this piece of cloth with your gripper and start to kind of clean the pier. Don't ask me why we're cleaning a big pier with a drum. That's beyond the question here. The point is that if you ask the humanoid to do the same, this is VLA, so this is language condition, say, hey, can you please brush the pier with your cloth? The model understands that it needs to do this, even though this idea of cloth and piers, it has never seen data for the humanoid. And again, we cannot share more work, so we are going to stop here for teleoperation. But I think there is something important to say, which is you can do a lot with teleoperation, and I think there is still lots more to come. But there is also a clear bottleneck. It's just that the teleoperation does not scale, and we really need to scale, right, to get what we want. And there is lots of issues. Some of them include, well, it's expensive to collect data. Like you need robots, you need operators. And as Jeannette was just saying, it takes a lot of skill to do any of this. I'm very bad at it. The quality is very bounded by how good are your skills. If I collect data, very bad. If someone is very skilled, very good, but it's bounded still. And of course, for hands, teleoperation with hands is possible. Don't get me wrong, but it's hard. It's harder than with grippers. So with that said, I wanted to give an example of how I think we can frame up this problem, which is, I think humans would open these airbots like this. Very simple natural motions. If you were to teleop, you would be more scripted, trying to be very visible, because again, you only have cameras, so better make sure that your cameras see everything. I think there are probably other ways that are better, right? Maybe less humans, but definitely very good. And I think, how do we get there is a big question, right? We don't want to be as good as humans, but at some point we want to go beyond. And of course, the clear answer is reinforcement learning. You are now able to surpass the teleoperation. But what we are able to collect with teleoperation are kind of classical approaches. I would say the modular is what I did a lot of my PhD, but we all know that the struggle is more to scale. So with that said, I'm going to present some of the work that we did in 25, which is ExoStar and DemoStar. Some links here, if people is curious for the websites. The goal is clear to me, which is we want a solution that is simple and scales. We're going to be using simulation. We want to find this kind of optimals, and let's not get into what optimal means, but optimal and transferable behaviors for real robots, and of course for hands, because we just discussed that hands is something that is hard to scale with teleoperation. We want to get kind of better. And we are going to get kind of better with this hand, which is 3 fingers. 3 fingers is the way to go? Probably not. If you ever try to use only 3 fingers, it's very hard. But that's the robot that we had at that time. So we are making it work. And I think it's pretty cool, honestly. But yeah, 3 fingers. So how do we go about that? So we built an exoskeleton that is kinematically equivalent to the robot. And it allows us then to kind of capture the expressiveness of your hands. You sense your world, you use it to manipulate. And that's something that even if you're using an exoskeleton, you're still able to do. And this is what we're going to see, like in this kind of 0-shot transfer, because we're going to go into simulation. So I'm going to go with steps into how this works. So the first thing is that you collect demonstrations with this human glove. How many? Little. 1, 10. We don't want to spend a lot of time collecting demonstrations. And the way we're actually able to get that is because this is kinematical double. So the data that we get is pretty good. You're going to see April tags, of course, because we're definitely collecting some of the pose. I mean, this is well studied. There is no reason we're not using April tags if it serves your purpose. In this case, is it going to scale up to some point? Because we also need to put them into object and cubes. But pose estimation, as we're just discussing, can get you there if you want. But yeah. And then finally, just collect these demonstrations, which then we're able to bring into the simulation because we're able to record, again, the schematic trajectories of hands and object. So once you have this, it's great, but it's not so great because if you look very closely, that finger down there on the red thing is inside the cube. Nothing is perfect. So what you need next is to actually clean a bit, in a way, your demonstrations. And for that, what we do is we actually drawing this through Mujoko. Mujoko is something that we have in-house with very simple cost functions like don't penetrate the object. You can actually bring these demonstrations to be dynamically feasible with something that we call MJPC, which is actually open to the public so anyone can use. So now that no fingers go inside the cube, and this seems reasonable, again, we don't need that many to start RL on top of this. And for that, we're going to use DemoStar, and I'm going to go a bit into the what is DemoStar, because I'm very insisting into the fact that we want to be scalable. And for that, we're going to have to use sparse rewards, because we all know that reward engineering used to be a thing, and it's painful. And we're also going to have few demonstrations, because if we have to collect thousands of demonstrations, even hundreds, that's again not going to be very scalable. So with that, yeah, much more scalable. This is kind of the sort of things that we have been very surprised, which is that we had better methods now with the exoskeleton, but at first we just had this kind of very simple device for teleoperation. And we went into Sim and collected this crappy, because it's pretty bad demonstration. Then it's a sped up data, but it basically took us a minute because again, I'm very bad. And with this just kind of thing, teleoperating a hand is hard. But then what we're gonna learn is policies that are much more optimized. You go from 1 minute demonstration, more than that is pretty bad, as you can see, into 4-second policy. And this is gonna transfer to real. So again, but we're using binary sparse rewards, which are success detectors. This is kind of easy to code, but then you get this. No, 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 yes. So how do you learn from that? We need to find a way to explore. And the way we do that is by what we call informative states. We're gonna reset our simulation to states that we call informative. So what does that mean? Let's say you reset your simulation to one of these states. The task is connector insertion. You take a connector with your hand and you insert it into a plug. So in the first state, let's say that your policy is already able to succeed all the time. It's able to just kind of be on top of the connector and just kind of plug it in. Then we're going to say, okay, this is too easy, not much to learn, you already know how to do it. But what about the one at the bottom where actually the object is on the floor? So then where you actually can try to roll out your policy and you're going to fail maybe every single time. There's nothing to learn, your policy is not good. What we found is that there is lots of, not lots, but there is a decent set of states that are what we call informative, where your policy will fail sometimes, will succeed other times. And those are very useful because these are kind of at the Pareto frontier of your knowledge. So what you can do now is you can find these informative states, and then if a state is not informative, you don't put it through the policy. But if it is, then what you can do is sample a lot of examples, so that you kind of get this kind of behavior you're almost about to really master, and put it into the replay buffer, and then this goes into the learner for you to do RL. So very quickly, as a recap of DemoStar, you are basically going to use these initial states. You're gonna reset your initial states, sometimes from these informative states, an auto curriculum is going to emerge. This is something very cool because it means that you are able to find what are the states worth learning. If you think about domain randomization, you also find which are the parameters that you are kind of capable to learn. So a curriculum emerges in many dimensions, and I'm going to explain more about that. And then what you have to use is something very simple like MPO with the SPAR rewards. So let me go into the curriculum because that's something very cool that we found. It just emerges naturally. We are not scripting any of this. It just happens naturally from the algorithm. And this is the task. It's very simple. Again, don't ask me why this task. You have a cup and a screwdriver inside, but that's the task that we decided for. And in order to explain, we're going to have these two axes. On the X is policy updates, so how much you are into learning. And on the Y-axis, this is where you are in your demonstration. Again, we're using very few. From 1 to 10 demonstrations usually is plenty. At the top, you mean you're almost done. The demonstration has almost finished. And now, what is the progression of informatives that you're looking at? Well, at the beginning, where you're learning, you're going to see stages from the end of the demonstration, where the task is almost solved. Like in this case, it would just be release the screwdriver into the cup. But as learning evolves, you're going to go from kind of easy to hard states. Again, this is something that just comes out naturally. So it's very informative. Like if you really want to understand what's something hard in your policy, you go into this, you see what are the informative states, and you learn a lot. So overtraining, the informative states keep on evolving and go into the beginning of the demonstration. Like for instance, at the end, you're just basically at a reset state of initial conditions. So once you have this, again, you can apply to many tasks, and you get this, that with very little demos, you get this kind of very optimized behaviors with hands. And now finally, on the scene to real transfer, the TLDR is the thing kind of works zero shot, which was surprising. So here you can see both the policy in sim and in real, and you can see these very fast behaviors. Like if you think about this threading, if you don't mind me playing again, it's pretty fast, right? I think at first it tries to understand what it is, and then it just goes, right? So it's nice to have. Here we have a few more tasks, like inserting a key. This is cube orientation, which works really well. It turns out to be pretty simple, even with 3 hands. If you try, it's not that easy, but it's definitely doable. This is one of my favorites, where you kind of use one finger to stabilize, and then you put it inside. Again, this is just coming from RL, so we don't tune these behaviors. They're just kind of coming from the demonstrations. And then finally, just a few more. You have already seen this one. This is just balancing, and the one that you already saw at the beginning. So I think that's a way to think differently about how do you scale manipulation when you are thinking about hands in a way that is less restrictive than teleoperation. So with that said, I'm going to thank everyone for being here. I will say there's lots of things to do. I think hands is definitely the way we want to go. There's lots of things that we cannot do without, like power graphs. Some of the hard manipulations, they take time. We haven't been able to show you everything, so looking forward to next year where we're going to show you 26 probably. I still think hands are the coolest, and I just want to say, if you think so too, please let me know, because we are hiring, and we definitely think that's a lot of things that we need to do. So with that, thanks everyone. Happy to take any questions.
All right, thanks for the talk. A lot of interesting things in there. I'm very curious about the exoskeleton for the next game, the one that's on one-on-one kinematic component. So do you use it to do force feedback, joint level, torque feedback to the operator? How important have you found this? Can you talk a little bit more about that?
So this was a project that was led by a student researcher, by 2 of them, Zilin and Tony. So in that case, we didn't involve all the big machinery of operators. If this would just be Zilin, she would put on, she would record 1 or 2 demonstrations up to 10, as I said, and that would be plenty. So there wasn't a lot of engineering. There was also just encoders that would basically measure the positions of each of the joints in the exoskeleton. And then because you're moving this into simulation, even if there is some noise in your recordings, you're able to kind of make the trajectory dynamically feasible. So it was very low effort and kind of cheap in a way, because you would just go put the exoskeleton on, collect a few demonstrations, and move on. Honestly, the reason why there are no more tasks is because our student researcher just was done for the internship. She's coming back, so that makes me very excited. But that was kind of the stand we had to go with this.
Thank you very much for your presentation. It's very interesting. As you kind of demonstrated, you need some idea of what the reward function is going to be, so you kind of need to be working on tasks in sim. And I'm curious, do you think that for kind of training these larger, more general models to do specific things, do you want to start by having a really large set of kind of randomly set tasks in sim and doing massive training, or picking like tasks in the domain that you want to do, and then building digital twins of them and training on those specifically?
That's a great question. I would say the answer is both, in the sense that, and actually it's both and beyond. So thanks a lot for the question. I would say we've been exploring teleoperation because the recipe data kind of works and you can get very far away with it. We have also been using sim as a way to eval our models. When you're running things at this scale, you cannot just say, oh, I'm going to try this model on 200 tasks. Oh, it's very bad. Let me try again. So sim is a really nice way for you to understand better the capabilities of your model. So that's also very important. There is a place where the more tasks you have, the more information you're gathering, generalization, instruction following, all these questions can be definitely answered in simulation. But there is one more than that, right? And is how do you kind of capture the intuitive physics that you definitely have in your simulator for your model to really be very good at it? And as you were saying, yes, I think you can have a very wide range of tasks that you can learn from, merges with data that comes from real and get the best out of both worlds. So that's something that we are definitely interested in looking into. But there is also the point that for some tasks like these ones, if your physics are good, which that's a question, that's something that you might require some work, you can also try to go very deep and say, how far can I go with sim? My hunch here is that sim is about getting the substrate, but the substrate doesn't have to be very basic behaviors. It can keep growing as you get confident that you really understand the nuances that come with sim. I would say sim, one of the issues that you will find, even we own Mujoko find, is that authoring new tasks, making sure that the physics are right, that's easier said. It takes longer to scale, but once you get a crack on this, then things go very fast. Actually, in this work, as we were saying, collecting demos was trivial. We just 3D print some objects, put the glove on, collect the demonstrations, you're done. No, you're not. Now you need to go into the physics, into the simulator, and replicate the task. And that was more painful than it seemed, and that was kind of one of the bottlenecks I had, just replicating the scene. Then learning was trivial again. So food for thought there, but definitely for hands, there is a big opportunity coming from sim.
Thank you.
Yeah, and share.
Yes, share your slides.
Oh, can't.
It's fine. It's fine.
Okay, cool.
We'll just record over there.
Okay.
Okay, welcome, Professor Lepora.
Okay. So thank you for the invite. Very happy to be here. So Dexterity Tactile Hands. These are some of the videos from my lab. So basically, we like to make tactile sensors ourselves, 3D print them. We like to integrate them into robots, and then we like those robots to do stuff, manipulation or interaction with the real world. So to set the scene, I put a lot of effort into writing a single author review paper in ICRA on tactile robotics. So I'm going to quickly skip through a bit of that just to set the scene. I do have a complete talk on it, if anybody wants to invite me to talk about this review paper. So the kind of hallmark of the paper is study the past if you would define the future. So I go right back to the beginnings of our field to track, to get some insight into where we're going and where we should go. So quick back to the 1960s. I'll just quickly mention, so the dawn of tactile robotics, as Marvin Minsky, also the dawn of AI. He was originally trying to create a hand, arm, eye system with tactile, but it was basically impossible in the 1960s. So we gave up and did it in simulation, but kind of did these idealized models of it, which influenced a lot of his later AI work. Also want to point out that vision-based tactile sensing, which is obviously a big thing now, with digital cameras, was being done in the 1980s in Wales, in the UK. Yeah. So in particular, high-resolution images. Yeah, you see at the bottom right, sort of similar to the kind of gel site levels, but I say in the mid 1980s. Moving more to the kind of last period, like 2010, which I kind of pick out in the paper. So there's kind of 5 areas, and in relation to this workshop and this talk, I'm going to pick out 3 of the areas. One is there's been a huge amount of activity in putting tactile sensors in the hands. Obviously, there's been a large acceleration there. And it's only now that we're actually getting those hands to do interesting dexterous tasks. But for a long while, people were, trying to do that. Vision-based tactile sensing, it's a big thing, obviously. Gel site, Tactile as well. Same year, the gel site is invented, 2009. And then soft and biometric. Softness is critical as well for dexterity. If you have a rigid tactile sensor, it's difficult to do manipulation with that, as all of you people who are using gel sites know. Yeah. What's the consequence of these trends, recent trends? One, there's as many different types, there's new vision-based tactile sensors appearing every day. There's various lineages, there's proliferation of those technologies. Take your pick. Now, the other one is that there's a step change in tactile dexterity. Basically, that's happened in the last few years. That came from those 3 areas coming together. But now you're finally getting kind of human-like levels of tactile dexterity, or near human-like levels, are becoming emergent, and the field is rapidly accelerating as well. Okay, so on to my lab's work. So I kind of like to make things hard for myself, because for our lab, because as well as doing the tactile dexterity, reinforcement learning, deep learning, so on, and building tactile sensors, I'd like to build the hands as well. I want to do the full stack tactile robotics. Yeah. So it's tricky, but it means that you have control over the entire, stack to do dexterity. So this is, if you like, our history. Started about 2016. Started working with Yale, Grab Lab hands. Then we started working with commercial partners like Shadow. Stopped working with some commercial partners. Collaborated with Pisa, and we've had various versions of their hands since. Had a diversion into soft robotics, pneumatic actuation, which I gave up. That's too hard. Technology is too preliminary. And then recently we've been working with Allegra hand and the Leap, which I'll report upon. So first I'll start off with underactuated tactile hands. So here's the motivation. So the Piezo IoT hand, QB robotics hand on the left, anthropomorphic, Shadow robotic hand on the right. The famous OpenAI in-hand manipulation demo. Okay, both look highly dexterous, both look human-like. Hand on the left has 1 motor and it's cheap. Hand on the right has 24 motors and a massive 4, and it's very expensive. So it's just full actuation isn't necessarily, at the moment it's a way forward, it's working, but makes expensive hands difficult to make. There's a lot to be said in the morphology of the hand. You can get a lot out of it. So we started working with Piezo IT. They gave us one of their hands, and then we integrated a fingertip-style vision-based tactile sensors into that. Yeah, and then there's 1 motor. There's not a lot you can do with a 1-motor hand, apart from hold things tighter or looser, which is what we did. It helps with pouring and so on. But another thing you can do is that once that hand is installed on a robot arm, you've got another 6 degrees of freedom of the arm. So you can use the tactile sensing in an underactuated hand to control the arm it's attached to as well. So that is important, I think, because it's not just the hand you're controlling, it's the arm and the body that it's attached to. Okay, and then so I like making the hands themselves. So a very talented PhD student, Haran, who made a 3D printed version of the Piezo IT hand. Because we could print it ourselves, we added the next most important motor to it, which I feel was the agonist. So you have an agonist to close it. We add an antagonist to open the hand. And the 2 of those can work in antagonism, can work together, and that can do things like variable compliance with that. Very important to have agonist and antagonist motions if you've got tendon-driven hands. Transform the capabilities of the hand. And the other thing we did is we integrated our vision-based tactile fingertip into this 3D printed hand. The development, how we drove that forward is everything apart from the camera is 3D printed. The gel, the skin, the markers, the rest of the finger that goes around it, the rigid thing that holds the gel, everything is 3D printed in one piece. Zero human assembly. Yeah? And that's the design of it there. And then, we integrate all that together and we have a 3D printed tactile hand that can do lots of things. My son built a Lego hand after chatting with Haran. So I'm into like open access, making stuff easy to make. My son built a Lego hand and we published it in IROS last year. So my 16-year-old son gave a presentation at IROS, which is brilliant. It opens up, on a serious level, we've got to engage the next generation in building hands. It's important. They're the people who are going to be taking this forward. So we had lots of fun. There's some holiday pics. And then this is the most recent one, which is just about to be submitted. So we've taken that forwards. It's more anthropomorphic, more human-like in scale, 3D printed tactile fingertips, more motors, more actuators. Yep. Okay. So next, how long have I got? I've got till how long? 10 minutes, is it? Another 10 minutes. Cool. So I'm going to move to fully actuated hands as well. At the moment, I don't know whether well, I do think in the end, under-actuated hands are the way to go, because it's going to mean that you're going to get cheaper, more dexterous, more human-like hands. Yeah. At this moment in time, obviously, fully actuated hands are popular because you can train your RL policy with them. You've got complete control of the hand. It's easier to get a fully actuated hand to do your control. It's like basically having lots of little robot arms on the end of your hand. I'll say long term, I do feel that the under-actuated hands, being clever about the design of the hand, will make cheaper, more robust, more intelligent hands. But I say at the moment, I think it's important to have a foot in both camps. So we do fully actuated hands as well, for basically doing deep RL, tactile sim-to-real research. So taking a step back, so this was a pivotal moment in the field when OpenAI did this with a shadow hand back in 2018, 2019. But of course, the way that they solved it was they had no tactile sensing and they had all these cameras. Yeah, about 20 cameras. And lots of GPUs, lots of money, lots of people working on this. That's not scalable. They sacked the team. They gave Isaac Jim away. I mean, NVIDIA was working with Isaac Jim for OpenAI at the time, gave that away. And then they pivoted to ChatGPT. Arguably the right thing to do. But since then, that's left a gap where, I mean, the way they did it wasn't scalable. All those cameras, it's not going to scale. So now it's recently, we're getting tactile. We've only just now gone past that level of OpenAI dexterity, but using tactile sensing in the hand and using vision-based tactile sensors. So the cameras have moved inside the fingertips. Okay. Now, in terms of our own work, we found there's a lot of labs doing deep RL, tactile for hand. In terms of our own work, House's work was very influential for us. We took the open sourced code for doing the sim-to-real proprioceptive, so no tactile, no vision, sim-to-real proprioceptive. He open sourced code. We used that code ourselves to do tactile and build upon. Hasn't open sourced the code yet for the tactile one, but we did our work independently of that. But just to draw attention, the way they do it, they're kind of balancing the object in their hand. There's one single orientation, and they did dimensionally reduce the tactile signal to basically an 8-bit, 8 ones and zeros. So we wanted to do tactile, building on House's policies with the proprioception, using our tactile sensors. Need to do more than that to get a paper. So we felt Matt, very talented PhD student, felt the way forward, a teacher, student, etc. for the learning, was we would do any rotate, which is basically to do gravity invariant in hand rotation. And that means you have to be able to hold the object stably as well as manipulate the object in the hand. So you see there's a much more stable grasp on the object. You can't balance the object on the fingertips, you have to hold it. So that was great. That worked. It rotates around any axis, pretty much any object that can fit in the hand. It works for. Great. So how are we taking forward? So some new work. Well, this is work from last year. So first thing we did, Harry, rather than have a year, a human spends a year tuning reward function to get policy to work, he designed an LLM to tune the reward function and spent 6 months designing the LLM to do it. But using an LLM to design a reward function in simulation comes out with both better reward functions in that the policy is more accurate, it's more robust, and also comes out with simpler reward functions than the human came up with. So great. But basically the same sort of policy, but it's a bit more accurate. Now some new work. So I like making hands ourselves in our own lab. So the leap hand fits with Allegro hand. It's very similar morphology. So we've moved now to using the leap hand instead of the Allegro hand. So this is basically using any rotate on the leap hand. And you want to do more than that. You don't want to just, what we did is we designed a new type of leap hand with a different morphology and compared that with it. And kind of a non-anthropomorphic and a non-anthropomorphic leap hand. And then kind of used any rotate as a way to compare the dexterous handling capabilities of the two hands. Yep. So that work is just about to be submitted. Basically, most of that, given a good policy, most of the hands are fairly dexterous and do the tasks. We found a non-anthropomorphic hand was actually better for in-hand manipulation. But there's other tasks to try. There's a lot to explore in this area. Most recent work, Vitac again, just in submission. So we brought in now vision into the policy too. So it's proprioception plus tactile plus vision. Change the task that what you're trying to do is rather than rotate around on the axis, you're trying to move the object to a desired pose, which is closer to true manipulation. Manipulation is controlling an object's pose in the hand. So you use vision, touch, and proprioception to move the object to a desired pose, and then you can flexibly keep moving that object around that pose. So that's a bit like the OpenAI, that you can give an image of the object to move to. You can also give a pose and a point cloud as well. That works. We do it gravity invariance as well. Messages to take from this. How long have I got? I've got about 2 or 3 minutes. Yeah. Messages to take from this. We found that tactile and vision plus tactile plus proprioception and vision and proprioception worked about the same. Yeah. I know in other work, like say houses work, they found that tactile is just adding a little bit onto vision. Here we're making a lot more out of tactile in the policy. Yeah, there's a lot more information that's coming out of tactile and policy. So we found that vision and tactile were closer. What we found is that vision allowed you to move the object faster. If you've got vision and proprioception, they can move the object faster, but it would drop the object more often. Whereas tactile wasn't as fast, but it was more robust in holding the object, which kind of makes sense. And then you put the both together, and you can move the object fast, and you can hold it robustly. That's kind of the takeaway message from this work. Yeah. I'm going to advertise Tactile Lab. So basically, we're bringing together a lot of the work I was showing you before in Sim to Real, brought up, bringing to Yijong Vaughan has brought the work together in Isaac Labs, upgraded it to Isaac Labs. A lot of the other work was in Isaac Gym. But work in Isaac Labs, got it sensing shear with rigid body simulations. It's got it doing the kind of tasks that we've been publishing in our group for years. Brought it all together as Tactile Labs. We're going to open source it and basically give away all the stuff that we, all the kind of knowledge and expertise that we've been building up over 5 years or so in the lab. Excellent piece of software. I think it's in the next month or two. It's imminently about to be open source. In relation to that, obviously to use some of the demos with it, you need our type of tactile sensor, although it will work with other things like a digit or gel site. Except I don't know how well they would do manipulation because they're very, very stiff sensors, and our sensor is very soft, and that helps it do the manipulation. So potentially we could start selling tactile sensors for cheap. $50 or something like that for each of the fingertips that goes on a leap hand or an Allegra hand. This is something I'm considering. More as just as a way of getting the technology out there for people to use. Yeah, rather than making money. I don't think there's much money at the moment to be made from just selling tactile stuff. But actually, there's a lot of value in enabling other people to do research and build on what you've been putting a lot of effort into. That's the motivation. In addition, I'm hiring as well, postdoc for ARIA. Like everybody, we're a postdoc down at the moment, and so we're looking for somebody to join our team. Thank you very much.
Thanks a lot for great talk.
Before presentation, visual technical sensor can be used to solve a lot of problems and like object derivation, page turning, or phone scrolling. But I take Joseph as an example. It's very difficult to make it smaller. So do you think it can be solved in the future?
2020, we had a fingertip-sized vision-based tactile. So it's still possible to make the technology. 5 years ago, we were making the tactile sensors that you can't really make them into a skin, but for a fingertip, you can. It's quite easy. And the trick is, you use a smaller camera.
I think it's because the difference between the focal distance.
That's a lens. There are solutions where you don't need lenses. People have done that. Use ingenuity. But basically, a small camera with a wide-angle lens. Tiny. We've got Moore's law happening for cameras. What cameras we bought in 5 years ago cost us £1,000 each, but now they're costing a few dollars. We actually haven't been able to buy ones as small as the ones we bought 5 years ago, but that's another question. Anyway, yeah, small cameras.
Thanks a lot. We move to the next spotlight station. So please, the authors for the spotlight.
Thank you. I'll see you. See you later. Rika, somebody say it.
Jeannette's going to come down, but
I'll sit on my seat then.
You also sit here if you want.
Good. Oh, thank you.
1 second. Yeah.
Hi everyone, I'm Kushal and today I'm going to be presenting Simple Real. Our advisor Jeannette gave a presentation before. I'm going to give some additional details. But first, I really want to ask the question, why tool use? Why study tool use? Because I think that's the way humans interact with the physical world. And why do research on this? I think it's a very hard problem. It requires you to grasp this thin handle from tabletop surface, do this in hand rotation, and of course, do the final tool use motion. And in this project, we were not just motivated to do one tool use or one task. It would be really cool if we could do multiple tasks, all ranging from using a razor on the top left, brushes, hammers, and move them across different trajectories. And what would be especially cool is if a single policy was able to solve these tasks zero-shot. So how do we create structure in such an unbounded problem? Well, I would consider 3 tool use tasks first. These require different skills. For example, in hand rotation in the first example, object spinning in the second one, or let's say you maintaining a stable grasp while there's some interaction with the world. The question we ask in this work is, can we unify the learning of all these skills under a single objective. And our answer to this single objective was pose reaching. If our policy gets really good at reaching random goal positions with different objects, any tool use task is a special case of random goal post reaching. And here the special case is moving it up, doing rotation, moving forward. But that's not how we train it. We train it on random objects, which are procedurally generated, random goals, which are not the same as the previous slide, and the same policy through massive parallel RL. We can solve this across different tasks, different objects, and spend a lot of compute getting very good at this objective. After we got good at this objective, now everything at test time is a special case of this objective. We get a sequence of goal poses from the human video, specifying how you should move the brush. And yeah, you can basically execute that closed loop, giving the robot different goals. Every time it hits a goal, we give the second one. And you can kind of track the tool use trajectory till the end. So what was really cool about this project was, we trained this policy once. Traditionally, sim2real is hard. It's difficult to scale to a lot of objects and a lot of tasks. Because it's a shared policy backbone, this just required PhD student hours to do all these tasks. And in terms of results, the things I really like are the high dimensional control of this problem. We tackled both the hand plus arm motion, multiple contact switches across all tasks. And the favorite thing for me is the fast speed. It's moving 1x, 60 hertz control, really making it evident why you need a dexterous hand for these tasks. Okay, policy isn't perfect. There's, of course, failures. But one thing that we often see is these failures are very lifelike. It makes failures, but it chases after it. Cannot get the rotation, but keeps trying. And this behavior is really seen in the last example. It'll just chase the marker till it drops off the table. At this point, we have to put the e-stop, but it's really cool to see this. And one more example where we didn't have to put the e-stop. It picks up the hammer, falls down. It's very chaotic motion. In one sense, you might say it's not super controlled, but I think that is what manipulation is about. Being able to structure the chaos and the noise and complete the task. So thank you for listening to the presentation. We'll have a poster, and here's our project page.
Hello, everybody. My name is Steven, and I'd like to present our workshop paper on human dexterity through a dual surface tactile fingertip. Here, we're exploring how having both fingernail and finger pad on a fingertip level really helps and help robots to achieve human level dexterity. So the argument here is that in a task like this, where the human, that's me, but we are trying to pick up a very thin layer of card. You can see that the thin layer of card is very hard actually to be seen by camera. So here, a fingernail is very important to be able to pick the card up. And when you want to maybe transfer the card to a different place, you switch the grip, you switch it to a pinching posture in which you engage the finger pad to actually hold very tightly onto the card. So in this scenario, both the fingernail and the finger pad are very important on a hardware level. The existence of both elements unlock this kind of tasks. On top of that, on a sensory level, having tactile information on both the fingernail and the finger pad is equally important. And we think that this kind of dual surface tactile sensing remains underexplored for dexterous manipulation. So in a collaboration between Waseda University in Tokyo and Zero Robotics, so Zero Robotics produced a sensor that combines both a sensorized fingernail and a sensorized finger pad. Without giving too much away, just to take a look at what the fingernail is able to do, you can see that if I'm tapping onto the fingernail from three very kind of meaningful direction, from the backside, from the inside, and from underneath. It gives distinctive signals that are both high quality and useful for downstream tasks. So what we can do is then feed these very high quality signal into a behavior cloning policy to do some dexterous manipulation tasks. And here are some of our results that we were able to achieve. One of my favorite tasks is actually the top left, in which the hand squeezes inside a shelf of binders using fingernails and uses finger pad to securely grasp the binder out. And in the second task, the thin piece of paper is incredibly difficult to actually be picked up. If you're using a gripper, that's probably impossible. So using a fingernail, especially with the rich tactile information, we're able to do these kind of very fine-grained dexterous manipulation tasks. We also found that having both finger pad and fingernail tactile signals together in the policy really improves the performance. If you just feed in the finger pad only versus fingernail only, it doesn't perform as well as having both of these modalities available in the dexterous policy. Just to showcase this example in which we're picking up a very thin piece of card and flipping it over, having both available is able to help the robot hand achieve the task much more successfully compared to feeding only fingernail or only finger pad, in which you can see that in the case where we're only feeding finger pad, we see more of these failure modes in which the card is not being securely kind of picked up by the fingernail. On the other hand, if you're only feeding in fingernail information, the grasp becomes less secure. So having both fingernail and finger pad really unlocks a lot of the tasks and a lot of robots to do many of the tasks that humans can do. And we think this is the way to go for a future robotics fingertip designs. Thank you very much.
Yes, sir. Hello, I'm Pasquale Marra, and I'm going to present my work on multi-fingered force-over control for humanoid robots. So our idea is to understand how we should move the upper body from the torso to the fingertips to balance an object of unknown mass, leveraging the concept of center of pressure. So first of all, we use these fingertips, Xella fingertips, and to collect data, we use multiple indenters and these omega sensors. And then we have ground truth forces with the Nano 1780 sensor. We collect that on 5 fingertips, and we also integrate the sensors with other data collected directly on the end of the robot to mitigate the effect of gravity, which was affecting our force estimation. And we also characterize the variability between fingertips. So about the control. First of all, we define a virtual plane on which we project the fingertips position. And then from this information, given the forces estimated at the fingertips, we estimate the center of pressure. The idea is to make the center of pressure sliding toward the center of this virtual plane. And then we solve a QP in which we have this main component, one that controls the fingertips on the plane, and another one that controls the centroids toward this center of the plane. And in the end, we also add this contribution to compensate for model inaccuracies. Then we send it to the robot. And here we can see one test at 50 Hertz. You can see that the robot is eventually successful, but the object, before going to the target position, goes back and forth quite a lot. While in this case, we increment the frequency at 100 Hertz, so you can see that the robot is more reactive. Thank you.
Hello, my name is Yafo. I'll be presenting our work beyond the binary, sim-to-real dexterous manipulation with physics-aware contact representation. So in this work, we use a novel contact representation that achieves effective sim-to-real transfer of tactile-informed dexterous manipulation tasks. And here, the key challenge that we're trying to solve is like how we can balance the trade-off between sim-to-real transferability and the information richness of the contact representation. So the COP, or center of pressure representation, consists of a single force vector, so three-dimensional force vector, kind of as a coarse approximation of the overall external contacts, and a single three-dimensional coordinate of the centroidal contact points, both expressed in some sensor frame. And for the Zilla tactile sensors, which we use in our work, each fingertip is covered in a sensor array, where each taxel of the array is an individual sensing point that provides 3-axis force measurements. We also derive a bidirectional and differentiable taxel COP mapping, so allowing us to convert between the COP force representation and the taxel forces. So specifically for a force vector, we first decompose it into the shear and normal components. Then we account for the internal stress propagation due to the surface deformation of the sensor cover, and calculate the effective taxel forces resulting from both the normal and the shear components. And then we can combine the components to obtain the resulting taxel forces. So this allows us to convert between the COP force and the taxel forces. We also propose a novel sensor calibration method via differentiable dynamics. So most existing works calibrate sensors via data collection of using some force torque sensor. So in our case, we actually don't need that. We simply only record the taxel forces and the joint torques and positions. And instead, we leverage the differentiability or the differentiable taxel COP mapping and the wrench space dynamics of the finger of the robot hand. So more details are in the paper. And for example, this allows us to learn the taxel orientations in a supervised way as a regression problem. So in terms of the zero-shot sim-to-real transfer results, we see that the COP condition policy outperforms the baselines, notably including the binary contact condition baseline and also the raw taxel reading baseline and some other self-ablations. And we also analyze what is learned by the latent state of our COP condition, the recurrent policy, so the output of the recurrent unit here. And for example, we see that through linear probing, we can actually predict the object state from this latent state. So both its position and velocity. And it can also implicitly capture physical object properties such as its mass. Yeah, so please check out our paper, video, and website. Thank you.
Now we have also 2 industry spotlights. The first one is on G-Hunt.
Hello, I'm the founder and CEO of Fuji Technology. My name is Rika. So I think you probably have heard us. And today we're launching our 2nd generation Dexterous hand, which is a major upgrade from our 1st generation. So I'm just gonna play this video. I think the Chinese version is already online, but the English version, this is the first one we present this. Okay, I think because I have very limited time, so I'm just going to summarize the major updates from our first generation. So first of all, it's very practicable, super good for IL senatorial policies training, and we have already tested that. And second is that it is way more robust. I think it's very good for industrial use and durable and harsh environment. And the third major upgrade is that we are adding fingertip tactile sensor, and it gives you very rich information. It's just like you have a 6-key tactile sensing, so you'll get the shear force and the 3D force very vividly. Yeah, and that's pretty much it. And we have a booth in this exhibition, so feel free to visit our booth. We have live demos, and we also have some RL policies rolling out. And this is my personal WeChat and also my mailbox. If you're interested, you can go to the website and hit me email. And also we're hiring. We have offices in Shenzhen, Beijing, and San Francisco. So that's pretty much it. Thank you for your attention.
Thank you. So the last one is Sharpa.
Good afternoon, everyone. I am Yun-Sung from Sherpa. Very excited to be here to share our perspective on dexterous manipulation. So from Sherpa, we started from a very simple question. We want to make robots truly useful, provide productivity to humans. So what is the most scalable path to that? Our answer is surprisingly simple, just to learn from humans. So the world has been built around us for human hands, especially for manipulation tasks. All the tools, the workflow, environment are sort of designed for 5-fingered hand. So when we are thinking of building the added factor for general purpose robots, trying to have a hand similar to human, same dexterity, same size, 5 fingers, is not just like a spec decision. It's more like we're taking advantage from learning from human demonstrations and also to take advantage of human scale data. So that is the first very crucial factor we recommend for Sherpa. Of course, having a 5-fingered hand is not enough. So the second thing very important is tactile sensing. We value tactile sensing a lot. Imagine picking up very fragile things like chips, slippery fruits, turning a pitch. Tactile sensing is always there to close the loop. You cannot possibly do this kind of task without it. So in Sherpa, we have optical-based sensors at each of the fingertips. So there are more than 1,000 pixels for sensing. The resolution is less than 1 millimeter. With that, the robot can have the finest sensing of the environment. So it can do things like we're showing here, peeling the shell of an egg, or folding origami. And also, we have some work demo in ICRA this year, and you can also go to our website, check out some of the researchers we have done around the hands, around tactile sensing. Here I want to say one called TechMap. Basically, we're bridging a unified representation for zero-shot tactile dexterity. Of course, for optical sensors, there is another challenge for everyone, which is it's not so good at durability. I think that is also one thing that industry can do better than academia, because robots don't fail because they cannot do one good demo. They're failing because they cannot do it 100 times. They cannot do it in real world. So at Sherpa, we treat reliability very seriously. We have done millions of cycles for reliability tests before they go to our customer, and we want everyone who are using our hand in their lab, like Jeannette's group, we wanted to push the limits to these hands. When you do data collection using the hands, please do it 7 hours per day, every day per week. Sherpa hand can totally handle that. That said, having the durability, dexterity, tactile sensing is not everything we're building. We're not just building the best hand in the industry. So at Sherpa, we think a good manufacturing manipulation system is a key for this, for closing the loop for physical AI flywheel. Think about it, if you have very good hardware, then you can use it for collecting the highest quality data, and using this data, we can train the top tier AI model that can eventually be deployed to all kinds of use cases in real life, and then it can give us new ideas for iteration of hardware. So everything together can help us close the loop. It starts from the best hardware, and hardware is an element of this process. So we are not just building hands. We also have robots. We also have very good data collection devices. And Sherpa has a booth at 33 in ICRA this year. We welcome everyone, come to our booth, try our products, and see, give us any suggestions. We already have a lot of demonstrations shown. Previously, last year's ICRA, IROS, CES, our robots can do things like peeling the apple or assembling graphic cards, but we also really look forward to future progress that you guys are making. Right. So I think we all share the same mission of manufacturing time by making robots useful. We're excited to present all of these devices, but we're more eager to learn from everyone. What do you value most? Please come challenge our devices, tell us what you like, what you don't like, what you want to add to the robots, and we will make sure that to provide the best research years for the community. So again, the booth is number 33. My name is Rika Yang, so I'm the Director of Business Development at Sherpa. If you want to buy a pair of hands, or if you want to explore long-term partnership, please come to us. These are my personal WeChat and WhatsApp, and also my email. Please feel free to contact. Thank you.
Thank you. Now is the coffee and the toast station with each other quarter after 4.
Myself is and also share the slides. The video is optional. Oh, 1 second.
Hello, everyone.
But there's nobody on Zoom. Oh, this is just for recording.
Oh, okay. The last station. Please find your seats.
I should be able
Now
to
we have our last speaker, Professor Matei, psychologist. He is the Associate Professor of Mechanical Engineering at Columbia University. His main research is to build robots that can operate in new and post-enforcement situations, expressing intelligence through physical interaction with their environment. So we want to start now. So for the industry station and discussion, we can put a bit like after this, after the whole demo. So Matei was awarded the early career award by the Robotics and Automation Society, and also a Young Investigator award by the Office of Naval Research, and so on. So everyone, let's welcome Professor Ciocarlie.
All right, thanks a lot, everyone. It's a pleasure to be here. I'm going to talk today about work both from our lab at Columbia and our spin-off, Tangent Robotics. The shared theme is dexterity with tactile hands. So, to start off with a fundamental question,
I was thinking about the theme of this workshop, which reminded me of an old joke we used to have back in Romania, back in the day. How do you fit 4 elephants in a Trabant? And in case you don't know, the Trabant is this very small car, used to be very popular in Eastern Germany, in the Eastern Bloc, in Romania. So how do you fit 4 elephants in a Trabant? Well, 2 in the front, 2 in the back. I mean, how else could you possibly do it, right? What else is there? And it's kind of the same with tactile dexterity. How do you do dexterous manipulation with tactile multi-fingered hands? Well, reinforcement learning or imitation learning. I mean, that's it, right? What else is there? So that's kind of how I'm going to structure my talk. Of course, this is a little bit of an oversimplification. There are combinations of these 2, various recipes, but this is a lot of where we have derived value as a field over the last couple of years. So I'm going to start with the first one here, with reinforcement learning. Before I get to the actual policies, just brief mention of the sensors themselves. I'm not going to go too much in detail about the sensors. We gave a talk, Sharfin, Eric, myself, we gave a talk at the VTalk workshop this morning where we showed some live demos. There are 2 tactile sensors that the work here relies on. One of them we call the popcorn FT sensor. The sensor is just sitting here at the base of the fingertip. Everything above the sensor is essentially just a blank, and it's a displacement sensor that you can pretty much think of as the equivalent of a force torque sensor sitting at the base of the fingertip. And this form factor, we think, has some really neat advantages in terms of ease of integration, in terms of the whole fingertip essentially being sensorized, right? Any contact anywhere on the fingertip is going to create a displacement on essentially a signal in the sensor. So this is what it looks like. This is an older version of the sensor where we used PDMS between the top plate and the bottom plate, but it gives you a sense of the intended behavior, right? So you get the resultant wrench acting on the fingertip regardless of what contact happens. And you get very nice sensitivity. It also adds a little bit of compliance in cities with your fingertip, which is really nice. So this is the sensor itself. On Friday at the RoboTac workshop, I'm going to talk more about how we manufacture it. And here is the same sensor integrated into a 4-fingered non-anthropomorphic robot hand. Kinematically, I think similar to the non-anthropomorphic leap that Nathan was talking about. And much like Nathan's lab, we are also always excited about going full stack, building the sensors, integrating them into hands. And what you're seeing there on the left is just a good old reinforcement learning policy trained in sim and then transferred via sim to real with domain randomization to the real hand. And the sensors lend themselves really, really well to domain randomization. So this is one path for doing tactile dexterity with multi-fingered hands. This well-known by this point, reinforcement learning, sim to real with domain randomization. But there's another sensor that we've been developing in the lab over the last couple of years. And this one is very different in nature. It's based on PVDF, which is a piezoelectric material. And PVDF generates a charge when it encounters dynamic events, so making and breaking contact. And we spent a lot of work on coming up with a way to build these into a fingertip shape. So I have a fingertip that has this outer PVDF layer that is just incredibly sensitive to dynamic events. Under the PVDF, we also add off-the-shelf classic capacitive pads that give you sustained contact, information for sustained contact. So we think of this as a multimodal finger combining responses to transient events with responses to static events. And again, this morning we showed a live demo on this. I don't want to go again into the details of how we manufacture it.
But this is what the spike attack looks like in operation. What you're seeing there on the top left is the finger sensing the pulse of the person. That's how sensitive it is. You put it on your wrist and it can actually feel the pulse. It is by far the most sensitive fingertip we've ever built. So here you see the PVDF reading the responses to the dynamic events and this super, super nice sensitivity that we really haven't had before. But then we said, okay, great, let's integrate it into a similar robot hand, 4 fingers, the same kinematics. Now let's train some dexterous policies. And immediately the problem is that this sensor is incredibly difficult or essentially impossible to simulate. The PVDF, the charge that you get from PVDF, incredible signal to noise, we love it. But the nature of it is just, you're not going to wrap your head around it and very, very hard to simulate. So then the same pipeline of, do the RL in sim and then sim to real with domain randomization was just not going to work for this finger. So we went with an entirely different recipe. This was work led by Jean-Pang, the learning work here. And the recipe here was to still train a reinforcement policy, an RL policy in sim, but with a much simplified sensor model. So you can always sort of dump down your sensor to something that you can understand and simulate. Then once you can simulate it, you can train an RL policy. You do sim to real to get it out. And then we repeat this cycle on real hardware, where you take the current policy that's been trained on simplified sensor data, you roll it out on real hardware, you add exploration noise if you want to. Here we added another bit of reinforcement learning from human feedback, so RLHF, where a person would then take the rollout and label parts of it as either good or bad, so we can do offline RL. And then once you have these rollouts on real hardware, then you can do training on the real sensor data, right? So the original policy, the one up here, is trained in sim on a much simplified sensor model, and it just needs to get you off the ground. It just needs to get you the spark of life on real hardware. Once you get even better rollouts on real hardware, then you can do offline RL or imitation learning on the real sensor output. So you no longer have to use the simplified model. And here's what it looks like once we're done with that. So this is what the policy looks like. This is the base policy, just straight up out of reinforcement learning. And then we did fine-tuning to discourage high forces, right? Before we do that, right, if you just run the policy on a fragile object, of course, it crushes it. This is the base policy out of RL. But then after RL fine-tuning on real sensor data, so the entirety of fine-tuning is done on real hardware, then it learns to be extremely gentle. It learns to be super gentle. It learns to reduce the contact forces. And this can really only be trained on real hardware. Right? So it makes this really gentle contact that the spike attack gets no problem, gives it beautiful, beautiful signal to noise. So it can manipulate a range of fragile objects. And I think the eggshell is one of our favorite objects in here. So the moral of the story here for us was, how do you do tactile dexterity on multi-fingered hands? Well, of course, sim to real is one way to go. If you can't simulate it, well, can you at least simulate a simplified version? Let the simplified version give you just a spark of life. And then once you have the spark of life, you can do fine-tuning on real hardware to get to the performance level that you want. So you have recipes, you have ways at your disposal. So these are both ways in which we did tactile dexterous manipulation via reinforcement learning. What about the other pipeline? The pipeline which is just straight up imitation learning. And here I'm going to take a little bit of a detour and talk about imitation learning in general. And right now at our disposal in the fields, we have these two paradigms which have really allowed us to make a lot of progress as a field. One paradigm is the in the wild paradigm, where the human directly executes the task that you want done. Okay? For example, the UMI case or generalist AI, the person does the task through some interface. Like, for example, a disembodied gripper. The person takes a disembodied gripper and directly executes the task. And this paradigm has two massive advantages. One advantage is that since the person is directly doing the task, the person gets tactile feedback, right? Even when you're holding a gripper like this, or even if here you have the robot fingertips essentially mounted on your own fingertips, so you're not touching the object directly with your own fingertips. You are touching the object through this interface, but you still get tactile feedback. And we are so incredibly good at making use of it and interpreting it, right? So this makes the operator fast and effective. So it's really easy to collect data at scale, okay? So that's the in the wild paradigm. The other big paradigm is the leader-follower paradigm, where you somehow harvest the movement of the human hand and you use it as actions for a follower robot, right? And here, there's a physical gap between the human and the task. The human does not physically touch the object being manipulated. Everything is done through the follower robot, which is physically disconnected from the human. And this paradigm, you get no tactile feedback as the teleoperator, which is a huge disadvantage usually, but it has other advantages, right? You have exact actions and exact sensor data from the follower robot, right? In the wild paradigm, you have to figure out the action vector, and then the observation vector is inevitably corrupted by the presence of the human. In this paradigm, you have exact actions and observations from the follower, which is fantastic. And there's no embodiment gap between the follower robot and the policy that needs to be executed. Right here, you have an embodiment gap. The data is collected using a disembodied gripper, but has to be executed by a robot. Here, the data is collected by the follower robot and then executed by the follower robot. So there's no embodiment gap. So these paradigms, they're both great, very useful, but they involve a trade-off. What if we dig even deeper? So let's zoom in even more. Let's look first at the in the wild paradigm. And we like to think of it along these two axes, right? On one axis, how much are you constraining the human hand? And when you're executing the task through a parallel gripper that the human is holding, you are massively constraining the teleoperator, right? We have 24 degrees of freedom, and now all of a sudden we're manipulating through a one-DOF interface. So the operator is very constrained, but the embodiment gap between the demo and the robot is still low because the robot is using the exact same gripper to do the task. At the other end of the spectrum, if you're learning purely from human videos, here, the operator is completely unconstrained. There's no constraint whatsoever. The person is using the full dexterity of the human hand to do the task, which is fantastic, but the embodiment gap to the robot is very high. So you're paying the price in that sense. And this seems to be the trade-off when you're deciding what interface you're using for in the wild data collection. Are you willing to constrain human dexterity a lot in order not to have an embodiment gap? Or are you letting the human use their full dexterity and then you pay the price in terms of an embodiment gap? Okay, that's the trade-off. And the same trade-off actually shows up in the leader-follower paradigm, right? The dominant, some of the most influential papers of the last 5 years, the Aloha, and then diffusion policies. In both cases, they're using parallel grippers, again, massively constraining the human hand. At the other end of the spectrum, you have this paradigm where you are teleoperating via mocap. You're just tracking the human hand and then targeting, retargeting, remapping human kinematics to robot kinematics. So you're not constraining the operator at all, but then there's this big leader to follower embodiment gap that you have to solve via remapping of IK. Right here, there's no leader to follower embodiment gap. The leader kinematics and the follower kinematics, as far as the hand is concerned, are exactly the same. Okay? So when we're thinking about the field in general, these are the trade-offs that we see. There's the big trade-off between, which paradigm are you using in the wild or leader follower? And then when you zoom in on each of them, there is this trade-off between how much are you willing to constrain the human hand in order to reduce the embodiment gap. So this is where we're trying to see, hey, can we improve on some of these things? Obviously, there's a part in this plot where you have no reason to be, where you have both constrained kinematics and the high embodiment gap, so that's just bad. Can we come further down into the left? Okay. So there's two pieces of work that I want to show you that have that purpose. The first one focuses exclusively on the leader-follower paradigm, and this is work that we did at Tangent Robotics. So purely for leader-follower, we were thinking about this and saying, look, the fundamental problem is that the human hand is so flexible, so dexterous, and inevitably when you constrain the human hand to match the robot kinematics, you're going to sacrifice some dexterity. Well, what if you didn't have to? So what we did is we designed this two-fingered gripper. It has 4 degrees of freedom per finger, and these are the individual degrees of freedom. But the nice thing about this is that this makes 8 degrees of freedom tip to tip. So between one fingertip of the robot and the other, you have 8 degrees of freedom, which if you do a careful kinematic arrangement, means that now you have complete authority to position one fingertip with respect to the other in SE3 space. So you can achieve any desired relative position and orientation of one tip relative to the other. You even have a null space, a 2-DOF null space in many configurations, right? Because there's 8 DOF in total, right? So that means, of course, when you do that, the palm of the gripper has to cooperate and it has to move the right way, but we can achieve that, right? Because the palm is mounted on the robot. So we can do any tip-to-tip position and orientation, which in particular also means that you can perfectly track the human fingertips. There's no constraining. Whatever the human teleoperator does with their fingertips, so we're tracking the human's fingertips with EMF trackers, very standard, right? So whatever the human does with their fingertips, we can track with the robot. And in fact, the robot can do more. The robot can do relative fingertip poses that the human cannot do, right? So then we can teleop all kinds of fun, very dexterous tasks, and there's no worrying about, hey, am I doing something now that the robot cannot actually achieve? So what I'm showing you here, this is all teleop examples. We're having fun with it. And then, of course, once you're able to collect high quality demonstrations, it's just a short step away, right? You can do in-hand manipulation, right? And then from demonstrations is just a short step away towards autonomous policies. So these are fully autonomous policies. And by the way, what you're seeing here is the data from the touch sensors that we have. And at the base of each finger, so right here, what we have is essentially the popcorn sensors that I was telling you earlier about. So we spun them out of the lab. We did another round of engineering on them at Tangent, and we improved many aspects. We went to titanium flexures instead of PLA. We made them a little smaller, a bunch of other improvements. And We use them without even thinking about them. They're cheap, they're easy to build. You can have 50 of them in the lab and just reach for them, put them on and use them. So here it's unthreading, and then after each turn, it's checking using the touch sensors to see if the thread is still engaged, and then it takes it off. So all of these are diffusion policies trained via teleop and taking advantage of the fact that we have this, I'm going to skip this one, taking advantage of the fact that we have this full tip-to-tip dexterity, so you're guaranteed to be able to do whatever the human's fingertips will do. Yeah. Here, when the card hits the second finger, I like this little bump in the tactile sensor of the second finger. It's really nice and sensitive. Okay. So this is the TR01 gripper from Tangent, which is unique in having the full SE3 relative positioning between the fingertips, so you can do really delicate fingertip precision manipulation. So there's no functional embodiment gap. Of course, between my hand and that gripper, massive embodiment gap. As far as what the fingertips are able to do relative to each other, how they can position it relative to each other, no embodiment gap, nothing, because of the kinematics of the gripper. So trying to get towards this little part of the space in the leader-follower paradigm. So this is one line of work. And then the other line of work that I want to talk about is from our lab at Columbia. This is very recent stuff. The first time I'm talking about this, we just submitted this to CORL last Friday. And this one, we actually have very ambitious goals. We want to target both of these paradigms at the same time. So have a system that can do in the wild and leader-follower teleop, very unconstrained or less constrained human dexterity, and still with a low embodiment gap. So of course, that's a high bar to get over. And the way we're doing it is with this new system we call Ditto, Dexterous Interface for Transparent Teleop, and Joaquin, Caitlin, and Janpang led this work. And Ditto is two things. It's an exo for the hand that we very carefully designed the kinematics of the exo such that they constrain human tip-to-tip dexterity as little as possible. The exo should let you do whatever you want to do between your thumb and your index. And then it's a robot hand that has kinematically equivalent kinematics. That has equivalent kinematics, actually, I should say. I don't know if Maria is still here. Is Maria? Right. Maria talked in her talk about an exo that had equivalent kinematics to the robot hand that you were using. This is the same principle, equivalent kinematics, but what that also allows us to do is joint level bilateral teleoperation. So we use the exo not just to record the human hand position and map that to the robot, but also to render back to the human the joint torques that the robot is encountering. Okay, joint level bilateral teleop is a very well-known concept that's been studied in the field, good old-fashioned engineering, we like to call it now. But now we're using it in this exo for a hand that doesn't constrain dexterity. And a fun bit about this is that you can either do leader-follower teleop, or you can just go ahead and execute the task directly using the exoskeleton. You put the exo on, then you use the exo to do the task, and you're getting in the wild data, essentially. Right, so this is a little bit of the kinematics. We thought long and hard, and Caitlin led this work thinking about the human hand kinematics, and the exo and the robot hand have joint axes intersecting the same way as our best models of the human hand. Of course, the human hand can be modeled in different ways, and it's not, this elegant exact axis like we have in robotics, but this is, our best guess. And then we were very careful to have similar joint axes in the exo. So this is what it looks like when you're collecting the paradigm, right? It gives you all this, side to side movement, this front and back relative movement of the finger. unfortunately, this being super new work, and because the video deadline hasn't happened yet, we don't have a good video of in the wild data collection. But you can imagine doing the task, but directly with the exoskeleton. So not in the leader follower parallel. Okay. And then once you have this very dexterous data, then of course you can go ahead and train, again, diffusion policies. And the nice results that we got out of this, so you having force feedback, what did I say, sorry? Oh, 3 minutes, excellent. Having force feedback in the exo as you're collecting data, it turns out is both better in terms of success rate of the demonstrations, but also significantly reduces how much spurious forces you are applying to the environment when you're teleoperating. You're able to be much more gentle with the environment if you have the feedback while teleoperating. We were talking about this in the VTalk workshop this morning about success metrics, performance metrics for manipulation. And not applying very large forces to the environment is a great success metric. And having force feedback on the human side allows you to collect demos with a lot less application. And the thing that we need to care about without sacrificing dexterity. This is what makes the human hand incredible, right? The articulation, the dexterity, and the dynamic range in torque sensing and tactile sensing, okay? So DITO is, all of these things come together, the one-to-one kinematics, which really makes joint level force feedback work. If you don't have exact kinematics, then you have to reason about rendering similar forces at the fingertips, which is much harder. If you have exact kinematic equivalence, then you can just do joint level bilateral teleoperation, which makes it much easier. And it enables better and faster demonstration collection. And because of the carefully designed kinematics, it constrains the hand very little. We have the results in the paper where we actually looked for all of these tasks. How much does it constrain human hand? If you let the person do the task just with their own hand, how do the fingertips move relative to each other? And DITO can do essentially all of those relative movements, 97% or something like that. All right, so to conclude, we're having a blast. I hope everybody here is having a blast because there's never been a better time to be in manipulation. Things are moving like never before. So, let's enjoy it. But still, all of these questions that were asked, maybe we'll get to talk more about these in the panel. Big questions still out there, multi-fingered hands. Is that, how much do they provide us versus a bimanual system with parallel grippers? I'd love for multi-fingered hands to be the clear winner there. I don't think the case is, cut and dry. For sensing, this big debate of, it turns out that vision only is more capable than we thought it would have been. Where's the guaranteed necessity for touch? Is it just a bump in performance? Is it a qualitative difference, things that you can do with touch, you cannot do without? And then, what's the right learning paradigm? We're investing in these combos, imitation learning, reinforcement learning. As I just showed, both are possible for tactile multi-fingered dexterity. Are there completely different paradigms out there that we haven't even thought about that are going to give us another, major step forward? And hopefully we'll talk about a bunch of these questions and more in the panel session. Thank you.
Thanks a lot. I really like the mahjong part. I look forward to play mahjong with the team and learn together.
We hope the results extend to Scrabble as well. Generality.
Okay, so we only have limited time, so only open to one question. I really want to ask because I see actually in your slides most of the demos are by 4 fingers or 2 fingers. So I would say actually for most of the human demonstration, our activity on hand prefer these three fingers are fine. So what do you see this on this one?
Yeah. That's an excellent question, right? So all of this, so even, whether it's this, Dito or the TR01 hand, very dexterous, many degrees of freedom, but, 2 fingers. I'm actually thinking, hey, am I allowed to talk about this? Because this is a workshop on multi-fingered hands. And I said, no, it's 2, right? It's not a unifinger. So it's not a unifingered hand, so it's okay, right? So yes, maybe there's this intermediate step from parallel grippers to more fingers where we get, 2 fingers, but very dexterous, right? We can do a lot with 2 fingers because we have 7, 8, depending how you count, degrees of freedom just on the thumb and the index. So very, very capable. So we're trying to see how far we can push this idea. And then, yes, we are, for example, at Tangent, we're in the very advanced, we'd like to think, with a 3-fingered version that's going to have the same tip-to-tip dexterity between the index and the thumb. So you don't, compared to this one, you don't lose any dexterity between the index and the thumb. But then the 3rd finger gives you nice, stable tripod grasps. And then we hope to also get nice transitions from fingertip to power grasps, which are still very important and back. So we think that the 3rd finger is going to give us a quantifiable performance improvement. But still a lot of things to be done with 2 dexterous fingers.
Thank you. So now, thanks again. Let's move to the demonstration of innovation. Please, the speakers in the audience go to the stage.
Working on Dexterous manipulation and Lepora in Switzerland. So I'm going to moderate today and discussion about Dexterous manipulation, also Tactile manipulation. And so first of all, as a researcher on Dexterous manipulation, I always get a question. People will ask, okay, parallel gripper is much simpler than multi-finger hands or anthropometric hands. And it's also more robust and more reliable, and from control perspective, easy to collect data, which is in this low dimensional and easy to learn policy. Why do you spend time on working on this topic? And my answer is typically okay. Because it's hard. I like solving hard questions as a PhD, and so this is the reason. But how would you to convince people like why won't you work on Dexterous manipulation and convince people to pay more attention on this topic? Maybe we start from Maria.
I think that's a really good question. Sorry, my voice is feeling a bit. I would say go play with grippers, and immediately you will see at some point where you have some good policies that actually there's a lot of things that grippers cannot do. One of them is the obvious one, which is a power grasp. If you have to hammer something, it's just not possible with grippers. And we've been looking at that. I won't go into the details, but there is actually a plethora of tasks that you are just not going to be able to solve with grippers. I think 2 grippers by arm, it's very capable, but you're still going to find a lot of questions and things that you're not be able to solve. So honestly, to me, it's like, yeah, just become block, multi-finger dexterity. There's no way otherwise to keep them moving.
Does this work? Oh, perfect. Okay. Maybe a simple answer is, I showed this with Wonder. We took the Orca hand and we artificially made it a 2-finger, and we compared the performance to 3 and 5, and like introducing these degrees of freedom, and we found that there was several of these 18 tasks that we chose that couldn't even do it or were very slow with it. So that's my answer, and I mean this extends to more things.
Yeah, everything that has already been said, and maybe adding to it that I think it's also a question of throughput potentially, right? Because if you not only can you now fundamentally do some tasks that you cannot do with grippers, but maybe the tasks you can also do with a gripper, now you can do them faster with a dexterous hand, because you can just use in-hand reoriented objects in your hand, for example, just as an example.
Yeah, I think that's exactly true, right? So if you have a gripper, you are relying on the degrees of freedom of the arm for a lot of the controllability of the finger manipulating, or the other arm, exactly.
And you're relying, if you're doing force sensing, via joint control, you are relying on the joints of the arm to sense and to control the torque. And all of those are very far from the finger manipulating. And robotics 101 tells you that your manipulability ellipsoid gets smaller as soon as you start putting the degrees of freedom really far away. All kinds of bad things happen. When you have all of that control authority really close to the object that you're manipulating, you can be so much more precise. You can have so much more delicate force sensing. So there's a lot of advantage to be gained from taking the control authority and bringing it very close to the object that you're manipulating. So that's a big one. And then exactly as Maria was saying, power grasps, and not just power grasps, even if I can borrow your phone for a second, just as a prop, right? Just this tripod grasp. Oops, see, right? If you hold it by the end, you have to squeeze really, really hard if you have only 2 fingers. Once you have 3, you have this tripod grasp so much easier, right, to hold it stably.
You still not grab it this way. You would never do this, right? You would always do this.
And then you would transition it, right, into a power grasp. By the time this panel is done, you're going to get your phone. So many potential advantages to more dexterity closer to the thing you're manipulating.
I've definitely came with my answer, which is, the human hand's got 5 fingers. What's the point of our field? It's to get to human levels of dexterity or past it. But we need to there's arguments for how many fingers we actually need. Apparently, according to surgeons, losing your index finger is the one to go. The little finger's more important than the index finger, apparently. But anyway, we've got a long way still to go in robot dexterity. We still, until we can call out a robot handy person to fix your sink and paint the walls and do your rubbish and look after your kids, then we've still got a lot of dexterity to figure out how to do. And we've got an existence proof. We've got a multi-fingered hand that every one of us has to do.
Thank you very much for the answer. Yeah. Now we are convinced to focus on dexterous manipulation with more understandable.
This will never be a question again, right? So.
Okay. Now, also in today's talk, we saw a lot of different multi-fingered hand, like robot showed, the orca hand, mimic hand, 5 hand. Then actually, do you consider to train a simple policy for across different hands? Because as we know, Jeannette also mentioned data collection, calibration using that hand for the dexterous manipulation is very tricky compared with the parallel finger. And how do we make these also data shareable across different multi-finger hands? Yes. Any comments?
Yes, we consider it. We have a couple of works in the making, so we're trying to share this, mostly because students don't want to be recorded on every single hand. This cross embodiment, that's been around now. I saw talks now about this, right?
Whatever.
It's been, so yes, ideally, even the 2-finger hand community does this, right? Look at physical intelligence, everyone is doing this, right? So you also talk about this in your talk. I think it's very hard though. So we tried to find actually a human hand as our sort of embedding space in some way. It's one project where we sort of trying to just align it all back to the human and using that as a way of aligning it to whatever design change happens. So we have something in between and taking the human as the baseline, but I'm sure that's not the end of it.
Maybe Mariam, yes. I saw a video on your slide where the control policy from Gemini robotics control the parallel grip and dexterous hand at the same time. I guess that's a single model. How is that realized?
So, without going too much into the details, I think there is no way in which we're not going to be able to solve that problem, right? Because there is no way there's only one hand out there that we need to control. It's going to be multiple hands, it's going to be very soft, very gentle, one type of hand is going to go into some place where everything just kind of cut your hand. Definitely going to have a different environment that's much more robust. So I think the need for being able to transfer from one hand to the other one is just going to be everywhere. So we have done work showing that even in one crazy environments you see transfer. I don't think this is going to be the hardest problem Because honestly, we have 5 fingers. We all have seen AI. You can do things, you can do some transfer. So I think it's going to be a problem that we're going to face, that we're going to solve. To me, it's more important of, okay, you have one hand. Get it to do everything you need to do. To meet the generality that we're going to need to bring it to our system. It's less about transfer between robots, between humans. I think that's going to be much more global than actually really understanding how do you do forceful interactions, how do you really convey all this information that humans can very easily in our robots life.
Jeannette, you mentioned also in your talk, like with sharper hand, with more reliable factor sensing, it's more helpful. But before that, maybe you have a not that good hand. And so across these two different hands, do you use a single training policy, or just because of improvements to the hardware, it's better improvements in the performance?
Yeah, just one clarification before I answer the question. The sharper hand does have tactile sensors, but we haven't actually used them yet in any of these, which is super interesting direction for the future, but we haven't yet been able to do it. So this, what you saw was actually completely without just vision based. Like given that, so the difference wasn't, so we started with the Allegro hand, right, like, which is like double the size of my hand. And then it has, of course, 4 fingers. It has to be cooled down by putting a stand next to it while it's operating. Things like that. So, but you know, that doesn't matter in simulation. So actually, what turns out is when we exchanged this Allegro hand with the sharper hand, it made learning actually much easier. You know, I think it could have something to do with the size as well, but I think it's maybe more a kinematic question, right? Like, of course, the Allegro is, for example, very big, so like holding tools, for example, becomes harder because also the palm is so big, right? Like in the Allegro hand, for example, so it's like hard to really grip something thin and skinny. So I think, yeah, I think it somehow makes exploration for RL somewhat easier to have this particular hand.
Great, thank you. Matei, you just mentioned your demonstration had a lot of video about using 2-finger gripper, Dexterous one, and you just mentioned you have a 3rd one and 4th one can be have a more stable graphing. And how have you considered how do you transfer the policy already trained for the 2-finger hand to the 3 or 4 one?
So the 3-finger hand hopefully should have strictly a superset of capabilities compared to the 2-finger hand, right? So we wanted to make it that it only adds, it doesn't take away anything. But from my perspective, I'm a specialist. I'm a specialist. I have tremendous respect for generality, both in terms of one policy capable of, assembling the spark plug now and then 30 seconds later making the peanut butter and jelly sandwich, and generality in terms of one embodiment to another. But just my natural instinct is we're going to do specialists. Specialist policies, we're going to try to extract every ounce of juice that we can, and that the way you get to extremely high performance fast is with specialist policies. And also because, I love full stack work. I like to say, I take pride in saying, we're a full stack lab, we build the sensors, we build them into hands, and when you do that, right, you want to extract, you want the learning bit to extract all that it can from the hardware and the sensing that you've built. And if you want to do transfer, that almost kind of implies you have to give up on using some of the unique capabilities of this piece of hardware because you also want your policy to transfer to that piece of hardware. Now, all of a sudden, the policy has to work with kind of the least common denominator, the smallest set of capabilities that all of your hardware has. And I just want to say, look, we're going to specialize. We're going to specialize the hardware to the learning and the learning for the hardware, and then we're going to specialize in terms of the task, and we're going to make them as performant as we possibly can. That's the first thing that we're trying to do.
And the reason is because that's how it can be the most useful? Sorry, my question was like, I'm asking like why, and I'm wondering if the reason is because you want to make it the most useful for the end user.
Well, right, it depends on the end user, right? If the end user is okay with, you know, the robot's gonna do one task, it just needs to be super fast, super robust, and it's gonna do this for 5 months, and then we're gonna spend 3 days retargeting for another task. For that kind of user, absolutely, it's clearly better to specialize. If the user is more, you know, take the robot to come and fix your sink, and, you know, maybe also take care of the kids, then you need a generalist, for sure. And I think both are just as valuable. All I'm saying is that I think our lab is better at the former, and there's value in both of them, so we might as well focus on this one.
Maybe make one comment.
I want to understand, why do you think that if I have multiple embodiments and I'm trying to abstract something that they have in common, or trying to abstract something in a common space in some way, why you then think that all of the hands will suffer from this? I.e., they will then only be able, because I'm not sure I agree with that argument.
I guess the point that I was making was that if, you know, one hand has really high quality tactile sensors and then another one has very crude or not at all, then if a policy is to transfer between any of them, then the policy has no choice but to not make use of the tactile data in order to be able to function on the hand that doesn't have tactile sensors. And then the good tactile sensors on the hand that does have them are wasted. Maybe it's possible to train a policy, one policy, it transfers on all hardware, and it uses the best features of each hardware individually. Maybe that's possible. It's even harder though.
I mean, I completely love Matei's work, and I think my inclination say yes, specialist policies will definitely do much better than that you're aiming at. Unfortunately, reality has hit me here recently, showing me that actually you add dumb data to your policy and it performs better. The Dexterous stuff that you really wanted to see doing well. I think it's because the dumb data still has lots of the physics, lots of the recoveries, lots of the mistakes. So even when we go into multi-embodiment, which is again this data, this should not help me. I would rather just spend my cycles training on the task that I really care, that is very extra, so this embodiment that I really like. We keep on saying that, damn, I just need to put less weight into my beautiful data and add more of the others because they keep on improving for the task that I really care. I know that some models are really big, they have lots of capacity. We are lucky enough at Google that our models are pretty big. But for us, it's been a surprise that you want to just focus on fine-tuning on one single thing really good, and then you're going to be like, well, actually, I'm going to put on my data. So, learning here from everyone.
Yeah, maybe. Yeah, you also have an application about in-hand rotating, but with also allegorical hand, with legal hand. Have you tried to unify them? Because you train with IR, and IR also consume a lot of resources. Have you considered to get a policy across different hands?
Well, they kind of are unified in the sense because they all use the same simulator and the code, same code base. I mean, that took the person hours developing all of that, retraining it with a different morphology of hand. It's not that much extra work. It's basically just press and go on the computer after you it's loaded in. I mean, on this generalization thing, I mean, so Bohg, who's done some of this work, is in the audience. For a while, we just had disembodied fingertips and forgot about the rest of the hand. You know, that's another way to do it. I mean, obviously we use a lot of our, rest. We don't just use our fingertips to manipulate. But for a lot of tasks we kind of do. Then why bother with the hand? We just have the floating fingertips with some constraints, and that's automatically cross embodiment because there's no hand.
So, question to you all: what do you think about the palm? Because we're talking about multi-fingered here, but actually we have a very complex palm overall. Well, nature does this in many animals who have complex palms. And I found it actually extremely rich to actually just investigate the question of that. So why are we only talking about fingers?
I also want to bring up the wrist. Our wrist is very
Let's go further.
I guess there's a trade-off in terms of complexity, right? Like, so, for example, the example of like, oh, we exchange allegories with the Sharpa, and then suddenly learning also works better without changing anything else. And so I think it's probably similar, right? Like if you put a wrist like the one we have into it, instead of the usual stupid one that we have in our normal arms, or a cool palm, right? Like you can articulate also. It probably will help you to learn fast, I'm guessing.
Yeah, I think you're completely right. The palmar arch, this subtle degree of freedom that lets you have this arch, so massively important. If you ever try to grasp something like a baseball bat or a bottle without arching your palm, and it's impossible. You cannot use it. You cannot grasp it. It immediately goes away. And completely agreed on the wrist, right? The same concept that we have these degrees of freedom so close to the fingertips, and no robot arm has that.
I guess it's kind of tricky to build a adaptable palm. But I think it's super important. I mean, people have done it. Microphone. Oh, can't you hear me? Violently agreeing again. The palm's critical in dexterity. So interesting, all the muscles for moving our hands are in our forearms, apart from the ones that we configure our palm, they're within the hand itself. It's kind of hard to build that in an artificial hand, but there are designs out there for it. Yeah, critical. And wrist as well. So a lot of almost all industrial robot arms don't have that degree of freedom, and yet, you know, that's probably critical for the most dexterous tasks. As I think we saw recently with the Ruji hand and the Gemini demonstration, it's a Genesis demonstration that had wrists on it, and I think that's probably key to the dexterity. So we need if you could talk industrial arm makers into putting a wrist at the end of it, that would be good.
I think particularly if you want to walk towards dynamic motions, minimizing null space motion, then it's super crucial to have that articulation, right? You can have a 7 degree of freedom robot arm to trying to get there, right? But we should have it in the hand directly. Actually, it leads to this constant discussion when you're developing hands, where do you cut them? Like we make a lot of, as you saw, tendon-driven hands, so we always ask actually the real estate from the robot arm manufacturer in some way. Right? We don't want them to build the wrist parts. We don't want them to do that. We want their arm to be cut further down there because it's actually part of the hand. So how do you see what belongs to the hand and what belongs to the rest of the body?
Why do we need to make a cut?
So I think the reason why we need to make a cut is depends of, I mean, in our case, very practically speaking, what we were also saying, we have all of our muscles in the forearm, right? So if you take a Bushi hand, it was designed to be centric with a higher gear ratio in the hands. Very convenient because you can directly place it on a franker. You can place it on all of these arms that already take care of the 7th off all the way up to the flange or the end factor. But if you want to now make, I mean, that's my argument, if you want to make basically antagonistically driven hands that not only control force but also combines, you need to have the ability to drive tendons. I strongly believe in that, and then where do you place the actuation for it, such as motors, muscles, etc. And then you start coming into this conflict.
But then you run into the inevitable difficulty that we have, first of all, essentially zero friction cartilage that the tendon goes over, and our joints are actively lubricated. We have synovial fluid in the joint. So we have these zero friction, actively lubricated tendon paths that our tendons go through, and we don't have that in robots. So how do you see that compensating for that?
That's why we do biohybrid robots.
What kind?
That's why we do biohybrids.
Yeah.
Which are actually from cells, which trying to imitate that bit by bit, but it's far away. Yes, I agree.
That a bit for this. I think there are some self-lubricating 3D printable materials in there as well. Inflated bearings. Wouldn't it be brilliant if you could buy an industrial robot with lots of tendons hanging out at the end of the arm?
And you just attach to it.
But you just attach to your tendon-driven hand. Yeah, that would be brilliant. With a wrist as well.
Yes.
Okay, so for multi-finger hand, we have a lot of variants. Like some you utilize the wrist more, and some utilize the palm more. And how do we consider like across different hands? How when during the educational and rules of learning, how do we, for example, one hand utilize the wrist more and one hand use the palm more? And there's some constraints like with a simpler hand, another hand is not reachable for another hand. And how do we encode this constraint in this learning as an inductive bias to accelerate the learning performance, improve the task performance also?
Just to clarify the question, like you mean if you have all of these different embodiments for hands and
yes.
different capabilities, how do we transfer again, like one hand together? Is that what you're asking?
Yeah. Also, in one case, when we want to transfer, also if another hand has more capable in the wrist, how do we make the learning algorithm be aware of, okay, I can utilize the palm or wrist more to finish this task?
Yeah. Okay. So, I don't know exactly how to do it, but yeah, maybe this goes back to this question of how cross embodiment is done, even implicitly by just chopping in more data into a big model. I think conceptually, I think you shouldn't pay attention to the degrees of freedom of the hand or like how to exactly maybe retarget from one hand to the other, but it's more about what does the hand do to the environment or to the object or something like this, right? Like what is the effect of a certain action it has? Now, whether it does it with a cool wrist or with the palm, in the end, it's not super important. But there must be a mapping somehow that says like, oh, okay, if I want to achieve this effect, this is how I move my hand, right? Like, so there has to be some example data there, so that's maybe what Maria is also talking about, right? Like you put more crappy data in there or simple data or something like that, right? Like that's not necessarily directly related to your task, but it does have this physics in there, so it's clear like, oh, this kind of visually looking contact is creating this kind of motion. So therefore, you know, if I try to do this with this different hand, maybe by flicking the wrist that I now suddenly have, and you know, that's how I achieve the same effect, which is ultimately what my goal is, not the movement of the hand itself in a certain way. Yeah, that's kind of how I would think about it.
Great. Yeah. Maybe Maria. When you train to do large scale training for general robotics, have you utilized any tricks to add this inductive bias into it? Tell them all, please.
Putting you on the spot here.
Not going into any details.
I mean, what I would say is that we definitely see transfers across embodiments. And I think that's probably the most important thing here, which is that if you think about, and it goes back to what Jeannette was saying, we really want these models to understand how they are affecting the world and what the actions mean in terms of that interaction, right? So that means that if your hand suddenly has some constraints, maybe you're going to have some data that will come from SIM that explains some of those constraints kind of indirectly, implicitly into the data. The model should be able to kind of understand from that what its motions, that what its actions commanding actually imply in terms of the actual interactions of the world, and therefore adapt to it. So I wouldn't say yes, because I have all degrees of freedom or less, more about what am I trying to shift. Do I understand the world enough to understand that this motion will move things towards the left, right, and of course as we go into more complex skills, this will require more intelligence. But I think it's less again about the particular requirements of each hand, I will think about more of the analytic. And then on top of that, I think what Matei was just saying is if you are able to collect some quality data that kind of bridges the gap for that particular embodiment, I think then you have a powerful recipe to really maybe give the extra mile. Maybe your model is lacking because maybe, like we've seen multiple times that some robots miscalibrate and we don't find it. And then you look at it and it's like, come on, it's like, should be here and it's there, but the model was still working. So it takes us longer to find these calibrations. And it's because, yeah, of course, I meant being here and I was meant being there, but the model is still capable to that, even with these are beyond complex. So I feel as models grow more intelligent, in a way, we might be able to see that these kind of nuances become a bit easier to deal with.
So I'm curious to hear from all of you, because you're spending every single day of your lives probably thinking about this problem. Where should we move towards? Okay, wait.
There was one time last year when I didn't. Like on April 3rd last year, I did not.
Okay, I should have formulated this differently. What I was trying to say is, we have large-scale simulation, and we have large amounts of tele-op data or other sort of human collected data. Let's say we don't want to use any of this. How can we really sort of, in the real world, get started? Because we only talk about IL and RL so far, right? Yeah. Where should the journey really be going? What should we be thinking more about to start tackling this problem? Because I don't want to see my students doing tele-op. I don't want to need to have huge amounts of compute necessarily either. Or is that the only answer?
Right, this is what we call in our lab the spark of life, right? Where do you get the spark of life from? And then you can optimize, you can improve, you can train, but where does the spark of life come from, right? Yeah. And I guess if it's not imitation learning or reinforcement learning, then the only other paradigm we have is large models, right? It's foundation models or VLAs or trained from internet scale data. But that one, I've done the least work on that, so I feel like other folks in this panel are more qualified to talk about that approach. That paradigm.
So that's like modality transfer, something, right?
I'm gonna joke a bit, but what about world models? You just have a world model, you just simulate what you think is gonna happen, not simulator, it's the world model, and that gives you the answer of what you need to be doing, right? I honestly think world models might surprise us. I have done zero work, so I'm not the right person to talk about this, but that could be just another way to think about the problem, where if things are really good, you may be able to navigate this space. I know very little about this, but if you want to learn alternatives, you can also.
Thank you.
Yes, world models, and then also I think in robotics, robots are complex systems. We talked a little bit about this last week as well. So I think there's something contributed every day. That's why robotics is so cool, because you can have any background almost, and you can still contribute something to robotics. So you can grow robots now or muscle. I mean, who would have thought? So I think you can come in from whatever angle at robotics, and this is because at every layer of the robotic stack there is something to work on. And I feel like all these learn models, they are very cool because they, for the best case performance that we see in them, which are shown to us in videos, thank you, not explain what's behind it. I mean, that's really exciting because it's definitely a much higher bar compared to what was possible even a few years back, right? And so that's very cool. But it's also sitting on top of the control stack, right? Like that is now kind of invisible. But from what I'm hearing, I don't know who told me today, it's like very difficult to find people who know robotics or control or anything anymore, but they are actually really needed for these startups, but also big companies, right? And so I think there's lots at every layer of the stack of a robotics system. There's something to do, including hardware, including local control, including the middleware, quite frankly, and all the just all the infra, and then of course also the high-level reasoning and so on. So there's I don't have like this one number that we should be like. There is so much to do for everything because the only thing we see is like best case performance. So it becomes useful to anyone, anywhere. It's going to take some time.
I'm curious. Let me ask a quick question of the audience about the word models. Generative video models trained on internet scale data, capable of producing beautiful, ray tracing quality or photorealistic videos of anything you want. Who thinks that generative video models have some deep, innate understanding of physics?
That's a trick question.
One person out of the entire audience. Okay, well, let's
Ask the opposite.
Okay, who thinks that they have no understanding of physics whatsoever and all they're doing is pixel level overfitting? Another you should and I guess everybody in between is saying, come on, Matei, that's such a complex problem that you're dumbing down.
No, you're making a black and white.
Right, yes. Yeah. I think, again, knowing too little about this maybe to speak, I like to believe that there is an understanding of physics in those models, just like language models turned out to have a lot more understanding of abstract concepts than we originally thought. So I think that generative video models, we will be able to get them to understand physics, and we will be able to extract that knowledge along the lines that you were talking about as word models.
Just something to add.
Come back.
So I just saw on Friday, Nathan Colton was giving a talk back in Zurich, and he showed a result where he had learned a model that could basically sort of rearrange various types of problems in the 2D space. And they could go into the model and could extract the thinking process in a way where visually they could see that the model was actually learning these operations. So they were basically disintegrating the full stack of the learning pipeline to observe actually that they think in electric sheaves. That's part of the name of the paper.
I had a comment I was going to say a few lines back, but I'll try and fit it in. Classical control. You know, you don't just have to throw your biggest GPU and computer at it. Classic control can get you a long way, and what you should be doing is combining classic control. Well, what I mean by classic control, PID control, what people, roboticists used to do before AI, modern AI came along. Combine that with the modern AI. Take the classic control as far as you can, and then you've got an easier problem to solve for the rest of it. You can go along with. I mean, my lab has done things like goal-based tasks. Getting the code from say here to there using touch alone, just doing this kind of thing. Just did it with a PID controller. Whereas now I think most people would just throw some complicated sim-to-real RL with policy distillation, and with an LLM tagged onto the end as well. That's it.
Thank you very much.
You seem convinced.
I think this brings us to education. Maybe, right? Like people forget that we know things.
Okay, looks we also need the help from the large language model, foundation model, but the robotics we still have to focus on the representation of the robot, like what's a good format we want or outcome from the foundation model we want to obtain. So due to the time limit, I'm going to close this panel discussion and take maybe only one or two questions from audience.
The person that lost one point.
I think this question is for the entire panel, but specifically for Matei. One of the comments you made during the discussion was that you love specialism and you want to create specialist models. One question I had is that what are the road to specialist models like through generalization? Because that's what we found in LLM community. Like to get very good coding agents, they had to first train good language models. Do you think there's a parallel to be made for robotics? To tackle the really hard problems, we need to design a curriculum through more general purpose tasks.
Or I guess I can try to be loud. So, well, okay, I mean, this ties back to the point that Maria was making earlier, right? That that data from some tasks will probably help you with this other task that's not those, and that there's value. And actually, in order to be a better specialist, you should be a generalist. And being a generalist will help you be a better specialist, and that's possible. And at some level, at some abstract, high enough level, that's entirely possible. What I'm talking about mostly is the lower level, the system 1, system 0, if you wish. Right? We're stuck because we started with system 1 and system 2. System 2 at about 5 hertz, system 1 at about 20, 30 hertz. Then we need system 0 at 200 hertz, and now we're stuck because if we need something below, we're out of numbers. We don't have anything to put under system 0. system -1. So what I'm saying is that yes, at system 1, system 2, system 1.5, I think there's a good possibility that yes, being a generalist will help you be a better specialist. But still, even for us, at the end of the day, for any one specific task, there's no substitute for you training on your own embodiment at that task, and it will make you better. And yes, maybe it'll make you better at some other things and so, but if you want to get better at chopping onions, chopping lots of onions on your own embodiment is going to make you better at it, no question about it, and there's no substitute for that. And that's the kind of value that I think we should try to extract.
Thank you very much. Due to the time, due to time limits, we have to close this now. If you have more questions, please discuss with the speaker in private. Okay, thank you.
Foundation and Engineering Research Center, which is really focused on making robots more dexterous. Exactly the topic that we had here today. If you look at the website, you will see my name listed there among the organizers. But really, I did almost nothing, and the real organizers are sitting right up here. So I personally am extremely grateful for all the work they put into this. We could have kept that panel discussion going for another hour, and the audience and the panel members themselves would have wanted to, right? Just a great set of topics, a lot of interest, a lot of passion around this, and really fantastic speakers today. So I'd like you to join me in thanking, after I announce their names, the real organizers of this session. Kenny Shaw, is Kenny here? Kenny Shaw, Shuang Li, please stand up when I say your name. The big boss of the whole thing, Haoji Chi. Outstanding workshop. Really enjoyed it. Thank you so much. As you know, we have 3 Best Poster Awards to give out, and those awards are being sponsored by our sponsors, Franka Robotics and Agrawal Robots. And we have here today Sven. Sven, you're going to be presenting the awards. I'll announce them, but you will be presenting. I'll give you. I didn't know. That's great. And Sven, you'll do it. Co-founder of Franka, thank you. So we have 3 award winners. When I announce, please stand up and come to the front. The first winner is CoreGrasp, Coordinated Contact Control for Adaptive Dexterous Grasping Under Uncertainty. Okay. Second winner, Sim Tool Real, an object-centered policy for dual step testing.
Yes, please. One, two, three.
Our third winner, a U-Skin fingertip with a tactile fingernail for contact-rich dexterous manipulation.
One, two, three. Last. Thank you. $500.
Oh, I should also mention that due to our sponsors, each winner gets $500. So congratulations to all of you. I'd like to thank you all for attending this session. There's a welcome reception starting in half an hour, I think. And I wish you all a wonderful